Good morning, everyone. Good morning, everyone. Good morning. Good morning, everyone. Good morning to everybody online, and good morning to everybody on site. We have a weather forecast said it was going to rain all week, but it seems that the sun decided better, and we're pretty happy. So, in one word, Benoit and myself are going to chair the first session, which is very short. It's just a welcoming session. And I will make a presentation to welcome you to ESRIN. And then we're going to have some changes in the program. So we printed the program, and as soon as we printed the program, of course, we made changes, or we were asked to satisfy some requests of changes. And we see people online here. Very good. Hello, hello, Margit.
Hello,
Liam.
good morning.
I don't know how many people there.
Hello,
Okay,
good morning.
so. Okay, so we'll start with the first presentation, which is welcome to ESA. And I will do that here. Second, I will turn.
We cannot hear you, Jérôme.
All right, thank you. Okay, there we go. Can you see the presentation online? No?
No, at the moment not.
No. Would it be possible to share the presenters' slides from the computer?
What?
We can see the speaker, we can see you, but we can't see the slides. Yeah.
Okay, so. Oh, I thought this was already launched. Okay. All right. There we go. Okay. Well, welcome to the European Space Agency, and welcome to the ESRIN establishment in Rome, which is essentially focused on Earth observation. And I would like to just present you. This is for people online, so they're flying over and they can see where we are. We're right behind the E of excellence. I mean, the third E of excellence here. And okay, what do we do here? We do Earth observation mainly, but we hosted the Vega launcher, the small launcher that we have next to Ariane, and we have corporate informatics, security, contracts, personnel, sat management, communication. We have, like in 2019, because that's the statistics we're based on, because in 20 and 21 they were a bit perturbated. 50,000 visitors per year here, and there's more than 800 people working on site. So I would really like to express my warm thanks to the co-sponsors of this event, CNES, GWEX, WCRP, GWEX, and Jet Propulsion Laboratory and NASA, and NOAA. And in particular, I'd like to thank Benoit. Benoit Messignac came to me and said, oh, it would be fun to organize a workshop with ESA and so on. And so he seeded the idea of having this workshop here, and then he guided the organizing committee, Maria Haguba, Seiji Kato, and Tim Boyer, and your most humble servant. So a few words on what we do at ESA in the Earth observation science, application climate. So it's a small opportunity for us to showcase what we do for people who don't know much ESA. So basically, we're trying to push the frontier of science engaging the community, developing new algorithms, new methods, new products, and to advance earth science. We contribute to scientific campaigns, or at least we request them. We do also training, education, capacity building, try to be open to open science, develop tools for the users, networking, partnership, and we try to transfer to the projects and what we've learned of the past mission to design better the future mission. Our strategic activity is to have a good coordination with the European Commission, to develop clusters here, and I'll show you a few examples. We have a science hub where we host research fellows and visiting scientists, and the idea is to advance the understanding of Earth's system, and developing the twin Earth and so on. So the cluster that we've set up is the ocean cluster, which I'll talk about, and the carbon cluster and the atmosphere science cluster. But we're going to develop 5 more: biodiversity, extremes and natural disaster, agriculture, the water cycle, and solid Earth, internal geophysics, magnetic Earth, and so on. Basically, the idea is to have a continuous dialogue with the scientific community, and this workshop is one of the ways that we have continuous dialogue, and promote a community approach to the ESA science, and develop work plans for the years to come, and with ambitious goals, and so on, promoting, of course, collaborative research with Horizon Europe, and being open as much as possible. So we'd like to transfer science into solutions for society, enhance knowledge of the Earth system, and then develop novel and enhance of the system. This is the ocean cluster. So you see there's 35 projects ongoing, and the 2 that are circled are about ocean heat content, Mohican, which was a permanent open call that was won in a very competitive framework, and also the Atlantic Regional Initiative activity, ocean heat content. And if you want to know more about this project, talk to the Magellan people that are here, and to Benoit also. And so basically, we develop a strong partnership in Earth science. We got a formal agreement 3 years ago to have a common goal to work together and respond to challenges that our society is facing today. And so we try to launch activities in good coordination with Horizon Europe. And these are flagship actions. And one of the flagship action is something I launched, which is the sea level and coastal hazard. And it's about developing an integrated approach to Earth system science with Earth observation, but also in situ network modeling and cross-disciplinary research. Okay, the 7 global indicators of present-day climate change have been defined by GCOS and WMO, and 2 of them are of my high interest. One is sea level, and the other one is ocean heat. And in the past 30 years, I've been developing these activities focused on different objectives, different goals. And in red here, you can see what we've been doing at ESA, the Sea Level Climate Change Initiative, the Sea Level Climate Change Initiative follow-on, which is going closer to the coast, and is sea level going rising at the coast, the same as the open ocean, and also the 2 projects which I mentioned earlier, Mohican and for the Atlantic Ocean heat content. And well, all the information that was developed and published and so on are on the websites of all these projects. So the sea level is rising, and it's accelerating, in fact. So this comes from the work that we started in 2009 in the Climate Change Initiative, and was prolonged in a more operational manner in the Copernicus framework. And so sea level is rising, and the acceleration is mostly due to ice mass loss to Greenland, Antarctica. But ocean warming is an important contributor. And so the excess heat in the climate system essentially is absorbed by the ocean. And this is why we are interested in looking at ocean warming, ocean heat content, and in sea level rise together. And then we launched another activity called Global Sea Level Budget Closure. And you can see in red, it's a sum of all the contribution to sea level, including thermal expansion and mass change and so on, and even the land exchange, water exchange between the continents. But the black line is the altimetry measuring sea level. So you can see that there is a closure until 2017. Then things went a little bit different and have to be studied. And so this is done thanks to altimetry, Argo, and variable gravity mission, Grace follow-on, and so on. And so the global sea level budget closure, this is the work done later by Anne Barnoum. Clearly shows that, well, we have to see about the closure. There were a lot of things that had to be done since 2017, and Anne Barnoum corrected a few things going on with the altimetry. And here we see that 40% is thermal expansion, and the other 60% is mass transport. And also the regional sea level is affected. By the non-uniform ocean heat storage. And this is very interesting to look at the ocean heat content and the sea level together. The Mohican project, one word, but then you can talk to the Magellan people for more details. There was a paper published monitoring ocean heat content from space altimetry and space gravimetry. And here, very quickly, but it's maybe a bit small, but you can see on top what we did with the space data compared to the Argo data. And then after that, we launched this regional initiative, and the project has been presented to all these conferences, and the paper is under preparation. Just one question, which may be one of the seed questions that can be discussed. You know, do we have enough Argo floats everywhere in the world? It's something that might be discussed. And do we need also contributions from different origins that could be enhanced? Now, a few words on what we do to support the community. We've developed the Altimetry Virtual Lab. You can go there and process data with the new generation of altimeters, the one that are synthetic aperture. We have more than 120 users, 500 CPU years were funded, and came out more than 30 publications and 3 PhD theses. And we gather the community, like the Coastal Altimetry Workshop, and that has a long history, 15-year anniversary of these gathering. We're gathering the hydrology community over and over again since 2003, and Gaznav launched this thing in Toulouse, and we continued. And this is, I guess, important for oceanographers, for the freshwater flux to the ocean. And every 5 years, we like to see what progress, so the 15 years of progress in radar altimetry, 20 years, 25 years. That gave rise to a nice publication with 360 plus co-authors. And this publication is interesting because I took an extract, and it's really nice to read it again and again. Every year you should read it again because there's a lot of information in there. It's now possible with satellite altimetry data to study the Earth energy budget and analyze the Earth's energy cycle at annual and longer time scale. Papers by Messignac, Lécuyer, and they just happened to be in the room this morning. And we are organizing the 30 years of progress in altimetry in October 2024, somewhere in Southern Europe between Lisbon between Lisbon and Athens, maybe southern France. Or Spain, we'll see. And we also launched the Living Planet Fellowship. That's recurrent, and we're going to launch a new call And it's very important for us to have the postdocs here because they teach us a lot while we have our head in handlebars. They come up with interesting, and we do training. We spent a lot of money on training, and there's a lot of training activities done also with THEOS and the space agencies that are partnering with THEOS. And we cover different topics, including the ocean with MOOCs. And we have this support lab to do this activity and provide all the infrastructure necessary. And so. And we have made this new Earth System Science Hub. And it's a new facility where the postdocs are all together. There are different hubs in the hub. And one for atmosphere, one for ocean, one for land, one for cryosphere. And visiting scientists are welcome. So if you want to spend a week, a month, or a year with us, just talk to me about it. I would like to conclude by citing two of my very influential people. First, Carl Wunsch. That said, you know, after 6 years of having the TOPEX mission, TOPEX Poseidon altimetry mission, he said that we can see that the ocean is undergoing rapid and continuous changes day by day. This is a striking contrast to the pre-TOPEX era. And that the ocean changed, we thought the ocean changed only very slowly and on a larger spatial scale. We hope for the ability to continue these projects, meaning these space missions and all the activity done with the data. Without them, we go back to being blind. So that was published in 1998 with Walter Munk. And I'd like to pay a tribute also to one of the pioneers and the person who influenced me very much when I was doing my thesis, Michel Lefebvre. And he says, ocean yourself. And planet Earth is your vessel, not your dwelling. Thank you very much for your attention. And now we will have a little briefing on the logistics. And it's me again. After, welcome to ESA. So basically, we have to do this. And so it's a bit like when you board the airplane. So you have to take your earphones out, you have to look. And here you go.
Welcome to ESRIN. In the unlikely event of an emergency, any kind of emergency, you can report it to the security team from any internal phone by dialing 3333. From an external phone or a mobile, please dial +39 069 418 0333. Emergency numbers and a site map can be found on the leaflet you were issued along with your security badge. Ignoring it is at your own peril. In case the building needs to be evacuated due to fire or any other kind of emergency, please follow your ESA host to the nearest exit. If you lose your way, follow the exit signs. To leave the building, do not use the lifts, only use the stairs. During the evacuation, refer to ESRIN security guards and local area coordinators for advice. Once outside, move towards one of the 4 external meeting points on site. Do not return to any of the buildings until the all clear is given.
Okay, so you got it. We don't have the version for the people online yet, but we're working on it. So the program is available at the desk. You got your copy. Of course, it was printed and there are many changes, and bear with us. We'll probably put an updated program online this evening, we'll see. The first change is that we're going to invert Norman and Tristan's talk because it makes sense. And and so yeah, coffee break. So coffee break is going to take place in the room over there, the James Cook room. Again, we didn't plan anything for people online. Sorry. Lunch breaks will be served downstairs. So you go down the stairs. There's a cash machine over there. Also, there's a bank. And the icebreaker will be offered today, starting 18:30. Canteen, ground floor. The workshop dinner, a very important part. That's where all the international collaboration project starts. And so there will be a bus to take you there. We'll leave at 15 minutes after the poster session tomorrow. And this bus will also leave at 10 o'clock to let people who have to take the train, the last train, back to Rome. And the good news, which was recent because it just arrived last week, is that the workshop dinner is sponsored by the French Space Agency, and thanks to Benoit for organizing this this sponsorship. And thanks. Ah, yes, CNES and CNRS is of course involved in getting this organized. So, so good, and it's very nice to be invited. For us in the organization, it's very painful to collect bills and count them and pay them. So it's all taken care of by the French Space Agency and the French Research National Research Center. You know, there are buses that takes you up and down to Frascati. So there you go. You have it in the welcome letter. And 8:15, I guess, if you're here, you didn't miss it. And tonight, it will leave after the cocktail at 8 o'clock. So if you miss the bus, you walk up. It's 25 minutes walk. But it might be raining, they said in the forecast. A Wi-Fi service, so you got the credentials. So we'd like the oral presenters to strictly respect their allocated time. It's important, and leave time for questions, or not. You can use all your time to avoid the questions, and bring your presentation to the laptop before, of course, at the break before, or the evening. We would like all the poster presentation to be sent to us for different reasons, about making a publication of what we have, like putting PDFs online, if you agree, but also it will help us write the report. For participant online, you know, the usual thing, keep the microphone of your laptop turned off all the time, except when you're invited to present or to make a comment or ask a question. And but would be nice to turn on your camera if we can see you at the same time speak. Okay, and also for the people online, make sure you have sent a backup copy of your presentation to events.organization@esa.int, just in case something goes wrong. We'll show it from here. You can reserve a taxi. You ask the reception desks. There's an ATM downstairs. There's a space shop also downstairs. It's open during the lunch breaks. And this is something I wrote last night without asking my co-organizer, but we want to publish something, and that's what we are interested in at ESA. We would like to publish a report or eventually a white paper, a review paper. And so it would be nice that all the presenters send us, you'll get this by email soon, but send us a small summary of the presentation, you know, with motivation, the stuff that you use in terms of data models and so on, the algorithms you use, and the results, the outlook for future research. And that's the good part. I mean, future research requirement and recommendation, especially requirements and recommendations that are sent to funding agencies or European Commission or space agencies, and so on. And it would be nice to have it like before the 26th of May, so we can publish the report as soon as possible. And you can send it to me, and I didn't put Benoit's email here because he might complain that it will be saturated, but you can send it to me and to events, and we'll put it together. But it's important that out of this meeting comes a summary and recommendations from this community. And also because we want to give ourselves good conscience, we planted 100 trees, cacao, chico, zapot, avocado, which I like very much, and defrosia and coffee in 5 different countries in these 5 locations. And if you want your personal tree, you can ask the reception desk and they'll tell you which one is your tree out of those 100 trees. Have a fruitful workshop. Thank you very much for your patience. And now I would like to introduce Benoît Messignac, who is going to give us an introductory science talk. And you're
Ok, merci Jérôme.
Ah, c'est un PDF? Ouais. Ah oui, mais il n'est pas partagé. What is this? It's not on screen, is it? We have to stop. We have to share. So we have to say PDF. Where is PDF? PDF.
You closed it, maybe.
Let's share the screen now. Huh? Okay, then we do Control L. Thank you. Can you see it online? What is this? I mean,
Just close it there, I think. Oh yeah.
no,
Great.
no, this is.
Oh. You can't read PDF.
Wonderful, thank you.
Try it
On
there,
this.
maybe. You need to sign in to see a PDF.
Very interesting. I'll let you work this out, Lorenza. Et tu n'as pas le...
Si, mais je suis pas sûr qu'elle passe. Mais je l'ai sur mon ordinateur.
Huh? Lorenza is victimizing herself by giving...
We tried, but
Oh no. This is security for you. We're protected. And sometimes maybe I should put my password. Tu l'as le PowerPoint? You want me to log in, Lorenza? No, you do it? Why does... We're inside the firewall here. Why do you need to type your password? It works?
what you did, Control L, huh?
Control L for... This application collects data. Okay, can you see it online?
Yes, we can.
Thank
Wonderful.
you. Go ahead.
Oh, well then. Okay, thank you. Okay, thank you. Thank you, Jérôme, for this introductory talk. And thank you for reminding the deep involvement of ESA in satellite altimetry. How many satellites do we have up there now? I think about 13, and ESA is involved in each of them. I think you just forgot a point is that ESA is also involved now in variable gravity measurement from space, because ESA is preparing the next generation gravity mission with NASA, which is MAGIC, which is a combined double pair with NASA and DLR.
Yeah, too many slides.
Yeah, so in the future, I expect ESA to be more and more involved in gravimetry combined with satellite altimetry to get the ocean heat uptake and the Earth energy imbalance. So it's really, I think, a pathway that ESA is taking, and it's very good news. And thank you for hosting us, by the way. Okay, so welcome you all to the World Climate Research Program Earth Energy Imbalance Assessment. I'm very happy that so many of you could make it to Rome, and I'm also happy to see so many people online. I propose to start the workshop and give you a quick overview of what is this Earth Energy Imbalance Assessment, because some of you may have lost a few details about this initiative in the way to Rome. So what is this Earth Energy Imbalance Assessment? So it's an initiative of the World Climate Research Program that is held under the umbrella of GWEX, and it is led by Maya Kuba, Tim Boyer, Seji Katos, and myself. The objective of the assessment is to assess the different observational estimates of the Earth energy imbalance, and with a special focus on its mean, trend, and variability. The approach is to design an intercomparison of Earth energy imbalance estimates, and the result we expect is to derive a common, robust, and comprehensive estimate of the Earth energy imbalance and of the Earth energy imbalance uncertainty. And this aspect is very important. We will probably have some spread across the different Earth energy imbalance estimates, either across different techniques or even within the same technique. But what we want to do is to understand the causes for this spread. Why do we have this spread, and can we explain it? We want to find systematic errors in different estimates, and we want to find to which extent it depends on assumptions, models, or combined observations, and potentially to correct these errors by looking at the best assumptions or models, or by having a critical view on the combined observations we're using. We want also to understand the spread across the different uncertainty estimates. Many times we have different estimates of the uncertainty because we use different methods and different formula. One nice output of this assessment would be to have a list of best practices to compute uncertainties, to get uncertainties be comparable with each other, because we want them to be more consistent, with the long-term goal to get like reliable uncertainty on which we can use then to test theories, to validate models. So it's really about Earth energy imbalance variability, Earth energy imbalance trend and mean, and it's really about its uncertainty and to which extent we can provide some reliable range for this uncertainty. So the first question that may come to mind is, why do we want to look at the Earth energy imbalance, and why the World Climate Research Program is doing such an effort for the Earth energy imbalance? Well, there are many reasons for that, and you will see that in the first session today, this morning and this afternoon. If I had to summarize the reasons, I would say there are two main reasons why we want to have a reliable and accurate estimate of the Earth energy imbalance. The first one is to better understand climate change. It is because when you measure Earth energy imbalance, it enables to constrain the global energy budget, to quantify the radiative response of the Earth, and that enables you to evaluate the amplitude of climate change in response to greenhouse gases emissions. And I think the first two scientists to show that Earth energy imbalance was actually a vital variable to evaluate the radiative response of the Earth and constrain the global energy budget were probably Lindzen and Hansen in the 90s. At that time, Lindzen and Hansen were trying to reproduce the global mean surface temperature record, the historical record, with their general circulation model. And they found that with different configurations, they could fit this historical global surface temperature record, the historical record. And they had different configuration where they had a different global climate feedback parameter in their model, and different ocean heat uptake efficiency. And that was an issue at the time, because it means that with just the global mean surface temperature record, you cannot constrain the global energy budget, and you cannot constrain the general circulation model, the GCMs. And it's readily visible if you look at this equation of the global energy budget. So it's something which is quite fundamental. So in this energy of the global energy budget, you have the radiative forcing here, the radiative response of the Earth here, which is linear with surface temperature, and you have the heat uptake here with the heat uptake in the mixed layer and the heat uptake in the deep ocean. And what they showed actually that with this just one equation, you have two largely unknowns in the climate system, which is the ocean heat uptake efficiency and the global climate feedback parameter. So you cannot solve this equation and get those two unknowns from one equation. And what they proposed, and Hansen was really instrumental in this, is to break this equation into two equations by getting observations of the Earth energy imbalance. Because if you get observation of the Earth energy imbalance, then the global energy budget, you can break it in two parts. An atmospheric part, which depends on atmosphere and surface, and an ocean part. And then if you have observations of the Earth energy imbalance and the global mean surface temperature, then you can constrain the global climate feedback parameter if you're looking at the surface and the atmosphere. And now if you're looking at the ocean, you can expect to constrain the ocean heat uptake efficiency. And so the estimate is unambiguous, and you can expect to have some constraint. And that is the reason why Hansen was so hard to push behind Argo and to get the Argo program on track, because he wanted this Earth energy imbalance estimate. And today we have different ways to measure Earth energy imbalance. We have top of the atmosphere radiation budget, we have Argo, we have satellite altimetry minus GRACE and others. And I think it's our work to take over this legacy and to go at the end of the problem and provide accurate and reliable estimate of the Earth energy imbalance with uncertainty to be able to provide some constraint on this global climate feedback parameter and on the ocean heat uptake efficiency also, of course. Now, today, there is also another aspect which is very important for Earth energy imbalance. It's not only about understanding climate change, it's also about monitoring climate change and helping society to monitor climate change, to tackle climate change. If you look at if we want to monitor the response of the physical climate system to the ongoing and future greenhouse gases mitigation policies, we need to find the variables that tells you how the physical system is answering. And you need to find the primary variable and the one that will answer the most accurately and the earliest possible. And this variable is arguably the Earth energy imbalance. I'm showing here a plot on the right-hand side where you have the global mean surface temperature on the upper panel and the Earth energy imbalance on the bottom panel. And I'm showing two different projections from the IPCC. One projection in blue, which is a projection that follows the COP21 agreement and a temperature that stays below 2 degrees in 2100, and the red curve, which shows the projections in a business as usual. Well, not exactly business as usual, because now you know that SSP 8.5 is not exactly business as usual, but almost business as usual scenario. And the different scenarios are starting in 2018. And one thing which is very interesting is that you see for two different scenarios here, starting in 2018, you see that you can make the difference between a business as usual scenario and a COP21 scenario at the 68% confidence level with global mean surface temperature only in 2040. That is 22 years after starting to mitigate greenhouse gases emissions. But if you look at the Earth energy imbalance, you can make the difference in around 2018. That is 10 years after. And so it tells you that monitoring the Earth energy imbalance is very important just to provide this feedback on society to tell people how the physical system is responding to our greenhouse gases mitigation policies. And that's another aspect which is growing and which is more and more important now. It's further from science, but it's monitoring and it's also important. So that's basically the two reasons why there is this focus on the Earth energy imbalance from the World Climate Research Program. Now, we're not the first to look at this question of the Earth energy imbalance and the global energy budget in general. We have a long legacy, and actually we are standing on the shoulders of giants. GWEX, and especially the GDAP working group, has been working on the global energy budget for many years, for more than 30 years now. As an example, I'm showing you here the global energy budget that was proposed by Graham Stephens in 2012, and the update that he's proposing at this year in 2023. And you see that this group, GDAP from GWEX, has been working on estimating the different fluxes of the global energy budget for many years, and they have tried to estimate all the terms of this global energy budget, and also the Earth energy imbalance, which is very important, as Tristan will recall, to constrain this global energy budget. So the effort of this Earth energy imbalance assessment is really playing a role for this GDAP group, and our work is really a part of this general effort to try to estimate the global energy budget that is done in GWEX for more than 30 years. Then there was other initiatives as well. There was a climate concept heat research FROCI that was proposed by Kevin Trenbers and Karina van Schuckman in 2015, where they proposed an inventory of the reservoir of heat in the climate system. And there was also the workshop in 2018, the Earth energy imbalance and its implications in Toulouse, that was proposed by Rémi Roca, Tristan Lécuyer, Karina van Schuckman, and myself. And that's where it appeared this really need to get an assessment of the Earth energy imbalance viability with the different techniques, and to get a firm grip on what is the uncertainty we have on this Earth energy imbalance. Because we saw this very large community working with estimate of the Earth energy imbalance, using it to constrain theories, using it to validate models, but with a fuzzy uncertainty. And so people were getting to some conclusions that was really arguable, because given the level of uncertainty, sometimes you couldn't say whether we could conclude or not. And so the idea of this GWEX assessment is to make a special focus on the global and regional ocean heat content and ocean heating rate, because it's a very important way to derive Earth energy imbalance, but also on the top of the atmosphere radiation budget, and bring them together to get a robust documented estimate of the Earth energy imbalance, mean, trend, and variability with reliable uncertainty. Okay, so what is the status now of this GWEX EI assessment? So I'm taking too long, so let's go a little bit quicker. So we started in 2021 with data producers. The idea was to make data producers provide data, to make this data available on a website that you can go and visit, so the community can take this data and start the analysis for the Earth energy imbalance assessment. So we considered the community from geodesy, altimetry and GRACE, in-situ data, reanalysis, and top of the atmosphere radiation budget, and also surface radiation budget. We collected the data, now the data is available, and we're starting today to propose to the community all these data sets so you can download and start the analysis. Now we want to understand why we have different estimates and what is the uncertainty we have around this Earth energy imbalance. In 3 to 5 years from now, we will have to write a GWEX assessment report, and we will provide all these conclusions. So the workshop today, what are the outcomes we expect from this workshop? So we expect to start the work from the community. We want to have a status of the current Earth energy imbalance estimates and the Earth energy imbalance uncertainty estimates. We want to identify discrepancies across different Earth energy imbalance estimates. Within estimates from one techniques, but also across estimates of different techniques. And we want to define the milestones needed to get a consistent estimate of the Earth energy imbalance and the Earth energy imbalance uncertainty within the different techniques and across techniques. And we will write a community white paper with recommendations to follow, such that our community will be in the good track to respond to the Earth energy imbalance in 3 years to the GWEX, for the GWEX assessment report. Okay, so that's the objective. So just a few comments about the sessions. Sessions will be in plenary, all of them. They are followed by discussions that will be seeded by the chairs. So chairs will have prepared some seed questions to start the discussions, and they will report at the end of the workshop in a short summary about the different presentations and about the discussions. And that will feed into the white paper. We expect also from different presenters to provide us a very small summary of their presentations that will help chair people. Thank you. So if you have any questions.
Oops, any comments, any questions? A strong desire to move on to the scientific session number 1. And so Seiji, Maria, and Norman, please come up and share this first session.
For us to sit here while we're
Okay. No, sorry. I need to show it.
So the first speaker is Tristan Lécuyer, head of GWEX GDEP.
There was this one, right? Yeah.
Yeah.
Okay, thank you, Benoit and Jérôme, for hosting us and for inviting me to give, I guess, one of the earlier science talks here in the workshop. So yeah, I've been involved in this problem of, let's say, closing the global energy budget now for probably about 2 decades. And so a lot of, I think, the activity centered on the Earth's energy imbalance also sort of evolved around some, let's just say, discrepancies in some of the reconstructions in the first part of the 21st century of how well we understand the flows of energy through the system. And so what I want to present today is actually less about EEI measurements themselves and more on the subject of sort of this really critical role that EEI plays in establishing an objective closure of the, oh, there we go, let's see, sorry, of the global energy budget and the flows of energy through the system. Benoit asked on the bus today if I could say a few words about GWEX. Unfortunately, I already had a few slides in my presentation on that. So before I get to my actual science presentation itself, I do just want to talk a little bit about the GWEX program and specifically where the EEI assessment fits within it. So this is just a one-sentence description of what GWEX does, for those of you who are not as familiar with it. GWEX stands for the Global Energy and Water Exchanges Project. It's under the World Climate Research Program, WCRP. And it's dedicated to understanding Earth's water cycle and energy fluxes at and below the surface and in the atmosphere. So that should sound, somewhat familiar. Obviously, EEI plays a fairly big role in understanding that the energy, total energy in the system at the surface and below the surface. GWEX is comprised of 4 panels. The relevant panel, as Benoit has already mentioned, is the GWEX Data and Analysis panel. So it's the sort of 4th one there on the far right, which guides the production and evaluation of long-term global atmospheric surface water and energy budget products. And so there's some key words in there, global, long-term, and energy that are all relevant here to the EEI problem. A little bit more detail on specifically what GDAP does. So I've co-chaired GDAP now for about 5 years. My new co-chair this year is Hiro Masunaga from Japan, but Rei Miroka, who is also intimately involved in the EEI problem, was my co-chair for the last 4 years before that. These are basically our three sort of, I guess, overall governing questions that we're trying to address with GDAP. And I've highlighted some of the key words again in color here. So GDAP coordinates global scale observations of the fluxes that make up Earth's energy and water cycles. And really the main overarching goal is to understand how sensitive the Earth's climate is to changes in radiative and other forcings. And so again, as Benoit pointed out very nicely actually, EEI is sort of central in understanding that Earth's climate sensitivity. GDAP seeks consistent reconstructions of the water and energy budgets. What we mean by consistency, and I'll show it on the last slide here, the next one, which shows our vision, is most data sets from all of these great satellite sensors that we have flying around the Earth are derived independent of one another. And so when you put them back together again and try to create a consistent picture of the global energy and water cycle, you find that there are imbalances, large ones, in fact, due to some of the structural uncertainties in the various products themselves. And so what we're seeking now, and this is something that's fairly new for GDAP, actually, Benoit mentioned there was 30 years of history, but really it's only the last 5 years that we've really been focused on this consistency problem. And I'll show that really one key aspect of this consistency is having a good EEI constraint. And then, as Benoit pointed out also, GDAP coordinates the assessment of various products. And so the key to being here, this is the EEI-A. It's the assessment of Earth's energy imbalance products. And the goal there is really to try to understand what the uncertainties are and, as Benoit pointed out, develop a consistent approach for assessing the uncertainty in those products. So here is the GDAP vision. This sort of pulls together a lot of the components that I know we're going to talk about in the next 3 days. Basically using all of the available satellite observations, this wonderful constellation that we've had now for a few decades of products that are measuring various elements of Earth's climate system, but putting it together in a consistent way for enabling the study of the climate. And again, so that if you look at some of the words there at the top of in the vision, that it's observation-centric, climate-oriented, consistency-driven again, global and research focused. And we want to be able to provide information for the research community, which I'm sure everybody in this room also wants to do. You want people using the EEI as opposed to just deriving it for the sake of deriving it. And Benoit already showed this diagram from Stevens et al., this BAMS paper that talks about the 30 years of GWEX. Basically, this is the updated version from the GWEX integrated product that brings together all of these different flux products from different sensors of the Earth's energy budget, all of the various fluxes, and you see the central player right at the very top there is the EEI estimate that everything has been constrained to. Benoit actually did the constraining of this diagram. So if you take all the products independently, as I'll point out here in the next few slides, they do not give you Earth's energy imbalance. They give you an imbalance of about 15 watts per square meter, but with the constraint of the various sources of Earth's energy imbalance information, we're able to create a consistent picture of what Earth's energy budget looks like. Okay, so that's GWEX. That's maybe sort of the motivation for this assessment activity. I'm going to now step back and talk about a little bit of additional context, I guess, for why or how we're using EEI to constrain the various flows of energy through the system. And to do that, I'm going to talk a little bit about my project with Seiji and a few others, actually a lot of others, called the NASA Energy and Water Cycle Study. There's a couple of different projects underneath that news program that I'm going to talk about. I'll start by talking about a slightly older project, about 10 years old now, called the News Climatology Project. Here we were actually trying to answer the question, when you pull together all of the various fluxes of energy in the system, how well do they actually balance? And try to identify which of the observations could be targeted to actually improve the balance. So which ones do we think have the largest biases that need to be reduced? And I'll talk about the methods in a second there. But basically what we did, we had about 25 people or so with expertise in all of the various fluxes of energy through the system, from precipitation to evaporation to radiation, latent heat, sensible heat. And so we pulled together this big potpourri of data sets, but also with the associated knowledge of how accurately we feel each one of these various fluxes can be measured or inferred from these observations, in order to try to put together the best estimate we could at the time of global energy budget. And so here's another global energy budget diagram. This is one of the ones that we published in a paper in 2015 that shows, without any constraint at all, what the global energy budget looks like. And I'll just highlight the number that's, so you can see all the flows of energy there. All the numbers in black are the ones that we put together from this news project. You see that when you add up all of the numbers, you get a net absorption at the surface of 16 watts per square meter. And anybody in the room who studies EEI should know that 16 watts per square meter is considerably more than the actual true EEI of the planet. In fact, it's orders of magnitude too large. And so we, and I guess I'll point out, there's a bunch of other numbers on this diagram. There are 3 other papers that came out maybe shortly before we did this study. Kevin had, Tremberth had a paper, Graham Stevens had a paper that I was co-author on, and Martin Field had a paper. You see that all 3 of those different reconstructions give some different numbers of the fluxes. I will point out that the energy imbalances in the other 3 sources here are all more realistic, the types of numbers that you're used to seeing from EEI. But I will point out that all of them involved some ad hoc corrections in order to get to that energy imbalance. So that wasn't an objectively determined imbalance, and you can tell that from going to some of the individual fluxes where you see differences of 8 to 10 watts per square meter in some of the fluxes, particularly the evaporative flux and the downwelling long-wave radiation. And so what we were trying to do then with news, this is the regional perspective, just so you can see where those imbalances actually occur. A lot of it happened to be over the ocean, where we a lot of the evaporation products are not tuned to agree with radiation. And so you see this is the global distribution of that 16 watt per square meter or 15.86 watt per square meter imbalance. And you can combine a variety of different data sets and you end up with an imbalance that looks similar to this. I think the imbalances are, depending on what combinations of data sets you use, range from about 13 to 27 watts per square meter. So what we did as part of the project then was say, okay, well, we understand that there's uncertainties in all of these products. We actually had expertise on all of the different products on the team. We wanted to then ask, is it possible to adjust the fluxes to reintroduce the closure information? We know that there ought to be closure of the energy budget to within the EEI, and water cycle should close to 0, on a global basis, unless we're fluxing water up into space. Can we actually close the energy and water cycles objectively within the uncertainties in the observational data sets themselves? And so to do that, we applied a variational approach, just a simple sort of 1D VAR approach, where we applied all of the budget equations that we knew on continental scales and annual scales, and basically adjusted the fluxes within their uncertainties to try to achieve balance to within some storage estimate of the storage term. So in the case of energy budget, like I said, that storage was the global EEI. For the case of water cycle, we had a 0 net global water change, and we also had estimates of the runoff on continental scales so that we could actually, and we had storage. We had GRACE that was measuring the water storage, terrestrial water storage. And so we had a series of equations, all linear, and we had this variational approach where we could actually optimize this and try to see if we could create a balanced data set. And what we found, these are the results from these 2 papers. If you want to look at them in more detail, I'll point you to those 2 Journal of Climate papers in 2015 that discuss the energy budget and water cycle separately. But what we see is that by applying this 1D VAR variational approach, using realistic estimates of the uncertainties for all the fluxes, we're actually able to balance the energy budget and water cycle to, like I said, by making adjustments that are not larger than the uncertainties in the various products. So what we've done is we've gone from the purple numbers, which are the unadjusted numbers, to the blue numbers in these diagrams, which are the ones that are after the 1D VAR approach. However, what you see is that the adjustments that you make aren't random. There are definitely evidence of some biases in the products, because in order to create the balance, you actually have to increase both precipitation and evaporation in order to offset an excess of radiation into the surface. And if you think about it, if you just looked at the water cycle independently, in order to create balance in the water cycle, you ought to see P and E going in opposite directions. If there was an imbalance, you would want to maybe decrease P and increase evaporation to get them to equate to one another. The fact that you have to put them both up and increase them both in the same direction to match the downwelling long-wave radiation suggests that there's an imbalance. There's biases in some of these products. It's not to say which one, but it says there's biases. Okay, so where are we today? I just wanted to basically say we've advanced considerably since then. We now have a much more complex set of equations, and I wanted to basically show all of the various fluxes here that we're now looking at in this new News, Energy, and Water Transports and Exchanges program, or NEWTEX. This is a slide courtesy of Brent Roberts. I'm obviously not going to go through this in detail, but I just want to point out this is a very complex problem. And the reason I want to point this out is because still critical to this is this overall constraint that we need to know what the total EEI is in the system. And so I'm going to show, I'll skip by this because I'm running a little bit short on time. Basically, what we're doing now is using that complete suite of equations, which included storage and vegetation and the cryosphere and the ocean and flux convergence in the ocean and the atmosphere. We're now applying the same variational approaches or similar variational approaches now with bias corrections and a few other bells and whistles that are nice to have. But we are again seeking whether or not we can use the Earth's energy imbalance constraint to actually adjust all of these different flows of energy and water through the climate system and improve our global estimates and actually regional on continental scale estimates of these fluxes. So this shows some preliminary results from that. We're getting to the point where we're ready to sort of release some data for people to look at. This is now covering the period from 2003 to 2009, and I'm just going to show a few quick examples of this. Bill Olson at Goddard is the person doing a lot of this work. What you're looking at here is our new sort of continental and ocean basin scales. This is the net radiation sensible and latent heating going into the surface. This is the horizontal flux convergence coming from reanalyses. And what I wanted to point out again is still, 10 years after the first new study, if you estimate the storage as a residual from these two terms, you still get in a lot of basins tens or 20s of watts per square meter. Whereas if you compare that to, oops, and I think, I went too far. There we go. Sorry. You get 20 watts per square meter. If you compare that to an estimate of storage, we're just using the GLORIES data set right here for that. You see that these estimates are, again, an order of magnitude too large without any optimization. When you apply the optimization, of course, you have to assume some uncertainties, like I said, on various terms. This is the regional version of EEI, the distribution across all of these basins of the heat storage in the ocean. If you assume a 1 watt per square meter uncertainty on that and a 10% uncertainty on the horizontal flux convergence, you can once again achieve balance in the storage. You can get numbers that actually look very similar to what the estimates of storage in these various basins actually are. But this is, yeah, okay, I'm going to wrap up in a second here. What Benoit pointed out and what the whole purpose of this workshop is to really assess the uncertainty, the accuracy to which you know that storage constraint. And I will point out, if instead of assuming a 1 watt per square meter error on the storage, you assume 5 watts per square meter, and that's the only thing that's changed. We're assuming the same uncertainties on all the other fluxes, including the horizontal convergence. You now see that the optimization comes up with a different estimate, obviously, and several of the storages in the different basins are still too large and the constraint hasn't really done its job. And so then how well can you trust the other fluxes if you're not able to really match the estimate of storage? So it's really important not only to know the amount of storage in the different basins and how the magnitude of EEI, but also its uncertainty, and you need to be able to trust its uncertainty. I'll skip over these slides. This is just to show that, we can actually do this on a monthly basis on all these different ocean basins. This shows that we're actually adjusting all of the other fluxes, not just the storage term itself, but all consistent with that storage. So again, this is sort of context that by providing a good EEI estimate, and especially the regional and temporal variation in EEI, we're able to actually estimate these flows of energy and water through the system. So my message is, not to go over time here, EEI is a very powerful constraint on this system, and what it actually is allowing us to do is get better estimates of all of the flows of energy and water through the climate system. This optimization framework provides a really nice framework. We can actually play with a lot of different EEI estimates. We can play with different estimates of the fluxes to try to see how the energy budget and water cycle reconstructions vary. But the key here is we need robust uncertainty estimates on all the fluxes, including the EEI constraint. I just made the point, time evolving and spatially resolved estimates are especially valuable. I know spatially resolved means it's no longer an EEI, it's a distributed energy imbalance, whatever you call it, but we are looking to go down to some sort of spatial resolution. And then a future challenge, and I don't know how much this is going to come up in this audience, but I do think we also need to be thinking about other places that energy goes, such as in vegetation over the course of the annual cycle and into the cryosphere. And I know that was a topic that we briefly touched on maybe at the workshop in Toulouse, or maybe it was before that. But I think we want to keep it in the back of our mind that there are some other reservoirs of energy in the system that are especially important on regional and monthly scales. Okay, that's everything I have.
Thank you, Tristan. Do you have any questions? Quick questions, because we are already running late. Yes, please, Andrea.
Thank you, Tristan, for this presentation. My question is about the spatial resolution that you mentioned. So I guess as long as you increase the number of basins, which I guess are a bit arbitrary, you also increase the degrees of freedom in your reconstruction. So and also the potential impact of the uncertainty of the transport and convergence. Do you think, how did you choose these regions? Do you think is the maximum we can have, or it's possible to increase further?
Yes, I think a goal is to increase further. Interestingly, when we proposed the project, we actually initially proposed to go to a gridded, something like a 5 by 5 degree resolution. That was a target. What we realized in doing this, that when you do add the additional complexity, and as you said, the uncertainties start to grow as you get to smaller scales, transports become really important on smaller scales. We decided that having these continental and ocean basin boundaries, it gives you some nice constraints on the borders, like a runoff and the terrestrial water storage on land. So we decided that this was sort of an optimal, at least for now, an optimal spatial resolution to go to. I think ultimately we still want to push down to a finer scale so that we can resolve some of those, the distribution of where the heat is going into the ocean. But so, like I said, in principle, you can apply any scale, but I think you raise exactly the point that the uncertainties at some point become very large, and whether or not you can actually get closure on a very small scale, I'm not sure. Thank you.
Okay, thank you.
Another quick question? Yeah, I do have one. So are you applying the global Earth energy imbalance constraint, or are you applying an ocean heat content constraint regionally? And in that case, could you tell us what is the uncertainty you would need? What uncertainty did you use if you used the regional ocean heat content, and have you played with the uncertainty? Because I suspect the level of uncertainty will change your solution. So have you played with this and could you provide us with like a threshold of uncertainty which would be sufficient to improve your estimate, for example?
So the answer to the last question is yes, we could, but I don't have the number for you. But no, this is that. So the answer is both. We have the global EEI because we really do trust the uncertainty on that one, and we trust that number. But because we would like to have constraints on this continental scale and on a monthly scale, we're also using these reanalyses to provide the change in ocean heat content on these finer scales. That uncertainty, I think we don't know very well, and so maybe I don't know if that's for phase 2 of the EEI assessment, or if it's something you're already talking about. I guess I'm hoping to learn a little bit. But I think more important than giving you a threshold is really just understanding where you think we are now in terms of a North Atlantic ocean heat content change. If you can give us some sort of an error bar on that, we can use a realistic error bar and see how the other fluxes adjust. So that the important thing is really understanding what the uncertainty is first, and then trying to improve it next is what I would suggest.
Thank you, Tristan. So our next speaker is Norman Loeb from NASA Langley. He will talk about the recent trend in EEI. Can you see the presentation online? I hope so.
Yes, not yet in full mode, but it's coming, I think. Yeah, thanks.
Oh, it's okay.
Okay, thanks for this wonderful workshop in this wonderful place. I'm going to be talking about changes in Earth's energy imbalance from a satellite perspective. Ceres is clouds in the Earth's radiant energy system. We've been collecting data since our first month of data was in March 2000. So now we have 23 years. And the graph here shows the time series of that. The bottom is what I'm calling net, which is essentially Earth's energy imbalance. It's the difference between how much absorption of solar radiation occurs versus how much outgoing long-wave radiation. And so the plot is showing the time series. You could see the internal variability in the system is quite large. At the monthly level, the thin lines are, a lot of noise in the system. If you average 12-month running means, you get these thicker lines. And these shaded areas are the multivariate ENSO index. So the first thing that strikes you when you look at that is the variability. The second thing is that there's looks like there's changes over time that are going on, especially in absorbed solar radiation. The numbers are on the right there. So these are trends in watts per square meter per decade, together with the uncertainty. So ASR trend is 0.73 watts per square meter per decade. OLR, there's been an increase in OLR, which is a cooling, so of minus 0.27. And so the net is about half a watt. So you saw in Graham's slide, which I think is outdated, he had an EEI of 0.5. We're seeing an increase per decade of about 0.5 watts per square meter. So that's pretty darn scary, pretty staggering. So if you look at it from another perspective, if you take the first 10 years of the series record, that was about half a watt in terms of EEI, and these are the various components, solar irradiance, absorbed solar, and outgoing long wave. If you then look at the last 10 years, it's about 1 watt. So Graham should redo his maybe a publication of 2024 and have 1 watt as the EEI. It's actually doubled during this period. And it's primarily because of absorbed solar radiation. Solar irradiance change over this period is very small. So the absorbed solar radiation, about 1 watt, partially offset by increasing outgoing long wave radiation. So that's pretty staggering and quite frankly, pretty scary. We're pretty confident about this. We have series instruments flying on 4 different platforms, launched in different periods and operated in different modes. And they all show very consistent results. So here I took a period of overlap where they were all in cross-track mode and essentially looked at anomalies relative to that climatology. And they're tracking each other really well At the monthly level, they're consistent to a few tenths of a watt per square meter, and there's no evidence of drifts of one relative to the other. If you take the two longest records from Terra in black and Aqua in red, and you look at their trends, first looking on the left at Terra, looking at the trend as a function of record length, so the first 5 years, 7 years, 9 years. The gray here is the 95% confidence in the trend. You could see we emerged from uncertainty after about 12 years, and so here's the half a watt that we're looking at, well outside uncertainty. Now, more importantly, if you look at the difference between Terra and Aqua, so Aqua was launched in 2002, and if you just take the difference in the anomalies between these and then take the trend and the uncertainty in the trend, you could see that they're within the uncertainty down to better than a tenth of a watt per square meter per decade. And so these are two series instruments on two different satellites launched at different times, operate in different ways, and they're really, really consistent. The other really critical comparison that gives us confidence in these trends is a comparison with in situ. So red here again is series. So these are annual anomalies 6 months apart. And we're comparing the blue, which is in situ. So it's essentially primarily Argo. As we heard, most of the energy is coming into the oceans. And so we have the Argo network, but we've also accounted for other heat storage in the system. For example, land component, energy that in the atmosphere, stored in the atmosphere, and energy that's used to melt snow and ice is all included in this. And so the comparison looks pretty good. You don't expect them to be perfect because the sampling isn't perfect, especially for the in situ. So there is some noise. We updated this since we published this paper in 21. We updated the last couple of years, and they're tracking each other really well. But what really impressed me is the difference in the trend over this period. It's 0.08 watts per square meter per decade, consistency between these two. And we do anchor the mean in series to Argo, but not the variability. So the variability is completely independent between these two very independent ways of doing these types of measurements. So we're pretty confident that the results are robust. So now turning to the spatial trends in absorbed solar, outgoing long wave net, and I'm also showing for comparison SST, you can see where the trends are largest, and we're seeing huge trends in the Pacific, especially where you have low clouds, marine stratus clouds. We're also seeing trends in the Atlantic off of North America and other places. The large trends in the tropics seem to cancel when you get to the net. So this is essentially ENSO related. What stays in the net is primarily where you have low clouds. And that's I'll come back to that. Low clouds are really important, and they're one of the big uncertainties in constraining cloud feedback. The other thing that struck me about these plots are the similarity in the patterns, the trend patterns between SST and absorbed solar radiation. Where you have warm SSTs, you tend to have more absorption into the system. And these are coupled. I mean, if you warm the surface, especially low clouds, they don't like to have unstable boundary conditions, and so they tend to burn off, and you get more absorbed solar radiation. More absorbed solar radiation in turn causes more absorption at the surface, which causes warming. So there's a real tight coupling between the two. But I was just struck by the similarity between these, the patterns of SST and absorbed solar radiation, and I'll come back to that as well. These are the zonal means. I'm looking at equal area zonal averages. ASR, just about every latitude band, especially the northern hemisphere subtropics are showing huge trends, and that's not too surprising given the regional plots I just showed. OLR is a bit of a mixed bag. You're getting an increase in OLR, and I'm plotting negative OLR trend here in the northern hemisphere, but really what wins is the absorbed solar radiation pretty much every latitude. You're seeing positive trends in net. So you can do an attribution. The nice thing is that Ceres flies with MODIS, so imager data, from which you can do radio transfer calculations to sort of try and assess what's driving the trends. And so what we did here is a radiative perturbation analysis where you can do, for each grid box each month, you can do a radiative computation where you essentially input the climatology of all of the variables that matter, and then difference that against the climatology of all variables but one to assess the impact of that one variable. So you can see, for example, how water vapor alone impacts outgoing long-wave radiation. What's its contribution to the overall trend? So clouds are really important for the absorbed solar radiation surface, primarily because of melting snow and ice. That's what's giving you this huge trend in ASR. OLR is dominated by an increase in temperature. We're increasing temperature, so you get more OLR as a result. But when you increase temperature, you also increase water vapor, so that you increase the greenhouse effect that offsets that. And so in the net, all of these guys are ganging up on the temperature to give you this overall positive. So you get that contribution from clouds, water vapor. Other here is also is basically well-mixed greenhouse gases. We also included solar irradiance in that term, which is very small, as I showed for this period. So well-mixed greenhouse gases, water vapor, clouds, surface, all really overwhelm the negative outgoing radii, the Planck response to warming. I'm coming back to the sea surface temperature again. So I'm looking at the time series of 12-month running averages from ASR and SST, and I'm just struck by how they track each other over time. I'm also struck by how the trend sort of emerges. It seems sort of flat, and then it just shoots right up, and then it's flat again. It's not just a straight linear trend. So what I decided to do is to take this record and split it in three, and I gave it arbitrary names. I'm calling the first period the hiatus period. You might have heard of the hiatus. Well, so I'm calling this the hiatus period. The transition to El Nino. So over this period, we had a negative multivariate ENSO index, so a really strong La Nina transitioning to a really strong El Nino. And then since then, we've kind of returned back to La Nina conditions, and we've had this so-called triple dip La Nina occur. And I heard on the radio that we're going back into El Nino this coming year, so the fun continues. But I'm doing this just to sort of look at the variability within that period, because we tend to look at trends, but there's a lot of stuff going on within that period, not just along the linear trend. So here's the trends for these period, the hiatus, and you can see how the transition period had a huge trend in MEI, and then it was negative. These are the corresponding SST trends, and you can see this is where that warming happened, and the trend just was crazy. It was like half a degree Kelvin per decade over this transition period. This is the hiatus. We continued to rise, but it wasn't spectacular. It was less of a rise than the previous decades, which is why they called it the hiatus. But this period, boy, they really huge trend in this transition period. And then basically no trend in this post-El Nino period, which in itself is kind of interesting because we went back to La Nina conditions for 3 years in a row, yet we still have really warm, we didn't have a negative trend. So there's other things going on. There's also forcing in the system that's playing. So it's really complicated because we have this continuous forcing and we have internal variability, and unscrambling that is not trivial and not really doable from observations alone. So here's the TOA fluxes for those 3 periods, and I'm putting the solar as well as a component because when you start to split things into shorter periods, you do worry about the rise and fall of the solar cycle, and you could see trends in solar irradiance over short periods actually do matter. Shortwave, alone. And then the sum of these two is ASR, outgoing long wave, and net. And what I want to point out here is you have huge fluctuations from these three periods in absorbed solar radiation and outgoing long wave radiation. But look at the net. Oh. There you go. Okay. The net is amazing. So it's basically for these woefully really big differences in meteorology between these periods, the net is robust. It's within 1/10 of a watt per square meter across these three periods. Whereas OLR and ASR are varying more than 1 watt, which is really was fascinating. When I looked at that, I don't know if that's a fluke just for this particular time period or if it really is a robust part of the system. What it implies is that the rate of planetary heat uptake is relatively insensitive to internal variability when you average over these types of timescales. Surely if you're looking at monthly, that's not the case, but if you take averages like I did here over 5 or 6 years to break up the series period, it's really amazing that the net is just really constant. The trend in the net is constant. So you could think about this in a forcing feedback framework where the net is the sort of the net forcing on the system, and it's showing that it's robust across really different periods, internal variability. So that's a curiosity, and I don't know the answer to that. We can also look from the data at the contributions of different cloud types. So these are the contributions to the overall trend for ASR from low cloud, middle clouds, high clouds, polar clouds. And I won't go into too much details about how I did the cloud typing, just for the interest of time. But the basic message here is it's really low clouds that are responsible for the decreases in the northern hemisphere, as well as middle clouds are important, but low clouds especially. And then in the southern hemisphere, we're also seeing large trends. So the trends are a little bit larger in the northern hemisphere than the southern hemisphere, but not by much. And so the middle clouds are really quite important for the southern hemisphere. We're also looking at this by different cloud types for the low-level clouds, cumulus, stratocumulus to cumulus transition, stratocumulus. And really stratocumulus is quite important in the subtropics and cumulus in the tropics. So I'm going to have to go a little bit faster here because I've got 2 minutes left. And there we go. So how do we trust these trends that we're seeing from MODIS to basically enable us to do the attribution and absorb solar radiation? Well, we can compare with Calypso CloudSat, which we did here, northern hemisphere, southern hemisphere, and it's pretty encouraging. For the low cloud types that I'm showing here, we're getting very consistent results in terms of the trends for this period. This is 2007 to 2017. We're also seeing consistency for high clouds. We're seeing increases in high clouds from MODIS as well as CloudSat Calypso, but we disagree in the northern hemisphere. And that may be just because of the different types of high clouds we encounter there and how, you know, these the detectability ability for CloudSat Calypso. But overall, it's really quite staggering how similar they are. So given the connection between SST, clouds, and TOA radiation, you then ask the question, okay, what's driving the variability in SST? And so I'm doing, you know, is it the atmosphere from above or is it the ocean from below? So you can sort of address that by looking at the mixed layer. So do a mixed layer heat budget. And what we did here is we used series at the top of atmosphere. And then Michael Mayer, who's here, provides a nice data set of the divergence of lateral atmospheric energy transports and vertical integrated atmospheric energy tendency. So that gives you that. So the difference between these two gives you the surface flux. You can, if you assume the SST is representative of the temperature in the mixed layer and you have ocean mixed layer depth, you could then calculate the ocean mixed layer heat content tendency. And then as a residual, you can get the the ocean component from below, vertical mixing, if you're looking globally. And when you do that, oh, there we go. And again, I split the period up into 3. You can see that the ocean wins. The ocean is providing the heating that caused this huge increase in SST over this period. The atmosphere contribution is really quite small. But you can also look at the, hello? Okay. You can also look at the regional distribution of these fluxes and see where the heating is coming from in different locations, and especially in the Pacific where we saw these large fluxes. And we can also look at the SST patterns, which I think are very important for clouds. And we saw some really distinct patterns for these 3 periods where we had cooling, which tends to favor more cloud cover during the hiatus. And then this reversal, which is very similar to a PDO pattern, but the PDO index flipped back to negative. And now we're looking at continued warming in the North Pacific, but cooling in the southern part here. And so the clouds pattern are basically responding to that. So I think to understand at least the absorbed solar radiation part, understanding SST, what drives SST variability is really critical, and then understanding how the clouds respond to that. But I think the net, the imbalance that we're talking about, is a different animal because of the compensation between long wave and short wave. And so that constant trend that I showed is really a puzzle. So part of the puzzle might be solved if we get climate models to produce output beyond 2014. So CMIP6 that everybody uses stops in 2014, but there's a lot of action that happened after 2014, including the trends in SST, the El Nino 2015-16 marine heat waves, not to mention the pandemic. But we don't get to really look at that with the CMIP6 protocol. Many of the inputs have also changed. The forcings have changed over time. Improvements have been seen in the forcings that are used, and SSTs actually have been updated. So why hasn't there been a coordinated effort from the climate modeling community to update their AMIP simulations? So the AMIP simulations are atmosphere-only simulations, and they're the most relevant for comparing with observations. We have this beautiful set of observations from Ceres, CloudSat, Calypso, yet we can't compare them with models because the models haven't updated their model simulations. So Gavin Schmidt is now leading a new effort to do something about that. He calls it Ceres MIP, and the idea is to use updated forcing, updated SSTs to produce these atmosphere-only simulations with everything updated, go through 2021, and basically have a tool to now unscramble the egg, to try and better understand some of the observational results I showed, because you can only really do that. You can only sort of tease apart all of the different processes in a model. And first you have to trust the model. Are the models going to get what we observe? And if they don't, why? And so there's so many things we can address if we have a model component in addition to the observations. So there's a fall AGU session on this, and I think we include observations in that. So if you're interested in going AGU and hearing more about Ceres MIP, I'm actually contributing to that session, please send in an abstract. And we also have a journal article in review, primarily for the climate community, for climate modeling centers to assess the kinds of simulations we want to do. So I'm really excited about this activity. Okay, so conclusion, Ceres observations show a doubling of Earth's energy imbalance over the Ceres period. It's primarily associated with absorbed solar radiation. Despite these wild fluctuations in ASR and OLR, net seems to be robust and very stable across those 3 periods, down to 1/10 of a watt per square meter. So again, it implies that the rate of increase in planetary heat uptake is relatively insensitive to internal climate variability averaged over those periods. Finally, ASR and SST global and regional trends track each other really, really closely. The large ASR trend is primarily driven by changes in low and middle clouds. And in terms of the SST variability, it looks like the ocean mixed layer heating is primarily due to ocean fluxes as opposed to surface fluxes. And that's it. Thank you.
Yeah.
Thank you, Norman. We have time for a short question. Yes, please.
Thank you. And thank you, Norm, for including solar. I got to start with that. And I did notice it was the only parameter that you allocated 5 significant digits to. So, but in this center conclusion you have, the net, have you added up the uncertainties that go into producing that to tell how robust that constancy is?
Well, I don't have to add them up. I can actually compare amongst the different sensors that we have flying. So I could independently use all of these different sensors and see how consistent they are. And that's what I showed earlier in the slide. And they were, you know, the anomalies were consistent down to a couple of tenths of a watt per square meter. And the trends were consistent to better than a tenth of a watt per square meter. So, you know, that tells me that, and then the ocean comparison with the ocean heat content tendency is consistent to better than a tenth of a watt per square meter. So I would say that we're at that level of about a tenth, at least for this period. It's not to say that something might happen to the satellite instruments in the future where something happens and there's an anomaly, but for the series period, the data we've collected so far, we're at about that level based on all of these different sort of analyses we've done at about a tenth of a watt per square meter per decade uncertainty. The other thing I didn't point out is that, you know, the similarity between the net trends in those 3 periods, the solar is actually an important part. It's happening not just because of balancing between shortwave and long wave, reflected shortwave and outgoing long wave. You also have the absorbed solar radiation. The solar part is really important too. And so we get this consistency in the net trend for different reasons in different periods. And solar is one of those. So it's just, I don't know if it's a fluke or fortuitous that the net is so stable because it's happening for different reasons across different periods. So I'm sort of puzzled, scratching my head about that. But I don't think the uncertainty is really driving that result.
Thank you. I propose we move on to the next talk. We will have time for discussions later on at the end of the session. So the next talk is from Karina von Schuckmann on the inventory of reservoir of heat. Which one is yours? Oh, really? Okay.
PowerPoint.
Okay, maybe, can you do this? Because, can you do this? Let you do it. I don't think it's plugged in. I tried, but I didn't manage. Go ahead. So that's already shared, right? Please go.
Merci. Okay, thank you very much. And thank you very much for the opportunity to be here and to present the results from a community work on the heat stored in the Earth system from the 60s up to 2020 with the question, where does the energy go? So I want to point out that this is a community activity which is driven under GCOS. And so we have worked on 2 cycles with the first evaluation published in 2020, and the second one recently published and is going up to 2020 with a bunch of authors from more than 60 authors, which are covering the different expertise on the Earth system components from the ocean to the land, to the atmosphere, and also for the cryosphere. So just starting generally with the question that the point that the Earth's energy balance is one of the most fundamental conditions for making planet Earth conducive to sustaining life. So I will not detail here, you're all in-depth experts, but due to the accumulation of heat, anthropogenic accumulation of heat in the Earth system, we have the major storage in the ocean, but also important components, even if this from a global perspective are small numbers, like for example the 4% for melting the ice in the cryosphere. But this is making up, as we heard earlier this morning, about 60%, for example, for global sea level rise. So it's all an aspect of perspective, and we as this community are convinced that it's very important to understand, assess, and evaluate the different estimates for the different Earth system components to further discuss and engage the community and reply to these questions of where the heat is going. So this is coming to my question, why should we care about this? So why should we go into all those numbers? So as we have heard already, the Earth's energy imbalance with the total heat gain, which is increasing, determining the Earth's heat inventory, which is then providing the estimate for the heat stored in the atmosphere, on land, in the cryosphere, and in the ocean. And those is leading to different warming aspects in these different Earth system components. And this in turn is leading to the changes in the climate system, such as in the ocean, the increase of sea level from the warming and also from the mass increase. But also we have aspect in the ground ice volume, which is decreasing, the decrease in glaciers. That's just some examples for the cryosphere. But also for the atmosphere, we have the increase in weather extremes, atmospheric convections, etc., and on land like soil respiration, the increase in extremes, and so on. And those implications had been all assessed to have considerable implications for the ecosystems, but also for human systems, which had been all assessed in the recent IPCC report under Working Group 1 and in Working Group 2. So with this, we wanted to state that the Earth's heat inventory provides a measure of the current status and the future perspective of planetary warming, as we have heard in all the great talks this morning. And it also hence determines how much and where the heat is stored and how this changes over time, not only in the ocean, but also on land, atmosphere, cryosphere. And it's the best available estimate for the absolute value only, but not for the changes over time, of course. The integrated view, it provides an integrated view, as we heard, for example, also from Benoit this morning, on the effect of radiative climate forcing, the Earth's surface temperature response, and the climate sensitivity. It informs about the status and the perspectives of global warming, and it replies to the question, as often stated in the Handan papers, of how much heat is in the pipeline. And then it allows for assessing the status of the global climate observing system, which was one of the major foci of this work in order to understand where the gaps are and where we can improve the fit for purpose for climate monitoring of the global climate observing system and the provision of recommendations in this sense. And it enables really new and innovative multidisciplinary collaborations which had been not established before and which is leveraging new questions which will in turn lead to new science advances. And so there had been a lot of papers, a lot of discussions which were growing in parallel to this initiative. So I continue this. So this is what we have done, as you can guess. So it's the estimate of the heat storage on land, on the ocean, and the atmosphere, and in the cryosphere. So I will tackle each by each, and also going on to the recommendations for the observing systems we have provided through this initiative. So for heat available to warm land, it's an update of what has been provided in the publication in 2020, and it's based on borehole temperature profile measurements. So you can see the profile positions on the upper right for these in situ measurements, and providing you a global cumulative heat storage within the continental last months since the 60s. And what has been added for the first time this year, so we didn't include this in 2020, through extended collaboration with more experts, is also to provide a first estimate on the heat available to melt the permafrost, and also for warming the inland water bodies. And so it's a combination of data more or less, but more or less very much model results and reanalysis system results, leveraging again some aspects for the observing system recommendations. And so this is the overall result on the heat available to warm land, where we considered here permafrost and the water storage, inland water storage, with the different contributions. Of course, it's the major contributions from ground, but also from the permafrost aspect. But remember, these are different scales. So of course, the big body is the land. And so with the different results on these aspects, and there was a specific paper which had been published in parallel. So the recommendations came here. So what is the issue? There's a lack of subsurface temperature profiles, particularly after the year 2000 and in the Southern Hemisphere. So there is currently no existing international data acquisition or curating efforts available. So this data storage and recovery is really based only on a research initiative. So if this is over, there will be big data loss. So the recommendation is to increase the sampling, of course, and to implement the acquisition curating efforts, and with a high impact, as mentioned earlier. By the matter of time, I will not precise, but you can go there, but such as with the soil conditions, fundamental to understand the evolution of land-atmosphere interactions, important climate and meteorological phenomena, the increase of surface temperature, but also with respect to the increase of extremes on land. So for the permafrost, so this has been mostly based on models results, so because of a complete lack of ground ice and liquid water content data. So, so the current monitoring system for permafrost soils is focused on soil temperature with scarce sampling. And so the recommendation is to improve sampling, establish monitoring for ground ice and water contents, and improve simulation, allowing for the inclusion of other relevant processes. In other words, albeit, I mean, the tipping points are currently model evaluated, but we are not able to monitor one of those identified tipping points in Earth's climate. Then for the inland water storage, it's also limitation for lake bathymetry and lake mask, and also for the observations. And so there's a use of upcoming opportunities from the Earth observation data, and different recommendations on different aspects. So there had been also an estimate of the atmospheric heat content, combining reanalysis and satellite data. So these are the results. So this is an update what we had provided already in 2020. And based on the studies mentioned here in Steiner et al. And Kirchengast et al. In 22. And on the right-hand side, you can also again have a reflection on what you could see also from Norman in terms of the increase, which is also observed in the atmospheric heat content estimate. So also here the issue is that this heat storage relies only on unsustained global climate observing system. And there's also a data gap risk, particularly because of satellite orbit choices, which will risk for limiting data to mid and high latitudes. And earlier data are from reanalysis only. So there's a sustaining recommendation and high inclination orbit recommendations, and specific also validation in situ measurement improvements. Then there had been an effort under the lead of Azzurri et al. And Straneo et al. In combination with the people from IMBI, CLIMBI, etc. So we have all worked together in order to provide these estimates. So this is a combined estimate from observations, from remote in situ observation, remote sensing, but also model and reanalysis. And so by assuming that the energy uptake is directly proportional to the mass loss, so the heat uptake over this period is dominated by the sea ice, so particularly the Arctic sea ice, by the glaciers, and then the ice sheets starting from the Antarctic ice sheet, and then with a less strong contribution from the Greenland ice sheet. So there are a lot of issues for the cryosphere. So we had to rely on a very combined approach, and so there's a scarce sampling and a non-sustained observing system elements. Through this initiative, there was also a new approach already started in 2020, not to look on the changes in the cryosphere on an aspect of mass loss only. So for the first time, we started to look at this for the heat available to melt the ice, which is a new approach and which also identified immediate gaps in the observing system which do not exist today for data. This is like lacking ice melt below the sea level firn and ice temperatures. And so there are a lot of recommendations, including also similar to what had been done, for example, for the atmosphere with polar focused orbits and multi-frequency altimeters, recommendation to avoid gaps with earlier launch, Sentinel-1C, and reliable gravimetry, geotic ice velocity measurements, need for ice thickness and extent snow firn thickness and density. So there are a lot of recommendations, and open data access and coordinated international efforts for monitoring ice loss and related energy uptake. But this is a recommendation which can be held, I think, for the 3 observing system components. Then we have also assessed ocean heat content, and I'm very much looking forward to see upcoming talks in this workshop. So we have increased use of different data sets. So there had been the use of 15 different international in situ data products, and they also, as we know from previous studies, so there are not much news here, that the ocean warming over the period has increased at a rate which is comparable what has been done in other studies and also in IPCC. What has been new is that we could identify that the heat is sequestered into deeper layers of the ocean over the past 5 decades. That you can see, for example, on the very right side, identifying the different periods at the intermediate layer with increased inclusion into this layer. And then in parallel and comparison, what the top of the atmosphere radiation results show that, so that we have an increased warming rate from the stored part, which is one of the pillars for the Earth energy imbalance in terms of the absolute value. So recommendations are similar to what we have already heard from earlier publications for the ocean. So they are not new. They're not moving, but they are important. So they have a decadal scale increase currently observed, but with large uncertainties. So the observing system in the ocean currently undersamples the polar oceans and the deep ocean, and also the shallow areas. And we know that there are important projects under the way which are about to fill those gaps and new technical developments, and they have to be sustained and further fostered. And but we also need to continue to take care, and there are a lot of initiatives which are growing. Also new one, I think we will hear from this tomorrow from Matt Palmer in the talk, also on the historical data set. So there's more work to do where we can recover information and improve also the long-term estimates from the ocean heat content. So what we do, we were estimating then the heat gain. So we come to a specific number, 381, which is within uncertainties consistent to the IPCC, last IPCC. And so we have estimated then those numbers, which are also not new, but in comparison to what we have heard before, with specific, starting with a major pillar is the ocean, and then followed by land, cryosphere, and atmosphere. And by taking the rate of change of time, we come up then to the estimate of the values for the Earth's energy imbalance with about 0.5 and up to 0.8 watt per meter square over the different periods. So if you take, we have done in 2020, starting from 2010, and we have seen in the presentation, the time series, Norman has shown the different periods. You can even reach higher values if you start in 2010. So the question remains here that both cycles of this initiative on the Earth heat inventory evaluation have shown that the Earth energy imbalance has increased over the most recent decades and almost doubled. So as also Norman stated, we have published this in 2020 and we have republished this now. Then also, as we have heard this morning, in parallel and consistently, the top of the atmosphere radiation results show a similar result. So we are consistent here with this message, which is a quite spooky message. And of the most recent decades, and also from the independent approach, from the remote sensing approach, so the message from developed under Benoit and also Maria. So there are a lot of discussions under the way, what is going on, and I think it's one of the priorities to further understand what is happening, what is the interplay between natural variability and the long-term trend in order to understand what is going on, to further work on the uncertainties, which is at the heart center of the GBEX activity for the assessment for the Earth energy imbalance, to see if this really getting out of the uncertainties or if we are really underestimating the uncertainties here. So there are a lot of different questions, and which I think this workshop is very important to further tackle and to identify the way forwards to urgently understand what is happening. So we have heard already from Norman, I will not repeat some discussions. And we have also this paper from Kramer, which is accounting for a positive trend in a total planetary radiative imbalance to a combination of rising concentration of greenhouse gases and recent reductions also in aerosol emissions. So it's another aspect of discussion from many. And also then the study from Aguaman et al., who is relying on climate model tests and also linking this signal more to anthropogenic sources rather than variability. But we still need further understanding to really attribute this specific signature and to understand what is happening and to see what the evolution will be, particularly if we have seen that there will be a kind of net flux robustness in the signature. So if this is a 1 watt per meter net flux result, that's not good news. Okay, so this is just a summary on the different values. I think I'm running over time. And so with the different values, again, summarized and providing again the status, so in coherency with the rest of the introductory talks today, it's a very important indicator. So we have to continue to work together to improve our best estimates from the different observing systems, to learn from each other and to combine and optimize then results, and to continue to work hand in hand to tackle this global challenge. Thank you very much.
Thank you, Karina, and thank you for keeping the time. Do you have any questions? Yes, please.
One quick one. You went over pretty fast about river and lakes, that you're looking for more observations. What do you need, like beyond lake volume variation and surface temperature that we can get from space?
So it's also in terms of the bathymetry. I mean, you need to understand also, right, to the bathymetry aspects in order to get. I mean, you need this to calculate the content of a different bathymetry body. So so that's one very big uncertainty on the masks as well. And then of course, yes, of course, all the subsurface temperature and information you need to in order to understand to calculate the heat content. So these are the major recommendations. And yes, we have fully worked on this with the models from this approach, because there is a lack of databases in order to do this. And so it's not only the surface temperature needs, so you need a subsurface information. And so there's really a few information available. So, and also limited in terms of satellite bathymetry. I don't know if there are opportunities also from the indirect method. Again, if you look this from a global perspective, it's of course a very small number. But if you look at this in terms of what we have tried with this cascading effect, if you look from an implication perspective, it's a very important estimate as well.
Thanks.
And there's this paper from which has been, so where you can find more detailed information from Costa Valero. Yeah, it's just published in Earth ESD.
Yes, CG, please.
In the slide toward the end of your slide, you said the highly unlikely that the natural variability is explained in the increasing EI. Do you have any exceptional, unlikely explain internal variability. That do you have any source of your thought of saying something like that?
So as I said, what I'm doing here, I'm just synthesizing the current discussion in international literature. So these are not my results. So these are different outcomes. So what has been discussed as a source from Norman, what has been discussed in the Kramer paper, and what has been discussed in the model result from Raghuraman paper. And so they state there from the models that might be more a long-term aspect. But I wanted to show here that this is still an open discussion because the results and the discussions here, they are not coherent. So that shows that we still need to work together to really understand what is going on. So that was my intention to show this slide, to put some nourishment into the discussions the next 2 days, because we really have to tackle this. It's really important. So
Thank
I'm
you.
not stating anything here.
All right, thank you.
Other questions? I have one quick one. So I understand from your heat inventory, you get annual time series, right?
Yes.
I was wondering, have you compared your heat inventory with the CIRES over the 2000 to 2020? And if so, does the fact of adding up over ocean heat content the other components, does it enable to explain better the internal variability compared to CIRES?
I warmly invite you to a poster from Audrey Menier, and there we will have our replies on that one. So that is an opportunity. You go there and discuss, and I can come to the poster as well.
Okay. So next speaker is Maria Akuba, who will talk about trends and variability in Earth energy imbalance. You want to break now and do this afterwards? What do you reckon? Maybe it's already late. Maybe it's better to break now. So how do you feel in the room? Do you feel like breaking, right? Okay, let's break now. Yeah, let's break now, and then we will listen to you in the next sessions. Yes, Jerome, you want to add something?
The coffee break is ready, so let's not keep the people waiting. And I would like to make a comment. Karina mentioned posters, and people online wonder how they can see the posters. And so what I said this morning is that if you send us the posters on a PDF, we will put them on the website so they can be seen, downloaded, and so on. So make sure
Okay, thank you.
I'll send your posters so we can publish them. Thank you.
Thank you.
20-minute coffee break instead of 25?
Okay, 20 minutes coffee break for people online. So we shall reconvene at 25. So I'm not sure to know everything about this, but let's try. Okay. I'm not used to.
But it's not, yeah, I don't know. I'm not sharing this screen.
Oh, okay. Hold on.
Okay. 5 minutes, okay.
Maybe you can ask if anybody online can tell you.
Should I?
You're sharing already?
No, I don't know. We're
So
sharing
this. Is
this.
showing the screen?
Yeah.
Okay.
But it didn't share. Mine is behind.
This one is yours?
No,
No?
no.
Okay.
but it's a PDF, if that makes a difference. Because I think you're sharing PowerPoint.
Yeah.
You're sharing the PowerPoint app, not the screen.
Yeah, maybe put the screen to be shared. That would be easier for everybody. Put maybe the screen. Yeah, the screen, it's easier. So we don't have to change. Yeah.
Thank you.
And now that should work.
Yeah.
Thank you. Thanks.
No, you're welcome.
Is this on? Oh, yeah, this is on.
Yeah.
Yeah. Wait. Oh. Oh. Oh, I can do it.
So we start, the next talk was the last talk of the previous session by Maria Hakuba. And the title is The Trend and the Variability is in Earth Energy Imbalance since 2006.
Okay, thanks, Seiji. So this talk is going to be more like an outlook towards the GWEX EI assessment, or phase 1 of it, and what we think to do with the data that have been submitted so far. So the content will be a little bit of introduction and background to the GWEX EI assessment. I have a little excursion as to what EI is when you derive it from series. What does it mean? Because I get asked that question a lot. Then a few slides on the phase 1 GWEX EI intercomparison, a couple slides on systematic discrepancies that we find across observing systems. And if we have time, a few slides on or a summary of the JPL workshop we held in February. Okay, I mean, Benoit more or less covered that already. There's this new integrated assessment on an EI led by him and Tim. And this is just a few things that you find on the GWEX or WCRP website. And I think one main thing that we want to focus on is intercomparing estimates of the time rate of change of ocean heat content. So there's a focus on ocean heat content in this phase 1 assessment. And we're looking to understand the spread of estimates, where that spread comes from. We want to determine systematic errors that depend on various assumptions that go into those data products, and understanding the spread of uncertainties as well. And as Benoit said, maybe come up with best practices for estimating uncertainty. So this is information that you should be able to find online. A little more detail is on this other website that Benoit put up. That's also the website where we had started collecting data. To this date, we mostly have in situ products of ocean heat content. No reanalysis so far at all, and the 2 satellite-based estimates from Lagos and JPL. And the objectives are listed there and a few science questions. And maybe I was going to talk a little bit about the science questions. Again, uncertainties by product and across products is something we want to look at, and the differences. There was one question that I highlighted in orange because we haven't talked about this much. What is the degree of homogeneity and stability of each data record? We haven't talked about this much, but this was at the heart of the latest assessment on water vapor records. And I think in the precipitation assessment, they also looked at homogeneity. And I wonder, is that even a question that should be asked for EI and ocean heat content or not? And how would we go at it? But I will not really talk about this today because I haven't thought about it that much. We also want to, of course, look into ocean heat uptake or storage variability, identify periods or areas where data products agree or disagree, and why do they disagree. What is the quality of the data that we have in areas that are often undersampled at high latitudes in the lower deep ocean. And then, as I said, it's not only in situ, it's also satellite and reanalysis estimates that we want to look at. To my understanding, the assessment will last a few years. There will be more workshops held, and we're supposed to provide a report to GWEX at some point, which I think is going to be a culmination of all the work that we do as a community, all the papers that will be published. Yes, okay, let's go ahead. Another little excursion towards GCOS, because Karina just gave her talk. Under GCOS, they do complementary at work towards the energy, water, and carbon cycle closure. And under Karina's leadership, the latest assessment or heat inventory analysis just came out. So that's been very exciting and at the heart of the GCOS working group or task team on energy cycle, I think. There's also a latest GCOS implementation plan, and there are several actions that they mention with regard to EI, and it's usually towards, GCOS is mostly concerned looking at the state and improvement that you can make to the global observing system. But I feel like their goals are often complementary to what the WCRP does, which is a bit more sciencey often. And I just wanted to highlight a few, identify the gaps, of course, in the climate observing system with respect to energy. They also talk about novel remote sensing techniques that might be required or improved upon to obtain better estimates from space. Also talking about heat fluxes, especially latent and sensible heat fluxes at the surface. And also a recommendation on expanding the integrated global ocean observing system, one Argo. I'm not sure we have a one Argo talk, but Deep Argo will be presented on, I think, yeah. Anyway, just wanted to mention that. So another thing that happened last fall was an ISI workshop, also led by Benoit, Graham, Remy, Sonia, Michael Rast on the water and energy cycles. And without going into too much detail with this, there's this one outcome that we need to provide until fall of this year, and that's a paper on EEI. And that was tasked to me and a couple others in this room. And we said at the heart of this paper could be the phase 1 GWEX EEI intercomparison, which will focus on annual global mean or ocean heat content and storage intercomparisons across in situ satellite and reanalysis, looking into transferability, accelerations observed therein, and maybe also some regional discrepancies. Okay, wait, okay. That's it, I think I want to say about this. Yeah, another little excursion, because I feel like I get this question a lot, and there's two groups of people. There's people who say, why do you compare your ocean heat content changes to series? Series is adjusted to Argo data. Okay, and then there's people who say, or don't even know exactly what does the energy balancing mean in series, and they compare it to the ocean heat data and, think it's a completely independent estimate. And both groups are kind of right and wrong at the same time. So I'm plotting a data record by series that is not yet energy balanced. It's called series SYN. And this is not data that you usually are recommended for climate studies or EI studies at all, but I'm just plotting it here to address the fact that without the energy balancing, the mean EI derived from series data would be around 4 watts per square meters. And this, as we heard, is not reconcilable with other EI estimates that we have, and nor so the forcing and feedback estimates that should kind of match with that a little bit. And no surprise, if you calculate the cumulative heat content based on this data, you would end up with an average rate in ocean heat content that is about 5 times larger than the average that we know from actual ocean heat content observations. But Norman Loeb and series team have done a very good job in adjusting the radiation flux products called series EBAF. So if you plot that, you end up with a time series that looks almost identical, but now has a mean that kind of matches the independent estimates that we get from ocean and the other components, climate system components, ice, atmosphere, land, and so on. And I think the adjustment is made for a particular period, which I think goes from 2005 to 2018. But it kind of corrects for the systematic offset. Is that right? No. Well, it's close, but the average is... That's the average for the total time series that I calculated. It's not the number that you used for the adjustment. Yeah. But it's kind of close. And then, lo and behold, if you were to integrate that, you end up with this red line that people like to compare with ocean heat content time series. And now it matches. So what really is adjusted is just that systematic offset, or in other words, the trend in heat content on the right side. However, the trend in EI and the year-to-year variability is completely unaffected by this adjustment, which is shown by this comparison of EBAF and SYN. Okay. looking into the GWAX EI assessment results so far. This is figures made by Tim Boyer and Sébastien Forest. Did I say that right? Okay. Yeah. Okay, and to the left, Tim put together all the oceanic content time series that we have so far. There's many more. We should probably get all those together. And on the right is just the individual oceanic content time series compared to the series heat content integrated. And I'm saying there's a substantial spread in annual global ocean heat content estimates, but I don't think it's that substantial if you compare like estimates that are way older than today. I mean, that's state of the art. That's the best we have right now. But still there's a spread, and that can have many different reasons. Input data, they should be very similar across products. Oh. Yeah. Yeah. But I think Tim might have reduced it to 90%. Is that right?
The black line is the gray
Oh.
line.
Okay, thank you, Tim. Okay, quality control, as we will say, I think tomorrow mostly, plays an important role in the spread, different mapping techniques. I wonder if even the math that goes into globally and vertically integrating these data sets can differ, might have an impact. Sampling coverage, I think this has been investigated in the past, but might play a role as well. And what you end up with in terms of trends, so hard to see. Oh, it's cut off. I'm so sorry. Interesting. In this sample of data products that we have, we range between 0.46 watts per square meters to, anyway, 0.8. Sorry about that. Okay, so Tim also used the ocean heat content time series to derive ocean heat storage, or EI, from an ocean perspective. And at first glance, it doesn't look like that the EI year-to-year variability agrees very well across products, and that's based on global annual means, and does not agree all too well with series, which is hidden behind there in black. So if you do a brute force differencing on global annual mean ocean heat content, that's what you end up with. And that's kind of odd, because we had Norman's paper, and in your paper, there's a very nice comparison with the PMEL ocean heat storage changes. And that poses the question, do we need to define and adopt some best practices to get there? Because yeah. But I talked to Greg. He said that that might not have been the largest contribution. Yeah. Okay.
Sorry.
Karina had something.
My point is that the year-to-year variability, if you don't have altimetry to sort of help you with filling in gaps from that you get when you just look at Argo, you get lots of noise. And so the plot on the right here has both. You've got the Argo and the mapping.
Right.
Okay. The trend is going to be over a long enough period the same.
Understood.
Yes, and another sensitivity factor is also the processing, because you do a derivation, right, for heat content, and then also look, for example, this peak there in 2016. If you look in the series data, it's a sub-annual signal, and so Argo is resolving 1 year globally, or at least maximum maybe 3 months. That's how it is designed. So it's not resolving potentially the signature. So that's another aspect. And so this explains also the high sensitivity when you start to derive something which is not designed to resolve something monthly, right? So again, the target of Argo was 3 months, and not monthly. So
that's annual.
yes, but if you look a bit more in with a loop, you will see that this is a sub-annual signature, which is very strong, and you don't resolve it properly with Argo because it's not designed to resolve it. No, I don't know. I didn't know. Look at.
Well, these are annual 6 months apart. Yeah, I don't understand this.
Okay.
They get on a plane and come, and then they'll. We did. I can't remember what my point was.
But I mean, that's exciting that we have so much to discuss on this. So that means we need to really figure out how to do this best. Yeah, and I also was going to point out that if you use satellite-based estimates, and I think that's an update to the Marty et al., right? You get way better comparisons. And I also did some comparison quickly based on annual mean satellite-based ocean heat content. And that's just to show that whether I do first differencing or centered differences makes, you know, there's a lot of things that can go wrong in all this. Oh, I only have 5 minutes left. That's very unfortunate. Another thing that oh, okay. Yeah. Just quickly, I wanted to highlight that in an earlier paper, we saw a difference in how well ocean heat storage time series correlate with net radiative flux, depending on whether those data products use Argo only versus all in situ. And yeah, I thought we could look into that as well. And I think Tim might be doing that in a couple of days. There's a bunch of investigations that will look into causes for discrepancies, mapping, quality control. I think that's all tomorrow. And today, a lot of talks on the satellite-based EI. Oh, God. Okay. That's an example of a discrepancy across observing systems. We've noted that the satellite-based ocean heat uptake on average is always a little higher than when derived from in situ observations, but we also noted that the discrepancy, but agrees with an uncertainties, the discrepancy seems to grow since about 2016. And Anne Barnou is going to talk about this, and back last year they had a nice paper on partially minimizing this discrepancy by doing a correction to the altimetry record. And then Jérôme showed an update to that and looked like there's no discrepancy left at all. So I'm excited to see what Anne is going to talk about. Another puzzle that we had seen in that paper back in 21 is when we compared all the different in situ-based data, that most of them kind of showed a decrease in allosteric sea level change since 2016. And I think it's back then I was told that's an artifact. I know now it might be not. There will be talks on this as well, I think tomorrow. Bias in Argo salinity by Annie Wong and diagnosing recent allosteric changes by James Rigg. I guess the question is, should I stop now? I could do this. I was going to summarize a little bit the outcome of Okay. So we did hold a little workshop at JPL on Earth's energy imbalance, and it was sponsored by the so-called Center for Climate Sciences. And I've been wanting to do this for years already, and motivated by this Toulouse workshop in 2018, mostly. That was my first touching point with this very interdisciplinary community, and I thought it was amazing, and I wanted to do something on a smaller scale for JPL. Since then, I've worked myself on different EI-related topics. And this was really to be informative, mostly for JPL, on the various aspects that touch on EI research and identifying contributions that we could do. We also have a quite vast ocean community at JPL, which is very fitting. So overall, in a nutshell, I think what I wanted to do was raise awareness that EI research ought to be an area of focus for us at JPL. And thanks very much for all the people who actually came in person that we invited to join us. I was then asked it was successful in the sense that leaders above me asked me for summaries. And this is one of the summaries that I had put together about the motivation, objectives, topics covered, and preliminary recommendations. And then we had Gavin Schmidt coming to talk about EI and model prediction. Peter talked about the radiometric challenge of measuring the absolute magnitude of EI, future mission concepts for EI, variability and change in EI, spectral radiation measurements that kind of feed into understanding processes on a spectral fingerprinting way. And then we had a full day just examining the heat inventory for ocean, cryosphere, atmosphere, and land, which allowed me to involve the JPL community more broadly. And also some cycle and water cycle people who joined us. And some of the recommendations I thought could be summarized as, no matter what we're interested in, EI quantification, looking into the causes and implications of EI will always, in some form, require an integrated assessment of various data sets and models. And also to understand global change, you need to have an understanding of processes and changes regionally. The other recommendation that we came up with is that if we want to do a direct EI measurement from space, it might require alternative methods. And for interpreting and attributing change in EI, we found that measuring EI or radiation by itself is not enough. There always needs to be a modeling component of some sort to figure out what's going on. We also identified various emerging misfits and accelerations in different climate system components. Okay. But I think one of the biggest outcomes was that there's various contributions that JPL is already making. They just need to be streamlined a little bit and strengthened. I was also asked to summarize those. I won't go over that now, but it's a nice slide. Enjoy. 1, 2, 3. Okay. I went ahead and started drafting kind of a summary of all the building blocks that are needed for what I think effective EI research. And I just wanted to highlight that the absolute magnitude of EI is just the tip of the iceberg. There's all these kinds of different scales that are on the slopes and components that we need to figure out. And once you have an overview of these building blocks, you can also attribute challenges and gaps therein, and especially gaps and challenges that JPL maybe can help with. Okay, with this, sorry. Oh, wrong. Thank you.
Move on to our next session, and next speaker is Greg Kopp. Right? Yeah, right. Yeah, good. The title is Summary of Earth Energy Balance Assessment Report from the 2022 BIMP WMO Meteorology for Climate Action Workshop.
Yeah, this is actually going to be a summary of a few different workshops that we've had that address Earth energy imbalance and needs that the National Metrology Institutes can perhaps help with to be able to improve measurements. Organizing team for this particular workshop is shown at the bottom here. So thanks to inputs from all of them and the broader community in terms of what came to the outcome of that particular workshop. But like I said, there have been several major workshops over the last decade or so, and 3 of them are shown here, going back to 2010 with measurement challenges for global observation systems for climate change monitoring. One in 2019 that Nigel hosted at NPL on SI traceable space-based climate observing systems. And then more recently in 2022, a workshop on metrology for climate action that led to several recommendations. One subgroup of which was Earth Energy Imbalance. Going back to the 2019 one, this is the one Nigel hosted that had about 100 international participants, and it was focused on space-based measurements to do climate observations. And the outcome of this was a real emphasis on SI traceability for space-based measurements that could help us improve climate measurements directly. So less so on ground-based, but more pure space. But it did lead to a 224-page workshop report that has been released that included inputs from all 90 of the co-authors, authors, and led to a set of recommendations. That was something that I think Bruce Wilicki said took a lot longer than we thought when we initially said we were going to write it up in a month or two, but came out to be a whole bunch better than he thought it was ever going to be in the first place. So that has been released now. It does include in it a lot of assessments, such as details like shown here. The left side plot is for reflected solar capabilities. The right side plot is for thermal infrared capabilities, but these are capabilities of existing instruments in red, and in green, the needs that the climate community has for how well these measurements need to be made. The dashed line distinguishes to the right of it the upcoming hope for measurements with SI traceable satellites, so SITSATs, things that are kind of a national metrology institute in space, where you can do almost as well in space as you can in the best labs on the ground. And that's a direction that we want the future to be able to go, to be able to improve the measurement capabilities via these SITSATs, not just directly for their own measurements, but for cross-calibrating other instruments that are up on orbit. If you can put something up on orbit that's a good reference, then it can cross-calibrate several other on-orbit instruments, providing broader spatial and temporal coverage. So this is a direction that was an outcome emphasis of that particular workshop, and hopefully emphasis that directions ESA, NASA, and the Chinese Space Agency are all heading. These are several of the different areas regarding climate that were discussed at that workshop. Earth radiation budget being number 6 in there, linked to reflected solar measurements directly below it, and thermal infrared directly below that. So that was a real useful report, but then that was followed on this last September by a BIPM and WMO Metrology for Climate Action workshop. And that one was split into 2 themes. Theme 1 being, what can the National Metrology Institutes do to help support measurements that we want for climate change? Theme 2, a little less relevant here, focused on greenhouse gas emissions. But theme 1 did include a separate session on Earth Energy Balance, in which we had the group of us that I listed as co-authors on this talk, but also 22 other accepted presentations and posters that were given. And the format of this, that's interesting. If you turn your head sideways, you can read kind of the way the format of the workshop went. The first day was sort of overview presentations. Second day was a whole bunch of online posters and pre-recorded presentations that people could go through. But the interesting thing was more the last 2 days were interactive discussions that we held for, given all of these different inputs, these different needs, how are we going to get there? What are the recommendations that we have? So this is where we really collected, kind of gave people a few creative ideas in the first few days, and then let them formulate what the recommendations and desires were for being able to achieve some of these objectives. And that led to a list of recommendations for each of the sessions. So This is an older version of something that's been modified. I'm amazed I've made it up to slide 9 without showing this. This is a image that's going to be, I think, in about everybody's presentation here. So if we could measure Earth energy balance, and I measure total solar irradiance, so that's nice and easy. I look at the sun, I measure how much energy is coming in, what area I collected over. Bingo, I've got solar, I've got one of the three parameters here. If we could measure Earth energy balance, if we could measure the incoming, the outgoing infrared, the outgoing shortwave, we've got it right there. That's easy. Total solar radiance we do reasonably well, and then chatting again once more and appreciating from Norman the complexities of measuring all of that outgoing, a little more difficult. But 99.97% of the energy heating the Earth is coming from the sun. This is a wonderful chart that Andrew Kren put together as part of his thesis a few years ago, coming up with all of the different heating sources for the Earth. And of course, there's the sun pouring in energy. The next most, I wouldn't say dominant, but the next largest things are down a factor of 4,000 from what we get from the sun, and they're heat flux from the Earth's interior, radioactive decay, geothermal, but they don't add up to be very much. And then there are a lot of neat secondary sources of the sun. It reflects off the moon and heats the Earth a little bit. It heats up the zodiacal light and heats up the Earth a little bit. And by little bit, I'm serious when I say little bit. Some of those are down to be about a millionth of what we get from the sun directly. Some even less than that. And if you add up all of those secondary sources of energy and the secondary sources of solar and non-solar energy, the net effect of all of those is 3,000 times less than what we get from the sun. So starting off, we've got that total solar radiance. We know that's what's coming in, and there's very little that's adding to that. So if you want to look at something, and it's getting easier with time now, isn't it? Because the imbalance is getting to be bigger. But if you want to measure something as small as 0.4 watts per square meter of an imbalance, and you need to do it with incoming and outgoing infrared and outgoing shortwave, each one of those on an absolute scale, you need to be able to measure to about 300 parts per million, or 0.03% on an absolute scale to do it reasonably well. The total solar irradiance on the left bottom, we do that reasonably well. Do that to about 150 parts per million, or 0.015% on an absolute scale. But you start to look at the outgoing thermal, the outgoing solar, the spatial variations in them, the temporal variations, anisotropies and what's going out, the ability to sample all of that over 4 pi steradians. Things get just a touch more difficult, and it's hard to get down to that 300 parts per million in a direct measurement. But ideally, that would be wonderful to be able to do. You also, since we can't sit up there in space and directly measure all of the outgoing and all of the incoming like we'd really like to, because that would give us all of the energy imbalance and we'd be done. Instead, we need to know where that stuff is going. As Karina said, where's the energy go? Some of it, a lot of it goes into the atmosphere, and it depends on wavelength. Where energy gets absorbed in the atmosphere or on the ground depends a bit on wavelength. So we need to know the incoming spectral solar radiance as well as the total. So again, since we can't measure the incoming and the outgoing well enough, we need to know where the energy's going. If we knew all of the incoming and or we knew all of the outgoing, or we knew where it's all going, if we knew 2 of those 3, we've got our energy imbalance. We've got the incoming pretty well. The outgoing's more difficult. And we combine that a bit with trying to figure out where the energy is going, to figure out what the real imbalance is. But it's that group of three that we really have to focus on. The recommendations from that Earth energy balance subgroup in this last organized meeting did lead to three areas that we want to be able to improve. One is directly improving the radiometric measurements, improving the absolute accuracies, maintaining stabilities. Focus there eventually is moving towards these SI traceable satellites, the SITSATs. To do some of those improvements, how can the National Metrology Institutes help? And that a lot is via calibration references, improvements to sources, detectors across the ultraviolet, the thermal infrared, black bodies. Another interesting concept is being able to take Earth-looking instruments and calibrate them off of the moon. We know the sun really well, but not many instruments can cross-calibrate themselves off of the sun directly. Minor detail being that it's about 1 million times brighter than the Earth that they're trying to look at most of the time. But the moon is about the same radiance level that you see from the Earth. So most on-orbit sensors can calibrate themselves by looking directly at the moon, if we could calibrate the moon well enough. So that's an emphasis that we'd like to be able to recommend going forward. And a lot of recommendations for Earth heat inventory. So in summary, we want to know what is the radiometric energy coming in, what is it going out. We want to be able to improve it with different ground or space-based calibration sources. And we want to know where it goes, what oceans, land, permafrost, cryosphere, again, like Karina was giving us a good overview of. For each of these topics, what we wrote up were various lists of what is the issue currently and what is the recommendation, again, collecting inputs from the broader community. So we've got that all detailed in an upcoming publication. But here's the summary of those. This is a report that's almost out, should be out next month for National Metrology Institute's responses or recommendations to be able to improve what they can do for metrology for climate actions. But on the way of Earth energy balance, the recommendations were to improve the radiometric measurements. And this is total solar radiance, spectral solar radiance, outgoing thermal. Ultimately, we won't let up on this goal of it would be nice to do this on an absolute scale, kind of getting down to the 0.01% level, maintaining continuity and stability in the meanwhile at about 0.01% per decade capabilities, initiating SITSATs, and several of them are coming up, Clario Pathfinder, Truths, Chinese-based radiometric, I don't remember what the B is there, sorry, and Forum doing SITSAT for infrared in space. These are instruments that have got about 10 times better accuracy improvements for benchmarking climate and this intercalibration capability for being able to extend themselves via other calibrations to other on-orbit sensors. Need to improve calibration sources, ultraviolet, thermal, probably via FTIRs, getting down to about 100 millikelvins, 3 sigma accuracy, possibly through improved black bodies using fixed point phase transition cells was one of the recommendations for being able to acquire better thermal outgoing measurements. And lunar calibrations. Clario, Arcstone, and Air Lucy are all working on that, getting the moon down to be kind of at the 1% level, which requires about 3 years of observations to acquire all of the different lunar phase angles and libration angles. Would like to improve knowledge of heat storage, and this comes from understanding the ocean better, improvements to Argo, sampling depths greater than 2,000 meters, and the shallower surface areas, closer to the surface than 300 meters or so. Getting subsurface sampling and international curation from the land measurements. Permafrost, we need ice and water content, soil temperature measurements, and cryosphere coming from gravimetric, geodetic, and ice velocity and thickness, especially near the poles, which are undersampled right now. And again, initiating SITSATs to be able to broaden the scope and improve the accuracy of measurements. Clario is likely to be the first of those, getting launched in a little over a year on the International Space Station, and going through a whole bunch of various calibrations and corrections shown in that long list of items there. This is sort of what it should be able to do from space, a little bit better than 0.3% absolute accuracy radiometrically across this spectral range, and it will have spatial and spectral resolution as it's sampling the Earth with good radiometry to both provide a benchmark and to provide intercalibrations to other on-orbit sensors. And here I do want to mention a distinction between continuity and stability. Having an instrument that's ultimately you'd really like good absolute accuracy. In lieu of that, we often fall back on continuity and stability. If we have continual measurements and stable measurements, and you need both, continuity doesn't help you without stability. Stability is no good without continuity. You can detect a trend with continuity and stability. And if you want to detect trends over a long period of time, and by long I mean climate timescales, multi-decades, your uncertainties as you start linking together one instrument to the successive one, those monotonically increase. That is, you never come along if you're just doing stability and continuity and make things better, get something way in the future tied back to the present day without having monotonically increasing stabilities in the interim. So every transition you make is going to increase your uncertainties a little bit. The risk of a gap as you go forward, if you have a gap, the longer this record gets to be, the more likelihood there is that you're going to have a data gap somewhere in there, at which point you can lose that entire record. So relative uncertainties are good over short time periods, but the longer you go, the more you start to rely on absolute accuracy. If you have something that you can launch today with very low uncertainties and something way in the future you can launch also with very low uncertainties, and they differ, and that difference is outside of their individual uncertainties, then you know you've really seen a trend. And the longer your time period gets to be, the longer of a trend you're looking for, the more you're going to rely on absolute accuracies. So these can be independent of time and temporal separation. Absolute accuracy lets you span data gaps, and it really helps over climate timescales. A little example in the bottom is several different instruments. If I stitch those together via their overlap and stability, my uncertainties increase with time. You can do that going forward or backward with instruments. But the only way that you can span a data gap is with absolute accuracy. So yeah, it's difficult to do, but absolute accuracies in these SI traceable types of measurements really are the best way long term to be able to measure climate trends. So let me end right there, and thanks. Take questions. Oh yeah, give it to Norm, who's going to tell me why I can't do absolute accuracy in space.
No, I think you can, and I think you should, but I don't think, well, first of all, the numbers you showed at the beginning of absolute accuracy requirements from that workshop you had, I think, in England.
Like 0.03% that you didn't like.
0.3%, I think, absolute accuracy?
I was doing better than that, 0.03%.
In terms of absolute accuracy?
Yeah, so I know.
Well, you were showing series was 2%, and then you said, I thought it was 0.3% absolute accuracy.
The 0.03%
climate requirement, which is...
Oh, for Clario.
Yeah,
Mario
well,
was aiming for 0.3%.
yeah. So I guess there's two things. I think it's great to strive for better absolute accuracy, but let's not forget, we're talking about radiation budget, and there's a lot more than just a broadband instrument that goes into producing those data products. So even with a perfectly calibrated broadband measurement, you're still not going to be able to bridge a gap because you've got other uncertainties. And so you absolutely need overlap. Now, a gap is just going to increase uncertainty. It won't kill the record necessarily. It's just you're going to have to be it'll increase uncertainty. You have to come up with other ways of figuring out. But the thing is, I think if I were to pick and choose between absolute accuracy and stability, if we assume they're completely independent, which they're not, but if we assume they were completely independent, I would pick stability over absolute accuracy, and I would say I need overlap. If you give me overlap and stability, I could produce a long-term record and do trends. If you just give me absolute accuracy, I'm lost because of all of the other sources of uncertainty that are going to cause heartburn in terms of creating a continuous, seamless record. So I think we talk about absolute accuracy as the Holy Grail, but I think the Holy Grail is stability. And I guess my question to you is, so if you do improvements in the instruments in terms of their absolute accuracy, are you getting better stability for free, or is in the engineering world you have to do something to really guarantee stability, or do they just one comes for free? Do you know?
They don't come for free, but they do come coupled. So if you're doing something better, you can almost, it's not quite right, but you can almost think of it as stability as the derivative of your uncertainties in absolute accuracy. So if you start off with an absolute accuracy of something that's small, and then that absolute accuracy is going to increase with time on orbit, that derivative is kind of your stability. It doesn't hold up completely, but that's a simplistic way of thinking of it. But that's a way where they are a little bit coupled.
Right.
So you often get one without the other. In terms of what the best approach is, if we were to sit down today and say, we're going to look for this trend that's going to go for a century, and I can make an instrument that's going to last for 5 years at a time, how much am I going to count on NASA or ESA giving me, well, I need 20 5-year missions and I need overlap, so now maybe I need 25. And how much are those funding agencies going to be consistent for every year of the next 100 years versus, do I build one of these today and do I build another one 100 years from now? Do I want to rely on funding agencies for consistency for 100 years? Or do I want to rely on 2 instruments I can make 100 years apart?
Well, why not? Why can't we? I mean, we're doing that with surface temperature, which is a poor measure of the climate. It's what we use. But why should we be saying, well, yeah, the funding agencies are just not going to continue this fundamental measure of the climate system? Well, that tells me they don't care about climate. So to me, I look at it a different way. I say it's absolutely essential that funding agencies continue to continuously measure things like the ocean heat content, ocean temperatures, the energy budget. All of those are so fundamental to the climate system that they have to. Yeah. And it's not just a choice. And, unfortunately, we're not there. That's not happening. But maybe, with efforts like this, and as we see these emerging trends, yeah, someone will say, well, maybe we should be planning better and have sustained plans to continue the measurements, and we can avoid a gap if you fly enough of those instruments. Some will fail, but you'll have others. Yep. So I don't think we should say, well, we're defeated and we have to rely on instruments that can tolerate a gap, because I don't think we're going to be there. As I mentioned, I think there's other sources, not just absolute accuracy. There's other things, because there's time, space, sampling, all of that has to get into these products, and absolute calibration doesn't answer. It's one component of many, and you need overlap to be able to anchor things, make the record seamless. That's just, we're not going to get around that one. As much as we'd like to, we're not going to get around that. It's just
No.
a given.
No, I agree. We're not. And I'm not proposing we give up on either one of them. But these are kind of the distinctions between where stability and continuity helps us and where absolute accuracy helps us. And since they are a little bit coupled, we kind of get a little bit of one with the other. And we shouldn't give up on either. We should be trying for both of them. Both have their advantages. So.
Move on to next speaker. Next speaker is Benoit. I guess I never correctly pronounce your last name. And
yeah, Messignac, but yeah, forget about it.
All right. The title is Historical Observation of the Earth Energy Budget Show the Time Variation of the Climate Feedback Parameter are associated with the Pacific Decadal Oscillation. Well, not long title.
Yeah, well, actually, yeah, I made it shorter in the presentation. So thank you, Seji. So in this presentation, I'd like to present you the results of a recent study we've developed with my team and Norman, where we extended the Earth energy imbalance record back to 1955, and we used this extended record to evaluate the time variation of the climate feedback parameter. Okay, just before getting into the details of this study, let me give a few elements of motivation. So why do we want to estimate the climate feedback parameter? The first motivation, of course, and you all expect this, we want to determine this climate feedback parameter, which we usually call lambda, because it's tightly linked with the climate sensitivity, which is a global surface temperature rise after a doubling of pre-industrial CO2 concentrations. And that's a classical equation. And if you got a good estimate of lambda, then you can have a good estimate of the climate sensitivity. And you know how much the climate sensitivity is important for the climate community, but also out of the climate community. It's because it makes a link between impact and emissions. The impacts in the climate system, like floods and drought, and for example, sea level rise, they scale on the surface temperature. And the emissions, the greenhouse gases emissions, shape the forcing of CO2 today. And so when you provide an estimate of the climate sensitivity, you provide a direct link between impacts and emissions. And so it's very useful even out of the climate community because it's used by geographers and economists to estimate adaptation cost and mitigation cost and make like benefit to cost ratios and analysis. So that's definitely one thing which is important. It's very well developed in the community. We try to provide, as a physical science, the physical climate science community, we try to provide the best estimate to geographers and economists. But I think there is another reason why, for us as physicists, we want to estimate precisely the climate feedback parameter. And it's linked to the global energy budget. And it is because the global climate feedback parameter is actually, at the first order, it is the linear tangent, it characterizes the linear tangent approximation of this global energy budget. And so what gives the global climate feedback parameter is actually the sensitivity of this global energy budget to surface warming. And when we want to understand climate change, we want to understand how this global energy budget is changing with surface warming. So let me show you quickly why lambda is this it characterizes the linear tangent approximation of this energy budget. So I will take in the next slide the energy budget and smash it from top to bottom and just make a link between the Earth energy imbalance and surface temperature. And you will see that lambda then plays a very important role. So if we call Ri the incoming radiation from the sun, which depends on the sun constant, and Ro the outgoing radiation, which is in shortwave radiation and infrared radiation, and Ro depends on the concentration of greenhouse gases, the temperature of the vertical temperature in the atmosphere, and the feedback from water vapor, the temperature gradient, the cloud feedback. and the surface albedo feedback. And they all depend on the temperature in the atmosphere. If you apply the first law of thermodynamics to the climate system, then you know that the Earth's energy imbalance is equal to the difference between the incoming radiation and the outgoing radiation. And when this is positive, the system is storing energy, dE. So now if you consider this at global scale and on monthly and longer time scales, then the system is at the radiative convective equilibrium. That means that this radiative convective equilibrium will fix the gradient, the temperature gradient in the atmosphere. And so you can characterize this temperature in the atmosphere by just one value on the vertical, and you can take the surface value. And so you have this new function for EI, which is dependent only on the surface temperature. And now, if you consider perturbation in greenhouse gases into the atmosphere, in the concentration in greenhouse gases, and you consider the associated perturbation in surface temperature, then you can develop this with a Taylor development in the anomaly in surface temperature, and you get this simple equation, which is exactly a way, it's a simple way to smash this global energy budget from top to bottom. And you get the Earth energy imbalance, which is equal to the relative forcing from the greenhouse gases and the relative response of the Earth, which is linear with the surface temperature warming. And you see that this constant naturally appears from the equations. And this is the global climate feedback parameters. And what it tells you, in which sense the global energy budget is changing. Because the climate is stable, lambda is negative. And so when you increase the relative forcing, you increase the relative response of the Earth. And then the Earth energy imbalance is getting smaller as the relative response of the Earth is responding to the forcing. And then the energy that is stored in the system is getting smaller, and this temperature is getting back to an equilibrium. So that's the zero-D energy budget. And you see now how important is this climate feedback parameter. Now, recent study suggests that the climate feedback, that the relative response of the Earth does not only depend on the global mean surface temperature, it also depends on the distribution of the surface temperature. And if you put this distribution of the surface temperature in a global energy budget like this, it appears as time variations in lambda. So this is very important because if lambda is changing with time, what does it mean? It means that this global energy budget is not sensitive to the same way at the same time to the radiative forcing from CO2. And so we want to know these variations because we want to know when our global energy budget is more sensitive and when it is less sensitive. When lambda is getting closer to zero, then for the same relative forcing, the energy budget will answer much stronger. When lambda is far from zero and very negative, then it will answer in a much more smooth manner. This has been shown by theories and climate models, GCMs. We have also some hints from the recent study from Norman, who showed that after the hiatus, what Norman talked about this morning, that after the hiatus there was this sharp decrease in shortwave linked to a sharp decrease in the cover of low clouds, which was linked to a pattern of SST, close to a PDO pattern after the hiatus. But we have few observational confirmations that lambda is changing with time, and we don't know to which extent it is changing in the real climate system. So what I propose here is to use an extended record of Earth energy imbalance and to use a record of the surface global mean surface temperature, and to use both to estimate the variations of lambda along time. So what we do is quite simple. So we take this equation, we isolate lambda, and over different time windows, we estimate the Earth energy imbalance minus the relative forcing, and we regress it against the global mean surface temperature. We will take different time windows. So the shortest length will be 25 years. So we will take 25 years time windows, and we take successive windows that are shifted by 1 year. And then after we will test with other lengths of time windows. But over each time window, we will regress, Earth energy imbalance minus relative forcing over the surface temperature. For the global mean surface temperature, we take the Hardt-Krutt and Gies time series, which are corrected for gaps in the poles, and they're corrected for biases in the satellite SST. For the Earth energy imbalance, we used in situ estimate of the ocean heat uptake from in situ data. So we use 4 data sets, the EN4, IAP dataset, the dataset from NOAA, and the dataset from Ishii and colleagues. This is for the upper part of the ocean. And we complete the deep part of the ocean with Debria and colleagues' estimate of the deep ocean warming from 1993 on, and we take 0 as Karina did in her study in 2020 before 1990. We may have some systematic issues. There are systematic errors in those data sets. First, coming from sampling errors. So to address this problem, we use another data set from Baniel and De Vries, which is a autoregressive neural network, which is using in situ data, and it's propagating like data from well-sampled time and space regions to sparsely sampled regions. It has been tested against synthetic data, with the exact sampling of the historical data, and it gives good results over the synthetic data. So we expect these extra data sets to cover this problem of systematic bias in situ observations. We may have other systematic instrumental errors, which are coming from corrections that are done to in situ data, and which can be the same corrections for different data sets. So to address this, we use a geodetic approach to estimate an independent ocean heat uptake estimate. So the geodetic approach, you know it, we use a sea level budget. So we use a sea level measurement, the measurement of sea level, and we correct it for the mass component. So we get a thermospheric sea level from which we deduce the ocean heat content. So to do this, we use a sea level budget reconstruction from Frederiksen and colleagues published in 2020. They reconstruct the sea level budget over the 20th century. So we use the sea level observations from tide gauge records back to 1955, and we use the mass component from Frederiksen, and we correct it for this mass component, and we get an independent estimate of the ocean heat content. And so this extra estimate enables to address this issue of potential instrumental errors, because we have a very different, an estimate based on totally different instruments. You can see below the time series of this ocean heat content, and the dashed line is when it is corrected for volcanic eruptions. I'll come back to this later on. For the radiative forcing, we use the IR6 IPCC radiative forcing with the updated forcing from aerosols from Baillois and colleagues. Now, we take different, so I will start with 25-year time windows. We take 25-year time windows that start in 1957 and end in 2017. And we shift them by 1 year. And over each time window, we make the regression of Earth energy imbalance minus radiative forcing against the surface temperature. So this 25-year time windows is this line here you can see on the bottom. So that's for windows of 25-year lengths. And the date you can see on the bottom of the plot is actually the central date of the window. So the first window, which is centered in 1970, started in 1957 and end in 1982. And we compute here a value for lambda as a global climate feedback parameter. And we do this for each window, shifting by 1 year. And it gives this line. And then we do this for other windows, which are longer, like 30-year windows, 25-year length windows, 40 years. And of course, for the windows, which is 58, which has the length 58 years, we just have one window. So we have one estimate of lambda, all right? So it's interesting to read this triangle from left to right. And when you read it from left to right, you have an idea of the time variations of lambda across time. And what is interesting is that you see that lambda is changing with time significantly, with changes up to 1 watt per square meter sometimes, at least a few watt per square meters per Kelvin, but sometimes it's up to 1 watt per square meter per Kelvin. So what could make this change lambda? The first thing that comes into mind is, of course, volcanic eruptions.
volcanic eruptions are known to change the pattern of SST, but also to change the relative response and to change the lambda. So we've corrected this for volcanic eruptions using GCMs. And so it removes some small-scale features, especially around the dates for periods that start at some large eruptions like Montagong, El Chichon, or Mont Saint Helens. But the global pictures remain the same. We still have large variations of lambda in time. And the question is, what makes this? What makes the global climate feedback parameter change at those timescales? So what we've done is we extracted the time series of lambda for the 25-year window here, and we plotted this time series. We verified that the changes in lambda are significant, and the changes between the minimum and maximum here and the maximum and minimum here, they are significant at the 90% confidence level. And then we regressed it against the sea surface temperature. And that's the pattern we got out of this regression. We got out the pattern which is very close to the Pacific decadal oscillation patterns. So that means that the variations of the global climate feedback parameter you're observing here is definitely linked with the Pacific decadal oscillation because this pattern is representative of this oscillation. When we take the index of the PDO and we try to regress it against the time series of lambda, you see that we have a good agreement and we have a correlation around 0.9. We tried other indices, other climate modes like NAO. We also tried the Southern Annular Mode. We tried also the Indian Ocean Dipole, but the regression is never significant. So that means that this is consistent with the finding of Norman at the end of the hiatus, because it shows that the variations of the global climate feedback parameter is sensitive to the sea surface temperature pattern. And in his finding, Norman showed that the cloud feedback, the cloud cover was changing with the SST pattern, suggesting that the cloud feedback could change just because of a change in the pattern of SST. And this is giving a larger context to interpret these results over the last decades. And it shows that actually the pattern in SST could be linked to the changes in the global climate feedback parameter on decadal timescales. Now the question is, do climate models reproduce this? So climate models, if you take climate models, actually the atmospheric part of climate models, and you force them at the boundary with the sea surface temperature, so they have the same internal variability as observations, and you look how lambda is changing in 30-year time windows, and you have this time series here in black, which is the mean of the gray time series for different models and different realizations. And you see that climate models show that the climate feedback parameter is changing with time indeed. However, the main cause for this, and the amplitude is close. We are talking about a few watts per square meters per Kelvin, up to 1 watt per square meter per Kelvin. However, the cause for this amplitude in the climate models is rather forcing than internal variability. And if we take the same period as the one we are looking at, this period here, actually climate models are not moving that much during that period, and they do not catch these changes of the global climate feedback parameter with the internal variability and the PDO. And that's a concerning issue because this means that there could be a bias in climate models in reproducing the changes in the global climate feedback parameter. And climate models show that when we double CO2 in the atmosphere, the global climate feedback parameter tends to change with time, getting closer to zero, which makes the climate sensitivity be higher than what we expect from observations. But this raised doubt about the capacity of those climate models to actually catch how lambda is changing with the sea surface temperature pattern. So it gives, and that's another plot where we do the correlation between the lambda time variations in climate models and the pattern of SST in the climate models. And you see that After 1980, we catch some of the PDO pattern, but before 1980, if you look at the whole period 1970 to 2005, we don't have these PDO patterns that we have in observations. Okay, it brings me to my conclusion. So observations of the Earth energy imbalance since 1957 exactly enable to estimate the time variations in lambda, but only since 1971 because we need windows of at least 25 years because lambda is really an integrated variable. Earth energy imbalance and surface temperature records confirm lambda is changing significantly with time. But we find in observations that the changes in lambda are synchronous with the Pacific decadal oscillation. So it suggests an important effect of the Pacific decadal oscillation and the internal variability on lambda. And that's something we don't see in AMIP simulations. That is the atmospheric component of the climate models, which is forced with the SST at the surface, especially before 1980. So why is that? Well, it's not clear. That could be a deficiency in the SST record before 1980, which is less precise. And for example, maybe the small scale is not resolved and it doesn't trigger like a deep convection that would trigger a change in low clouds through the Walker circulation. So that could be a deficiency in the SST record that forces the models. That could be also a problem in models. 2-week tropical response of low clouds, something that Norman showed in after in his study on the hiatus. Too large sensitivity of the relative response to the Southern Ocean SST as well. Climate models show a very high sensitivity to the SST in the Southern Ocean, which we don't find in observations. It's important to solve this issue in the future because the climate model estimate of the ECS and of the energy budget, the changes in the energy budget depend on their capability to catch these variations of lambda with sea surface temperature. Thank you.
Thanks, Benoit. Very interesting, this connection with the Pacific decadal oscillation. You explain it with the cloud feedback, but couldn't be that also what you see on the SST is the signature of a heat redistribution in the interior ocean. So this could also affect the way lambda is shaped a long time, not only the cloud feedback. Do you think could affect somehow this? Also, why you don't explain the variation before 1980?
Yeah, so that's definitely right. I mean, we don't have the data sets to analyze in details what is exactly the part that's happening in the tropics and extratropics that explain this. That could be so. I talked about the low cloud feedback because Norman had something which is quite similar after the hiatus, and it is involving low clouds. But that's true that, first of all, it's not because it's low cloud that low cloud is the initial reason. There is a question of the egg and the chicken, which is starting the change in low cloud, which is starting the change in SST and the ocean circulation, which is starting the change in the deep convection. So all of this is coupled. And then the second point is that Norman identified this in low clouds, but it's true, we don't know about the change in ocean circulation that is associated to this. So my answer would be, yes, of course, there could be some change in ocean circulation, and actually we would have to take all of this into account to see how it ends up in a change in the relative response, which goes through low cloud and SST. Yeah.
Yeah, I think the oceans are really critical. And the hiatus, my mind was, a big mystery. Everybody was trying to figure out why models weren't getting it right. People were looking at aerosols, all kinds of things. But in the end, I think England et al. Showed basically it was wind-driven ocean circulations. You had a slowdown in, I think it was a slowdown in, no, an increase in acceleration of surface winds that were driving the SST pattern, which essentially slowed down the warming. So I think the coupling between the ocean circulation, winds are really critical as well, the SST pattern, clouds, and radiation, it's all really intertwined, and you can't look at one and not the other.
Yeah, yeah, I agree. And especially England, he started the cycle with the winds. The winds are related to the deep convection and to the different series of Niñas, which enter in the PDO. So I agree. Winds, because England looked at the ocean side, so he started with the winds, showing how the winds change the SST pattern. But we know that it is also feedbacking from the atmosphere, because the wind will change the convection, which will change the wind as well. So it's all intertwined, and it's a coupled ocean atmosphere problem. And that's why I think that the approach you used with an energy budget from top to bottom of the climate system, top of the atmosphere, bottom of the ocean, is actually the relevant approach, I think, in the future, to try to understand how this how the relative response is changing with the pattern of SST. We need to have the whole column.
Yeah. So can I ask a question? Is that okay? Sam? Did you? I should be asking him, not you. She has the mic, so she's in control. Did you look at in the model simulations with the AMIPS? Did you look at? I'm not sure if I followed it, and I can't remember if it's in the paper. The difference between those comparisons for AMIP simulations with forcing and AMIP simulations without forcing, in terms of these regressions with.
No, I didn't do that.
You didn't look at that. It'd be interesting to see how different they look. So you included the forcing in these.
Yeah.
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 Try it without forcing and see how.
That's a good idea.
Yeah. Okay.
Yeah.
Next speaker is David Painter. I think he's online.
Yeah, I'm online. Can you hear me okay?
Yeah, we can hear you.
Okay, I'm just going to start my video. Hopefully you can see me as well. And then I will share my screen.
So 20 minutes. No, I don't know how to say 5 minutes, but 20 minutes, your presentation.
Okay, hang on. And let me just make sure I share the right screen. So hopefully, can everybody see that okay?
Yeah.
Does it make sense for me to have my video on or off? Let's just see how that goes. Let's put that there. And hopefully everyone, sorry, 2 seconds.
Leave your video on. People online can see you.
Okay, wonderful. Okay, so everyone can hear me, and hopefully, let me just hide the sharing thing here. And hopefully, can you see the pointer as well?
Yes, I can see your pointer.
Oh, wonderful. Okay, I will begin. So, my name is David Painter. I am from GFDL, and I'm presenting some work which has been done by my former student at GFDL, who's Priya Bragaraman, and he is now a postdoc at UCAR. And he has done some very nice work looking at the spectral kind of side of what we've kind of seen in EEI over the last 20 years. So in particular, we've been kind of looking at this issue kind of connected to that. If you think about from about the last 20 years or so, we're going about 2000 through to 2020, and you think about the Keeling curve, obviously we see a very distinct increase in the amount of CO2 in the atmosphere. And quite interestingly, if you look at the kind of series trend in the long wave over the 2002 going through to about 2018 period, you don't really see a particularly strong corresponding kind of trend in the long wave radiative measurements at the top of atmosphere. So, this is obviously then kind of gives you the idea that maybe it's worth kind of delving a little bit deeper into kind of what makes up this kind of broadband signal and actually look at the spectral side of things. So that's what we've done. And here we've basically been using the University of Michigan's ESRIN spectral data, going from 2003 here through to 2018. And I'm just showing the broadband value of ESRIN here in the dotted lines compared to series, just to kind of show that, we're in quite good agreement in the broadband here, but the benefit of looking at at the ESRIN data in a long wave is obviously it gives you a spectrally resolved look at kind of what we have in terms of the long wave EEI change over the last 2003 through to 2018 period. I should add, that there's been previous kind of attempts to kind of show what climate change looks like spectrally in the long wave, but most of these have kind of used, for example, some of these old studies by John Harris have kind of used kind of reasonably kind of sparsely differentiated satellite data sets, which kind of means it's been a little bit difficult to kind of know, kind of going back to Greg's talk earlier, it's kind of difficult to know whether you're actually seeing something which is kind of a true signal, whether it's just kind of difference in calibration between two different satellite instruments. However, recently, I think some groups have started also to do kind of similar work to what we've done here. Florian Roma here just published a paper about a month ago or so, kind of looking at similar work that we've done with ESRIN, but looking at the IRZ instrument. So I also would recommend looking at that paper if you're interested in kind of the spectral signal. So what have we done? What products are we looking at here? So in this talk, I'm just going to kind of present kind of three main products. First one is basically just this ESRIN process spectral data. So this is obviously top of atmosphere radiance that's been converted to flux. And this covers the 1 to 2000 inverse centimeter spectral range. Just a few caveats here. Actually, ESRIN doesn't actually quite measure that whole range. So outside of the main areas which are measured by ESRIN, which is around about 560 wave number through to about 2200, sorry, to 2000, that's kind of estimated using this kind of offline radio transfer code. But most of what we kind of see for ESRIN is actually directly kind of what is measured. So what we've basically tried to do is to try and run a global scale line-by-line radiation code using input from ERA-5 to see if we can reproduce what we kind of observe from the top of atmospheres from the measurement of ESRIN. So this is kind of comparing, in essence, our kind of best state-of-the-art theoretical estimates of what we would imagine the top of atmosphere fluxes should look like compared to kind of what we're measuring. And obviously the two are not completely independent. Obviously some of the information that goes into ERA actually probably comes from ESRIN, but these are reasonably kind of independent kind of estimates. And then thirdly, I'm not going to cover these in so much detail just because of the amount of time I have to talk, but we've also done these kind of what I call idealized line-by-line calculations, where rather than using a large amount of data, for example, basically feeding your line-by-line radiation code with all of this data from ERA-5, we're just basically taking standard runs done by climate models, and then we're just scaling them to the present day to kind of show kind of how well the kind of physics of the climate models can kind of capture the kind of spectral signatures that we're seeing in the ESRIN data. Okay, so for those of you not familiar with line-by-line calculations, in general, when you think about what's done in most radiation codes, if in, for example, general circulation models, we use what's called broadband codes, and these, in essence, make radiation transfer much more simpler by integrating the spectral details over very kind of broad spectral ranges. What you do in a line-by-line code is you try and take things far more from kind of first fundamental principles, and you basically calculate the spectra, knowing the molecular line information from every single line of that particular gas. So, for example, here in the purple, I'm showing water vapor. I'm showing CO2 here in the green, and other gases which are important in a long wave are also shown. So, like ozone is in the blue, and then methane and N2O as well. And obviously, what will strike you about this figure is it's pretty complex. So, there's a lot of spectral features you're trying to resolve. So basically what we have to do these line-by-line calculations, so every layer in the atmosphere, we have to basically resolve the spectral data. So we have to calculate the spectra for each gas, we have to sum them together, and then we have to run a radiation solver, at pretty high resolution in order to kind of capture all these kind of key spectral features. So line-by-line calculations are generally considered like the benchmark of radiation transfer calculations. The downside is they're pretty computationally heavy to run, which is why they're not used in GCMs. In order to do this data, for example, when we do the ERA-5 calculations, we're basically using offline, basically doing kind of monthly mean data, which you kind of feed into this line-by-line calculation. But unlike previous calculations, we also include the impact of clouds. So we're really trying to match very closely with this kind of very high fidelity spectral calculation exactly what the atmosphere is kind of looking like for the measurements. So how much confidence can we kind of have in these results? So if we kind of then distill everything down, so, you know, we've done these line by line calculations for every month at every grid point. But here I'm basically just showing you the kind of complete value of the kind of global mean climatology top of atmosphere OLR. And in the black is what is measured by ESRIN. So we kind of, this is observations. As I say, you know, below 500 centimeter here, this is actually kind of inferred from values in other channels. But you can basically see we have pretty good agreement between our kind of line by line observations driven by the ERA5 data, and then what we're observing. And then secondly, we also have this idealized calculation. So this is basically what the GCM is predicting, but it hasn't actually been given any information about the introduced state of the atmosphere. This is just basically using an 1850 climatological run of the GCM and it's running that through our calculation. It's in general some pretty good agreement. We don't include any clouds in these calculations. So you see actually there's a bit of a disagreement in the window region here, and that's actually because of the absence of clouds. And here along the bottom, I just for reference for you, you're not aware of kind of the details of the spectra. I'm just kind of listing the main gases which are kind of controlling these spectral features here. And then obviously the key one to keep an eye on is CO2, which is this kind of it's almost like a bite out of the Planck curve here, around about 660 wave number, and this is the water vapor rotational band on the left here, and then other kind of smaller greenhouse gas changes in the CH4 and N2O are shown here on the right. So what we're more interested in here, rather than thinking about the climatology, are the trends. So how have things been changing over the 2003 to 2018 period? And this is pretty kind of a neat result that we have here. Is firstly you can kind of see in the ESRIN calculations, you can see a distinct kind of dips and the black lines here in the CO2 window, in the side of the CO2 bands here over the last kind of 20 years, and then also an increase if in the window region here. And you can see overall that we have a pretty good ability of our line-by-line calculation driven by the ERA5 data to kind of capture these trends in most of these spectral kind of regions, which really kind of gives us confidence in kind of our ability to being able to kind of model the changes in the long wave spectra over this time period. There is obviously one quite key exception you can see here, which we're still investigating. You can see it's kind of big dip in our line-by-line calculations around where ozone is. And we're just not really kind of seeing that in the observations at all. So that's still a little bit of a mystery to kind of understand why that is. We have a suspicion there might be an issue with the actual data we're feeding into our calculations from ERA5, but we haven't quite got to the bottom of that yet. And the other thing, so the trends here shown in the green, I'm going to come back to this a little bit later, but in essence, you can see that we're also with our idealized calculations. So for these, you basically give the line by line very little information about what has occurred over the last over the 2003 to 2018 period. We've only basically told it the changes in the amount of greenhouse gases and then some estimate of the feedback parameter to calculate the kind of response to surface temperature changes. And you're actually with that, you're able to kind of capture things pretty clearly as well. Okay, so the next thing we're kind of done, and this is obviously the benefit of having a kind of model rather than just showing observations of the totality of both the forcing and the feedbacks. And the previous speaker did a very excellent job for me of kind of giving a summary of the forcing kind of feedback framework. So what we can obviously do with the line-by-line calculations is we can attempt to kind of break things down into understanding how much of these differences are due to forcing, i.e. the changes in the greenhouse gases, and how much of those are kind of due to feedbacks. And so, typically when you think about the way forcing and feedbacks are brought about in the IPCC report, you have this thing called ERF, which is effective radiation forcing. And this is basically a sum of two things. It's your instantaneous radiation forcing. So that's just a change brought about instantaneously from increasing your greenhouse gases. And then also some adjustment term, which occurs in response to those greenhouse gases before you get any warming. And the most kind of canonical one that people know about here is the fact that the stratosphere should cool in response to CO2 increases. There are other adjustments which can occur as well in terms of clouds, but those more generally affect the short wave. And obviously here we're just thinking about the breakdown of this budget in the long wave. And then finally, as the previous speaker said, you have the feedback parameter here, the lambda. And then this is, the first order kind of governed by delta, by the kind of warming or also unforced variability here, because we're just multiplying this by the total trend of the surface temperature. So that's the kind of effort here, is to try and break down and understand the kind of what is kind of causing these trends of OLR, how much of that is brought about by this kind of forcing, and how much of this is brought about by the kind of feedbacks. So how do we do this? Well, this is just kind of showing you for these data sets I mentioned before, kind of how we break these down. So for airs, obviously, we just have OLR, we just have the term on the left here. For our ERA line by line, what we've basically done is, for our runs I showed you previously, we're changing everything. So we're trying to match this OLR trend. But also we can do a more simple run where we just change the greenhouse gases. And that allows us to get at this IRF. So this is just giving us the kind of effect of the forcing. And then we do a separate run where we, so in this run we keep everything else fixed. And then we do another run where basically we keep the greenhouse gases fixed, and we just change the cloud temperature and water vapor. And this then gives us an estimate of this adjustment term and the impact of the feedbacks as well. And then finally, with the line-by-line idealized calculations, I don't want to go into too much detail here because I'm probably going to run out of time. But in essence, we take 3 kind of canonical runs which have been done to kind of understand climate change, and then we've scaled them to the present day. So we've taken an 1850 pi control, and then we're basically just in the line-by-line, we've taken that state, fed it into the line-by-line code, and then we've just changed the values of the greenhouse gases in that code from 2003 to 2018 to get an estimate of IRF. We've taken a run where CO2 has been increased, a fixed SST run of a climate model. And then this gets us the cooling in the stratosphere. So we've then taken that cooling in the stratosphere from a 4x CO2 run, scaled it to present day values of CO2 change to give us an estimate of this adjustment term, and in particular the stratospheric cooling. And then finally, we take this kind of canonical run where we increase CO2 by 1% per year, and we've taken the warming state from that, and then we've scaled that. We've basically used that to estimate a feedback parameter lambda here, and then we've scaled that by the present day trends of temperature. So the idea here is to basically say, with pretty minimal information, how accurately do these kind of key ideas of climate change estimated by climate models, how accurately can they estimate the spectral changes or spectral trends that we've been seeing over the last 20 years? So, going back to the original slide here, so this is just showing you the total OLR trend for all of these products here. So probably comes as no surprise if we then look at our ERA line-by-line calculations, and when we look at the IRF contributions, this is the contribution from the changes just in greenhouse gas, you can really nicely show that basically most of this kind of dip in the CO2 tropospheric kind of bands here, kind of at the edge, are due to the IRF, the increase of the gases. Likewise, you can also see here, that the fact you get this kind of dip here is in the where you get absorption by CH4 and N2O is largely brought about by the instantaneous radiation forcing as well. And you can also see this slightly bizarre thing that we're not matching well with observations is kind of also in the O3 band is also due to the change of ozone which is occurring. And likewise, if you look at the adjustment term, so this is both the stratospheric cooling and also the surface temperature change, you can now see that this, the kind of increase in the window region can basically be explained by the change in the feedback parameter and the adjustment term as well. So really quickly, if we then look at this in our idealized case, which then allows us to then break down, see previously here, see the adjustment term is both the stratospheric temperature change and also the surface warming change. For this, we now break down things into the warming change and also then separately the stratospheric change. You can see some pretty nice results. So for example, we can know in the center of the CO2 band where CO2 emits in the stratosphere, you actually see the fact you get very little trend in the middle of that band is due to the fact you get compensation between the fact that the rate of forcing there is actually negative because you get more emission, cancelled out by the fact you get cooling in the stratosphere occurring in that region. And then likewise, you can also see that our idealized calculations basically match very closely what we get from giving us all the information from ERA as well, which kind of gives us confidence that what we're seeing in terms of the spectral changes in airs can be explained by our kind of conical understanding of kind of climate change. So that's my kind of claim here, is that if you kind of look at then the spectral changes in airs, you basically see 4 key features that are associated with you'd expect to be associated with a changing climate, and they are clearly there. So, you know, the first one being the fact we have very little change in rotational band. I haven't really had time to explain this. This comes from an idea called Simpson's law. Secondly, obviously, increase of greenhouse gases causes excessive trapping and a decreasing trend in the CO2 region and also in the N2O and CH4 spectral regions. And then a warming planet, as you would expect, has increased emission through the atmospheric windows, shown by the point 3 here. And finally, I just want to show one kind of thing. I've mentioned we've done these global scale line-by-line calculations, and the whole time I've been kind of showing you global means. But I think what's really neat is when you look at these just as a zonal mean. So this is the zonal mean trend in airs, and this is basically, if it's red here, it means we're seeing more trapping of radiation. So we're seeing much more trapping of radiation across the whole CO2 band here. This is a wave number on the x-axis here. And then you also see, for example, at the high latitudes, you kind of see this blue value increases. This is more radiation being lost to space associated with warming. And obviously, the fact this is more blue up here is the hallmark of polar amplification. In fact, we know we've got more warming in the poles, means you see more energy lost to space up here at the high latitudes compared to in the tropics, where you seem to be dominated by a shift, for example, here in the ITCC. But what's really cool is you can see how accurately our line-by-line calculations can estimate these changes when we feed them with the ERA. I mean, it's not perfect, certainly not for the O3 band here, but you know, the main spectral signatures and the observations we can model pretty accurately. And then likewise, you know, showing that previous breakdown, we can then break this down into the impact of the greenhouse gas changes. Here, you know, obviously the red, the increased trapping, apart from in the center of the stratospheric emission of CO2. And then, of course, in the warming term and the term brought about by stratospheric cooling, you can also see here on the right. So you have to see that all of this blue here is due to the warming term. Okay. So one final idea I just want to advocate, you know, is we have this idea of the kind of Keeling curve, obviously, for observations now, if observing amounts of CO2. But, you know, what's also interesting, of course, and this really is an advertisement for long-term observations, is when you look at the kind of, you know, the 710 to 720 spectral range of CO2, or you look at where the emission occurs of CH4 and N2O, you can also see something like a very strong negative trend associated with increased trapping. So this is how we really show true evidence, I think, of climate change occurring, and really kind of strong evidence that we can, you know, communicate to the public as well, that we are seeing this happening, you know, in real time through observations. Okay, so I don't know how I'm doing for time, so I forgot to mark what time I started. But, you know, here are my conclusions. You know, basically, you know, the air spectra shows these kind of key aspects of climate change. We see this decreasing trends in the tropospheric bands of CO2, CH4, and N2O. We see increasing emission in the stratospheric window, and then we see a weak trend in the center of the stratospheric, the atmospheric window, I said previously, and then we see a weak trend in the stratospheric CO2 band associated with the cancellation between the increased rate of forcing and the cooling of the stratosphere. Our state-of-the-art line-by-line calculations can pretty well accurately calculate these. And then, you know, breaking down the ERA results, you know, into these different terms, basically kind of highlight the causes of these things above. And then finally, I just want to say now our kind of idealized line-by-line calculations are very accurately able to kind of capture these changes as well, which gives us good confidence, I think, in the physics within our climate models. So if there, I will stop and take any questions.
Thank you, David. Any questions? If not, I have one question. You show that the increasing emission from water vapor.
Oh yes, let me go back to that slide. Hang on. Sorry.
and is that maybe due to increasing temperature outweigh than increasing water vapor?
So yeah, so that change is quite interesting. So we're pretty sure that some of that change is unforced, is variability. You know, El Niños and La Niñas can cause you to get kind of trends that aren't due to aren't necessarily due to long-term climate change, but you can also kind of show that as you get a climate which is warming, that your pressure broadening of the water vapor lines changes ever so slightly. And because that pressure changes, you can basically show that should lead to an increase of emission. So that's actually, and you kind of see our green line there, which is our kind of estimate from our climate model, which has no information about the present day atmospheric state, manages to capture that pretty clearly. So I think it's actually kind of fairly fundamental physics which is occurring there, rather than necessarily an indication of a change of temperature per se.
And if water vapor increases, the amount of water vapor increases, the emission temperature get lower, right? So
yes,
yeah, yeah, okay. Just make clarification. Any questions? Any other questions? Okay. Well, thank you, David.
Yeah, thank you, everybody.
Thank you. And
I'll just stop. I'll get back and I will stop sharing.
right.
There we go.
And next talk is by Brian Soden. Brian, are you there? Yes.
AG, I think it's me who's next.
Peter, I think Peter's talk was moved. No. Oh, came back. Oh, okay. Peter, are you there?
Yeah, can you hear me?
Yeah, well, I'm sorry that early, yeah, Peter, yeah, early in the morning, but yeah. Okay, so your talk title is the reconciling and improving of formulation for thermodynamics and the conservation of principles in Earth system modeling. Go ahead, Peter, to share your screen.
Yeah, I'm getting a complaint that WebEx doesn't have the, just a sec here, apologies.
Well, if you're using a Mac, you have to go to Preference, you have to authorize the screen, and you have to log out WebEx and come back in.
Okay, I also sent my slides yesterday. I wonder if that's easier, if you can share the slides from your computer.
Lorenza? Yeah.
Okay, I guess we have it.
Lorenza's working on it.
Okay, I think that's quicker than me logging in and out and
Just
changing my settings.
Here it is. We have your slides, Peter. So if you want, we can just. I can pass the slide if you just say next slide.
Thank you.
Okay, let me know. You are the first slide now.
Oh, I can't.
I have to share that? Yeah.
Yeah.
Hold on. Share. Okay. Okay, can you see the slides?
Yeah. Alrighty, thank you. Apologies for the technical difficulties here. My name is Peter Lauritsen. I work at the National Center for Atmospheric Research. Unfortunately, I couldn't be there in person to interact with all of you. So thanks to the organizers for letting me speak remotely. The price to pay is that I've been up since 3 a.m. this morning. I'm sure a lot of you there are jet lagged as well. My co-author here is Romain Rorik from Météo France. If you can go to the next slide. Both Romain and I are climate model developers. So we would like to provide a perspective from that side. So what we're interested in is, how well do we represent energy budgets in our climate models, which ultimately can affect how well we simulate Earth's energy imbalance. What I'm going to talk about today is rather technical. If you're interested in the details, please see this paper here. It came out of a beers workshop in Banff right before COVID hit. It ended up being a rather long paper. It's 83 pages, but it goes through all the glory details and some of the stuff I'm going to touch upon today. Please go to the next slide. So from a climate model developer's perspective, we obviously want to, from first principles, derive what the energy equations for the atmosphere should look like. And in order to keep that problem tractable, we need to do a series of some assumptions. This is the first round of assumptions. So we assume the primitive equations. So here we just assume hydrostatic balance, shallow atmosphere, ideal gas. For the equations I'm showing here, we're assuming that the model top pressure is constant. You can use whatever you want, but that's what's assumed here, which all pressure-based coordinate models will assume. We also assume what is very common in large-scale models, namely that all components of moist air have the same temperature and they all move with the same velocity components. And then in order to make the equations shorter here, I'm also assuming that water entering the atmosphere, for example, through evaporation, has the same temperature as water leaving the atmosphere, such as various forms of precipitation. This is not necessary, but it's just to make the formulas a bit more compact. So if you make all of those assumptions, then you can show that the globally integrated energy equation is the equation shown here. It took 94 equations to get there in the paper. Unfortunately, I can't point here, but if you look at the first term in the integrand here, the K, that's the kinetic energy term. Then we have phi S, surface geopotential. And then we have an enthalpy term, that's the temperature multiplied by the specific heat. So that first term here, that's for dry air. And then you see the exact same thing repeated in the sum, which sums over all components of water in the atmosphere. So that's water vapor and whatever condensates you have in the system. Since water can phase change, there are some additional terms appearing here. So the T00800, that's referred to the enthalpy reference state, which is that of ice in these equations. And when you make that assumption, then your latent heat terms, which is the line 2 there, appear, which is the latent heat of sublimation and fusion multiplied by water vapor and liquid, respectively. So the global integral of that, like over the entire 3D atmospheres, the time change of that is equal to the right-hand side here, which is the flux terms. So the sum you see on the right-hand side is a repetition of the terms that you see on the integral on the left-hand side, but now instead of the mixing ratios, we have the flux. So the F sign here is the flux into the atmosphere of water component L. So it's multiplied by kinetic energy at the surface, the phi S term, and then we have our enthalpy term. So I'm going to refer to this F times Cp times the surface temperature as the enthalpy flux term. And here we have to specify a temperature at which water leaves and enters the atmosphere. And I mentioned that for the sake of simplicity, we're just assuming that's the same temperature, although that's not very particularly accurate. Then you have a repetition of the latent heat terms, and then you have the sensible heat flux. And again, for notational simplicity, I've just put radiation into this F term, although it actually should have been on the left-hand side, but that's not important for the discussion here. So that's the continuous equations of motion. What we usually do, if you go to the next slide, is we put bars over all the terms here. So we just assume that this equation here holds for the grid cell mean values. And again, that's a questionable assumption, but that's what most models do. Then we go to the next slide. I'll now be showing the second round of approximations that's usually done in large-scale models. So first of all, in the sum of all the water components, usually only water vapor is included. So that means that condensates do not carry any kinetic energy or enthalpy in these equations. Large-scale models also usually assume that the constant latent heat, so that's an equivalent to assuming that all the heat capacities are just that of dry air. And then usually, at least to my knowledge, no model really includes any of those flux terms on the right-hand side, in particular the enthalpy flux terms. So you only have the latent heat terms on the right-hand side plus the sensible heat flux. Next slide. So in the modeling system I'm working in, so that's NCAR's community atmosphere model. The equation I'm showing here is valid for each physics column on the physical parameterization side as we step through our parameterizations, if we assume that pressure is constant. The most models assume that when you run one parameterization, you update the state, you run another parameterization, update the state. To my knowledge, most models will just assume the total water, or in a hydrostatic model is equivalent to saying pressure is just constant throughout that. If you go to the next slide, we obviously know that water does leave and enter the columns. At the very end of physics, in the case of CAM, we update the pressure and the total water to reflect that water has entered or left the column. And the energy tendency associated with that is shown on in the plot on the lower left corner here. This is a 1-year average of a 1-degree simulation using CAM6. And the global mean imbalance associated with updating water in the column is 0.35 watts per meter squared, so a rather large term. And then regionally, you see it's much larger. So in the evaporation zones, such as off the coast of South America, you see it's like 20 watts per meter squared or so. And then in heavy precipitation zones, like minus 30 watts per meter squared or so. So in a global model, we use energy fixers to artificially close our energy budget. So this spurious tendency associated with updating water in the system is compensated for by uniform temperature increment every physics time step. The dynamical core does not conserve energy either, and there can be errors in physics dynamics coupling as well. And this is also fixed with an energy fixer in the model, again with a uniform temperature increment. Next slide, please. So as I mentioned earlier, what's underlined with the red red line here, those are the terms that are usually neglected in climate models. If we were to diagnose what those terms look like, you get plot B in the middle here, and that plot is dominated by the enthalpy flux terms. Let's just focus on that. So you see that plot A here is energy tendency associated with updating water in the column. It's at least by an eyeball known pretty much the same as the plot B, the enthalpy flux term. So if we were to include this enthalpy flux in our models, then we would close our energy budgets much better. And that's what's shown in plot C, which is basically the difference between plots A and B. So now you see that, for example, off the coast of South America in the heavy evaporation zones, where our imbalance was about 20 watts per meter squared, it's now been locally reduced to about less than 1 watts per meter squared. And similarly for heavy precipitation zones, we go from minus 30 watts per meter squared to a couple of watts per meter squared. So at least locally, that would really improve our representation of the energy budget, so that the energy fixer has to do less work. Next slide, please. You can just skip to the next one. I'm not going to go through this in the interest of time, since you're probably all hungry. So it's a basic message here from the climate modeling or climate modeler community is that most global models do not rigorously account for processes associated with falling precipitation and evaporation in terms of the energetics associated with them. And if you want to take away one message from this talk, I really want to hammer in that, if we were to include the enthalpy flux term in our system, we would massively, improve our representation of local energy budgets. There's lots of other stuff going on related to falling precipitation that we're not rigorously representing in terms of energetics in the model. These are processes such as the frictional heating associated with falling representation, which you actually can rigorously include if you're in your model, at least from a theoretical perspective. There's also processes such as horizontal drag from falling precipitation, etc. So all of this stuff is discussed quite extensively in this lengthy paper on slide 2 if you're interested. Another side effect of being rigorous in terms of monitoring energy conservation in our models is that it really forces us to be much more rigorous regarding thermodynamic and thereby also energetic consistency in our models. And actually, while we were writing this paper, it became apparent that there was an inconsistency between the turbulence scheme that we're using in CAM6, that's called CLUB, and the host model CAM. Those two actually conserve different energies. And again, we're using fixers to correct for this inconsistency. It would be preferable to actually have consistent thermodynamics across parameterizations. And again, when I don't have the plot here, but if you look at the column by column imbalances, they're really quite large compared to our global imbalance in our Earth system. And then last but not least, if we want to include these enthalpy fluxes in our model, which obviously we're putting them into a coupled system, so we need to be consistent across climate model components. So here at NCAR, we've integrated GFDL's MOM6 ocean model that has a representation of these enthalpy fluxes. However, for the atmosphere to match these fluxes, the atmosphere model must move to variable latent heats, which most global models I'm aware of do not. Next slide. So in the development of the community Earth system model, the CESM, of which CAM is the atmospheric component, we're getting ready for the next round of CMIP. So we're in really intense model development phase. And one effort I'm working on is to include this enthalpy flux in the system, which is a rather complicated, long journey of getting there. We're unfortunately not there yet, but we are getting closer. So we've already changed the dynamical core. In this case, it's the spectral element dynamical core to use variable latent heats. That was done a while ago. Just recently, we changed the CAM physics package to include all condensates and pressure, so that's done. I've changed CAM physics to use variable latent heats. It's not a completely rigorous way of doing it. I won't go into the details here in the interest of time. So there's kind of 2 steps in this. I've done with step 1. I'm working on step 2 of that. And then finally, when that's done, then we're ready to pass enthalpy fluxes to the components to which CAM is coupled. Coupling with MOM6, at least from a theoretical perspective, is pretty straightforward because now the enthalpy fluxes will match across components. However, coupling to the land or ice components is a little bit less obvious, so we might have to resort to using energy fixers for that. Last slide, please. So there's really, what I just talked about, there's not too much discussion of that, in my opinion, in the global modeling community. So both Romain and I are serving on the WCNI, the Working Group of Numerical Experimentation under the WCRP. We've kind of been discussing how to engage the global modeling community to actually focus more on these kinds of errors and then diagnose them so we're aware of how large they are. So we thought that the best way to start such a project, it's very, very technical and it's not easy to put these diagnostics into models, is to send out a questionnaire or a survey, if you will, to the CMIP modeling groups and beyond, asking just questions like, do you conserve mass? What is your energy dissipation in the dicore? Have you diagnosed what your errors in physics are? Have you looked at thermodynamic consistency in your system, et cetera, et cetera. So if anybody here is interested, you can click on this link here and see what's in this survey. And we really hope that the modeling groups will participate, and some of them have already responded to us. Next slide, please. So since I'm not here in person, please feel free to email me at pel.ucar.edu if you have any questions. And then once I get the enthalpy fluxes in the system, I really like to work more with the observational community to kind of assess how well we're doing. Since again, there are a lot of stuff in the details in representing enthalpy fluxes and other errors associated with falling precipitation in the atmosphere. So with that, I'll take questions. Thanks for driving this slideshow.
I have a short question. Yeah, I have a short question, Peter. Bernard speaking. I was just wondering, you showed the mean and the regional variability of the error that we can expect from those approximations. I was wondering, have you looked into simulations a long time, like, I don't know, historical simulations or the abrupt increase in CO2 simulations? And does it change with time, this errors in the energy budget?
So I haven't looked at it specifically, but I can definitely guess what would happen. So if your precipitation patterns and evaporation patterns do change, now you directly impact this flux. So I'm pretty sure there will be a variability on long time scales. Also, there's also big seasonal variabilities in this term as well. But it is, I don't know how much it varies, but
so you suspect it would scale?
No matter when you look at it, it's going to be a large term.
Yeah.
But yeah, it would vary for sure.
Hi, Peter. Thank you. This is Seiji Kato. The question is that when you include the enthalpy flux, you still assume that the precipitation and water vapor leaving and entering atmosphere at the same temperature, air temperature, right?
Mm-hmm.
But the question, the question is what temperature of the precipitation has when leaving the atmosphere. Sometimes people assume that the wet bulb temperature and so on and so forth. But the first thing, I guess, that including the enthalpy flux in the model is probably important.
Yeah, that's a very good point. Like you get a lot of the signal just by choosing the temperature of the lowest level in the model, but you're right, that's definitely not correct. So once we have it in there, then we can start playing around with using other temperatures, such as the wet bulb temperature, which can be like 4 or 5 degrees off what the atmospheric temperature is. And similarly for the evaporation, I think we're going to use just the SST value instead of the lowest model level temperature. So there's a lot of devil in the details here of getting these fluxes right. But just getting it in there will get us a long way there, in my opinion.
Thank you.
No other questions? Okay. I think we should break now. Thank you, Peter.
Yeah, I guess we're gonna break now.
Yeah, we're about 1 hour and 10 minutes late. So
before cafeteria close, yeah.
Let's rob 15 minutes on the lunch break. You're lucky because now there's not much queue, but there's less choice of food. Then we'll rob 5 minutes on the coffee break in the afternoon, and we'll rob some time on the icebreaker cocktail. So let's get back at 15 minutes after the hour. So you have 45 minutes for lunch.
Oh, yeah.
Thank you. Thank you for the people online. So 15 minutes after the hour, we start sharp.
Brian?
There are 4 cameras in the room. So if somebody steals something, we'll see it. And we might even lock the doors. So yes, please leave everything.
William, your talk will start the second talk in the afternoon. So, right, the second talk in the afternoon, what time is it?
Brian Soden will speak at 14:15 Central European summertime.
Brian is not here. Brian not here. I don't think it. William is here.
Yes, I am.
William, can you hear us?
Yes, I can.
Will you be able to connect at when we catch up the session? Because maybe you will be the first talk, or maybe the second one.
Let me your time. Well, 5. So start from 220. That's
Okay, can you see my screen?
Yeah.
Is it okay? Is it full
Yes.
screen?
Yes.
Okay, good, excellent. So let me know when can when can
Okay.
I start?
Okay. All right. A few more. I think it's, yeah, almost. Hold on. Okay, good afternoon, and we continue this session's science questions associated with the EI. And the next talk will be by William Lovell, and the title is On How Deep Argo Can Help Close the Sea Level Budget. With that, go ahead, William.
Okay, thank you for introducing me. So I'm very pleased today to present some status of deep Argo. And first and after, in the second part, I will present some recent results on deep ocean temperature changes, but also on deep steric changes from deep Argo and different approaches. So I would like to first acknowledge my co-author. And I've had so Antoine Aucher. Antoine helped me in this talk to investigate the deep ocean steric changes from a numerical model. Antoine is the new postdoc funded by ESA at LOPS in my lab. So let's start with the observing system, the in-situ ocean observing system, the current status. For several decades now, we have access to different platforms, mainly from ship-based observation with a CTD cast to record temperature and salinity from the surface to a different depths on the ocean. We have also mooring and expandable bathythermograph, and the last one record only mainly only temperature for the upper ocean, let's say 700-meter depths. On the bottom right, we can see the data, the number of casts as a function of year. And we can see that before 2000, they are based on ship-based observation. And after 2000, we have a rise of number of profile. And actually, this coincides with the rise of autonomous platform, mainly from Argo float that we've discussed already this morning. But this is not only the platform we have. We also have glider and CTD attached to marine mammal. In terms of data coverage, on the bottom right, we can see that over the 3-degree by 3-degree boxes, the percentage of data coverage are getting better and better for the upper 1,000-meter depths after the year 2005. And this is mainly because of the Argo float. But below 2,000-meter depths, we still have a lack of in-situ data, and the deep ocean remain mostly unmeasured. So for the upper ocean measurement, so since the beginning of the 2000, we have now access to the Argo network. Now we have a global distribution of almost 4,000 operational float. The map on the left, top left, show that as of August 2022, we can see that we have kind of good coverage, especially for the open ocean. but some regions are still not well sampled. For instance, the maritime continent region or the sea ice covered regions such as the Arctic. So Argo provides the global subsurface ocean temperature for the surface to 2000 meter depths. So a cycle of Argo is basically 10 days. The float go to the parking depths, which should be at 1 kilometer, and drift for 9 days. And at the last day of the cycle, the float descends to 2000 meter depths and go back to the surface by sampling temperature and salinity, and after send those data by satellite. So those float in a real-time profile has an accuracy of 0.01 for salinity, 2 millidegrees Celsius for temperature, and 2.4 decibel. And one of the main results we have known for those data that the upper ocean is warming for several years now. And Dean Romick and Sven Wischfeld published this result a few years ago. And they show that there is a consistent global ocean warming trend from the surface to 2000 meter depth for the last decades. So thanks to this data, we can constrain the ocean heat changes and increase for the 2000 meter depth. Regarding the deep ocean, people have attempted to estimate the decadal deep changes. And this is a very famous work by Sarah Purkey and Greg Johnson in 2010. They showed that there is a deep decadal sea level change and deep decadal ocean warming as well over the period 1980 to 2010. And they found that the Southern Ocean, especially the deep abyssal ocean, are warming, and there the sea level, the deep ocean sea level are rising. So this study relies on ship-based ocean data from CTD casts over the worst ghost ship section, and the name are on the left of the slide. But we can see that this estimate relies on sparse data as well as in space, but also in time. We can see that if we consider like the section A05, for instance, we only have 5 repeat of time for the 3 decades. So the author estimate these deep ocean changes in terms of sea level and ocean warming as well with few data. So we can ask if those deep changes are consistent and coherent, or do they have any bias? For instance, seasonal bias, because we know that the oceanographic campaign take place usually during the summer. So because of the lack of data and the lack of our knowledge of deep ocean changes, people have thought about extending the Argo program to the deep, below 2000 meter depths, and they call it Deep Argo program. So here is the status of this program. So we have floats that can reach depth below 2000 meter depths. We have 2 kinds of floats, some reaching 4000 meter depths, like for the French one, the French Arvor, and the US float, for instance, can reach 6000 meter depths. So the principles are quite simple and quite similar than the Argo floats. For the deep solo, for the deep the US float, the float are reaching the parking depths, which is basically 6000 meter depths, drift for 10 or 15 days, and after go back to the surface and sample temperature and salinity. For the French float, the Deep Arvor, actually the parking depths can be different, and but there is a recommendation to keep the parking depth at 1000 meter depths to be consistent with the core Argo and have a better estimate of the ocean circulation at 1 kilometer depth. So on the right, we can see a map of active deep Argo floats. and the color represent the float from the country. And now we have 181 active float as of March 2023. We can see that the deep harbor going to 4,000 meter depths are mainly deployed in North Atlantic, and the deep solo float from US deployed in the Pacific and also in the Atlantic Ocean. So the accuracy, the target accuracy measurement are 0.002 for salinity, 0.001 for temperature, but for the solo float. For the deep harbor, it's more or less than 0.002 degrees C, and for the pressure, it's 3 decibars. So those plots should help us to reduce error in decadal trends in ocean heat content, for instance, from 0.04 watt by meter square by decades to 0.0036 watt by meter square by decades. And in terms of sea level, they should help us to reduce the uncertainty from 7 millimeter per decade to 0.1 millimeter per decade. So now we have 15% of the data coverage target but been reached. But actually, the Deep Argo program, the target is to have 1,200 floats covering the entire oceans. So I would like to share you some science highlights on the deep ocean warming that have been done by Greg Johnson and his team. So he has published 3 different papers with quite of the same conclusion, that he has found a deep ocean warming in the Brazilian basin, in the deep Brazilian basin, deep Argentine basin, and Southwest Pacific Ocean. So basically, they have compared like a 2-year of deep Argo measurement with a historical hydrographic measurement that took place in 1980 and 1990. And they made differences, and they found that below 4,000 meter depths, they found a deep ocean warming for the Brazilian and Argentine basins, and warming deeper, let's say that's 5,000 meter depth for the Southwest Pacific Ocean. So the objectives of the Deep Argo program is to extend the temperature and salinity profile for the subsurface to the bottom of the ocean, to extend also the parameter measured with the oxygen measurements to investigate the pH changes and the oxygen minimum zone variability. Because the float are reaching almost the sea floor, there's a collaboration to improve our knowledge in a deep ocean bathymetry. So the people working on a Deep Argo are also collaborating with GEPCO to enhance the bathymetry maps. And there are also possible development for ocean mixing and optical scattering. And the target, of course, is to have 1,200 floats for the deep global coverage to go to the One Argo program and having 4,000 float from the surface to the bottom of the ocean. Okay, so now I would like to switch to estimating the deep ocean change. Deep ocean change, as I told you, rely on too few measurements. So another way to overcome that is to use the sea level budget approach, and basically what we call the geodetic project, when we correct the altimetry by the GRACE data, and we call also this geodetic steric sea level with the Argo-based steric change.
William,
Yes.
William, we cannot hear you in the room. We have a audio problem.
I don't have any problem. Can you hear me?
Yes, I can hear you because I'm also online, but we don't hear you in the loudspeaker in the room. So please wait a few seconds.
Okay, I will.
Wait.
Let me know when I can resume.
Il y a plus de son? Pasquale?
All right, we can hear you.
I asked William to halt, and Lorenza ran to see if somebody pulled the plug or what. We don't have noise. But when you speak in the loudspeaker, does it work? speak.
Hello?
Hello?
Yeah.
Can you hear? William, hold on. We have a technical problem.
Yes, yeah.
Looks like. Yes. Okay. Help is coming. Okay.
It's the computer.
I stopped the clock, by the way.
William, speak.
Yes, can you hear me? Is it better now?
Okay, go.
Okay, can I resume?
Go ahead. It's like 3 more minutes.
Okay. So to finish this talk, I would like to infer the deep ocean change from the silver budget approach. And the map showed the deep steric trend over 2005-2015 based on satellite altimetry minus GRACE minus upper ocean steric trend from Argo float. So we can see that there is a large regional variability, and with back to the envelope calculation, we can change those steric trend into temperature trends, and so we expect a trend range from 2 to 10 milli-degree C per year. So the deep Argo accuracy, which basically 1 to 2 millimeter degree C, should help us to see if those trends are realistic or not. Okay, so I will jump to the last slide then, if you don't have time. So to validate the deep ocean change from geologic product, we compare that to the real deep Argo. So here's two examples. In the North Atlantic Ocean, we have a float, off the Portugal coast. We compare that in terms of deep steric change from 2000 to the bottom of the ocean. And actually, we can see like very good agreement between the blue curve, the geodetic product, and the red curve, which is the deep steric change based on the Argo float. We found the same result in Australian Antarctic basins. And because thanks to the Argo float, we have access to temperature and salinity. On the bottom, I've partitioned the contribution for the temperature and salinity changes. And for instance, for the North Atlantic Ocean, we can see that the variability that we have found with the deep Argo float are mainly temperature origin. So we can go a step further by separating which can be due to thermosteric and allosteric. But actually, I'm quite happy because the comparisons are quite good for the North Atlantic Ocean. And we have made some other comparison with the float from Nathalie Zilberman with the deep Solo. And here was an example north of the Caribbean region with the float 6021. And we found that the deep steric changes are quite the same amplitude that the deep steric from the geodetic approach. And for this float, we can see that there is a compensation between temperature and the salinity contribution for the steric changes. So as a conclusion, Deep Argo is an ongoing expansion of the Argo program, and that will help us to increase ocean sampling from the surface to the seafloor. Deep Argo has the ability to improve estimate of deep ocean heat content, but also sea level change from regional to a global scale. And the target is to deploy and maintain 1,200 deep Argo floats for the next years and decades. Thank you.
Any questions? Li Jin?
Thanks. It's really interesting talk. So my question is about your deep ocean heat content time series has very big high frequency variability. So where is this variability coming from? Do you think it's real or just noise? Okay, thanks.
So yes, this is the part I didn't show you, but we have with the genetic product, we found that we have subannual variability and interannual variability. And those variability are very high for the Western Boundary Current and the ACC, the very highly energetic region. So yes, we We didn't know if it was a real signal or noise from any observing system. So we decided to compare with ocean reanalysis. And basically, when we do that with GLORIS at a 1/4 degree and 1/12 degree for the subannual variability on the left side, especially at the 1/12 degrees, we can see pattern coming from the highly energetic region, but not for the interannual variability. So we are still investigating if those signals we are seeing with the geodetic product are real or not. And one outcome would be to use the ECHO2 output for that as well.
Another question? Okay, well, thank you, William.
Thank you.
Next speaker, we have Brian. Brian Soden. Brian, are you there? If not, we're going to move on to the next session, right? Or, hold on, what's the next session? Discussions. Yeah, so discussions. Okay, well, how do I go with the discussion? It's just, I don't have any notes. Yeah, so discussion is about the this session one.
The chair should go up front and seed the discussion with their own question.
I think this session, for the interest of the Earth Energy Imbalance Assessment, is really about getting a feedback from the community about the requirements we are seeking for the Earth Energy Imbalance Assessment. What is the accuracy we need, and what is the uncertainty we need on the Earth Energy Imbalance to answer the science questions that the community is interested in?
Yeah, so currently we are doing that using ocean heat content, which is primarily the most accurate measurement of the EEI. We integrated all of the Argo floats and the constrained series measurements, right? And then the question is, if you see that increasing EEI, do we have enough observation to understand what's causing that changes? And also, do we have enough observation, or do we have enough accuracy we need for understanding that or predicting the future climate?
If we trust your observations, the Earth energy balance has not changed that much during the last 20 years. What has changed is what caused the Earth energy imbalance, right? Between the EI, between the hiatus and after the hiatus, what is the change in the Earth? Well, there is this trend of plus 0.4.
The rate of change of EI is not changing.
Yeah, the rate of change.
Yeah, EEI doubled, and that we're seeing in the in situ as well as series. So over this period, the EEI doubled. So I don't know what question you want to, because Seiji's just talked about 2 or 3 different things, and each of those is probably, yeah. So I think your first question was how accurately do we need it? And I know Jim Hansen had a paper at some point. 0.1 watt was the sort of target for knowing EEI. That was his number. How he arrived at that, I don't know, but that's probably reasonable given that it's not, it's somewhere between 0.5 and 1, probably now closer to 1. So, yeah, right. So 0.1 watt is probably, yeah. Well, I don't know that we're going to get better than 0.1 watt per square meter, absolute EEI. Go ahead.
Yeah, I'm just starting here just to get the ball rolling. So one point discussion we had is the role of the ocean and the role of the heat redistribution within the ocean as part of a player explaining potentially part of this increase, this recent increase. So with this respect, in terms of your question on the accuracy, so we have seen also this time series comparing the top of the atmosphere radiation with several products. So the figure you was in your talk with a huge spread. So if we want to explore, let's say, the pist of the role of the ocean and potentially heat distribution explaining part of this signature, we need to understand why they're so different, right? Because the spread is huge, and this is exceeding all the uncertainties we are discussing about, and that's definitely also exceeding almost a signature because it's really huge. So what's happening? We are in a golden period, and what's going on? So it's one of the first, maybe.
OHC, not a product, I thought was used to estimate an uncertainty for the ensemble, right?
I mean, this is not an uncertainty, right? So we have done this. It's an approach to do something with what we have at hand. So, and so the products or the producers today, that's maybe one of the recommendations they do not provide. There are very few who provide the structure and internal uncertainty. So we can't do more with the products unless we put yes or I don't know. So we can't take the data. We don't have the uncertainty. So we have to deal with this. But the question is nevertheless, why there is this huge spread? So and with this, which is so big, we are not able to really at least look at this part for the ocean to understand with the redistribution or even don't talk about uncertainties and transports.
So I think I keep wondering if, so we tend to want to just use Argo and analyze Argo, and people do that, and they use different techniques for, sampling limitations, and they end up with different results. So to me, I guess as maybe Tim would have, and you, what's the right approach? Because it's a great system, it's a great distribution, but it doesn't cover all of the oceans. And so does it make sense to sort of have a baseline that brings in altimetry and other data sources to fill in all of the gaps, to reduce some of the mapping errors? Because I think the plot we saw where they were all over the place was largely because of different assumptions in terms of trying to make up for the lack of sampling. So that's probably, I mean, if you're going to do an assessment, you can't avoid that. And I don't know if you're probably thinking along those lines as well at some point.
Thank you. The plot that Maria showed was for yearly, and I think it's debatable whether we have enough data. I would say yes, there are enough data at the yearly level. And when you say Argo, I mean, we kind of use that as a blanket term. There's Argo plus other in situ, and yeah, we're still lacking, especially up in the Arctic, but there are some data, and in places like the Indonesian through flow. But I would argue that there's sufficient data, but it is, as you say, how the different groups use the data, quality control it, or and I will show tomorrow a little bit of how mesoscale eddies can skew the overall heat content, or possibly maybe they're selectively sampled by Argo, or maybe there isn't enough coverage to actually sample at the mesoscale level like that. But then how do we deal with that? That's a data set we do have. How do we deal with that? And I'll suggest one possibility is using altimeter, not to actually get the ocean heat, because but to help to quality control the data, or not actually quality control, but identify mesoscale eddies, and then well, then we have to decide what to do with it. Here's an Argo float in a mesoscale eddy. How do we handle that? And I think we need to handle it differently than a lot of the methods do now. Definitely our method, where just that if an Argo floats in a mesoscale eddy, it's extrapolated, if you will, or interpolated to a larger area around it than is represented by that mesoscale eddy. So I do think it's how we deal with the data.
But you see value in bringing in things like altimetry to help, you know, it's basically, it's not my understanding, like the Willis et al. Approach, it's to help the mapping, you know, where you don't have data, it doesn't substitute.
Yeah.
It's like a fancy interpolation approach or extrapolation in a sense.
Yeah, and there are a number of methods that do that. I think we need to use that with caution, because altimeter, the signal's more than just ocean heat, and we've seen that, you know, 60% now is mass change. So you can use altimeter, but have to be really careful because that signal is not just ocean heat.
No.
Yeah. Yeah, it's kind of a related question. You know, this morning I've heard a lot of, you know, very interesting talks, but I've also heard a few instances that I would categorize under the realm of, you know, structural uncertainty, and I'm wondering how much we underestimate that. I'm going to give you examples, the one that was just discussed. The choice of excluding the altimetric record from the analysis of ocean heat content seems to completely change the trend, right? It seems that on the top of the atmosphere radiation, there is a 4 watt per meter square correction that is somehow then compounded into a 0.1 uncertainty on the imbalance. I don't understand that either. And the third example is, you know, by kind of, you know, in the ocean analysis world, you can decide to use dynamics or not. I tend to, you know, see optimal interpolation in that way as a reanalysis that just doesn't use a model. And, you know, by excluding those, we shrink the uncertainty estimate, but I don't think it's defensible. So I guess my question is, how do we plan to account for structural uncertainty better, maybe?
So which of these do you want to talk about first?
So first of all, I think there is a misunderstanding. So when satellite altimetry is used with Argo, it doesn't change the trend that much. There is a good agreement between the trend in Argo and, on the other side, altimetry minus grace. It changes especially Argo, the distribution of Argo makes it difficult to get interannual signals and below in terms of frequency. And if you put in altimetry, you get a better resolution of interannual signals. And actually, I think that's a key point. And that's something we're thinking to do, is to take altimetry minus Argo and to include altimetry minus grace and to include Argo to try to go high frequency to be able to better compare with CIRES. And I think CIRES is doing a good job at high frequency for the Earth energy imbalance. So it's really about different timescales for different observing systems. And they overlap on some timescales. And we have very good confidence when they overlap, because you're removing lots of systematic errors. When you compare altimetry minus grace with Argo on interannual and longer timescales, you've got a very good agreement, and we feel we're safe. And when we close the energy budget, comparing, for example, altimetry minus grace with Earth energy imbalance from CIRES on the interannual timescales, at 2 years and longer, and you will see some time series this afternoon, there is a good agreement. That means we are closing the energy budget. And this gives a very good confidence on this global variables. And you're removing this question of systematic errors. And I think in the future, of course, combining those data will give probably a better estimate of the Earth energy imbalance. But I think we should never do it as something which is just done, we will have to do in a several step. First step, we will have to take the data independent and check that where it overlaps, it agrees. And then if we have confidence in the data, then we can start to mix it in a second step and propose a product but we have to keep a step where data is just kept independent to be sure that we don't have any systematic errors. We can, for example, we have to check, in the first step, we have to check that we close the sea-level budget. Because if you close the sea-level budget with independent data, you're making sure that you're checking your observing system at each month, and you just check that the observing system is doing the right job. And I think this is a safe procedure. That's, I think doing a sequential way of combining the data, starting with validation by intercomparison where it overlaps, and then mixing it to try to solve the different timescales in EEI is potentially a way forward that answers these questions of systematic errors.
Okay, so this is a more of a TOA session. So it's a question to the uncertainty of a series data set, because we know this it's not 100% accurate. So the uncertainty should depend on the time scale, right? So the month-to-month variation and the year-to-year variation should be different. So what is what are your opinions about the uncertainty for year-to-year, month-to-month, and also the trend for series data?
Okay, so I just want to address something that the previous question, he's confounding two different things. The absolute accuracy of series, yes, we constrain to Argo, we have 3 to 4 watt absolute accuracy uncertainty. So what we do is we take a 10-year period and adjust the TOA shortwave, longwave within uncertainty so that it's consistent with in situ based EEI over that 10-year period. And it's a one-time thing. It's not a time varying adjustment that we're making. So you do a one-time adjustment. Essentially, if the truth is here and series is up here, you essentially take the whole record and just basically put it on the same radiometric scale as what our understanding of what EEI is. So that's one part. Then the variability is completely independent, right? The variability is basically series measuring Earth and showing variations. That's not tied to anything. That's purely. So the 1/10 of a watt per square meter is based on comparing it's multiple lines of evidence. We've got series instruments on 4 different satellites, launched in different times, operated in different modes. We do head-to-head comparisons between those, and the differences are on the order of 1/10 of a watt, say for the longest records, Terra and Aqua. Then we did the comparisons with Argo that brings in the altimeter data as well, and it's better than 1/10 of a watt per square meter. So that's our, we don't have truth. Well, not yet, truths, but, when you have multiple instruments, you compare them and you get that kind of level of agreement. So that's sort of how we're coming up with that uncertainty. Now, at the monthly level, we do the same sort of thing. So we produce monthly anomalies from series instruments on different platforms, and we compare them against one another. And the uncertainty there is about 3/10 of a watt per square meter, like the 1 sigma. 3/10 of a watt when you take a time series and look at the difference. It's about that. So what contributes to that? Well, we get global coverage daily, but sometimes there's instruments turn on and off, and so you don't get 100% global coverage daily. And so that contributes to a few tenths of a watt per square meter. We're comparing series instruments on different platforms with different orbits, and so there could be some difference there from diurnal cycle, but I think that's very small. So it's about 3/10 of a watt per square meter is the consistency at the monthly, and of course, then if you're getting down to annual, it gets knocked down tremendously. So I don't know the actual number. It's probably down to 1/10 of a watt per square meter 1 sigma at the annual scale. It's very small. Is that what you were looking for? And then trend-wise, based on what I just said, right now we're on the order of maybe 1/10 to 2/10 of a watt per square meter per decade. Uncertainty, if you trust our comparisons amongst all of these different platforms. But that's all we can do. We can't pull out magically numbers from the air. We have to look at multiple different instruments and see how they compare, and that's what we get. So it's not perfect, but it's what we have.
Yeah, I don't know. I have a strange feeling about working towards the perfect EI record by merging different things and so on. I mean, it's a good goal, but like trying to work on something that magically nicely fits to what series is telling us in terms of variability. Is that the right goal? I feel like it's good to have all these different heat content estimates, having a spread, having variability, because we don't know which one truly is the right approach to do it, right? And I think it's a good idea to do these systematic investigations into what if we put all the different input data into the same mapping technique, or in broader terms, quantify the uncertainty due to mapping, due to quality control, to get a better sense of the true uncertainty that's in there beyond the spread, right? I don't know. Oh, do we have to move on?
Well, just meanwhile, just to answer, I don't think it's about reproducing CRES. I think it's just about closing the energy budget. And I think it's exactly like closing the sea level budget. And what I was saying before, those global integrals, they are very difficult to measure because we know there is a sampling issues and all the instrumental issues and many issues, and there could be systematic errors. And then we have these conservation laws which help us to watch carefully our observing system at each time step, but also to check that we don't have some issues or systematic issues within the system. And so the idea to mix, for example, sea level, gravimetry, and Argo, and potentially put also the atmospheric estimate from Michael Meyer from ERA5, is to go higher frequency, to be able to close the energy budget by comparing with CRES on a longer time scales. And then if we can do that, we get some robustness because we know we are conserving energy. And this is very relevant to cross-validate our different observing system. It's not about just...
Yes, so I wanted to go a bit in a similar direction. So I think also, well, so there are products available which combine already and which do not combine, which are based also on a remote sensing approach alone. And so we have seen a lot indirect approaches, and so on. We have seen a lot. So, but and I agree that the importance is to track the quality through budget constraints, because again we could have trust in this and this and this, but there can be always something. So there was a discovery of an altimetry bias and so on, which had not been discovered before, etc. So these are all aspects. So what I think, in line what you also said, is to continuously track what we have available and what the issues are, which will bring us ahead to improve what we have, and try to optimize the different approaches which are used in different manners, because they're funding there, different countries have different approaches, why they have put together now a specific activity. And also to understand, for example, what are issues with, for the ocean data, this is a vast investment. You have any idea how many data these are? And you have to quality control them, and then you have to fight all the time that people continue funding also for the shipboard measurements, because they say, oh, you have Argo, you don't need shipboard measurements. But if you don't have shipboard measurements, you can't calibrate your Argo measurements. So, and also if you don't have precise in situ measurements, you also can't calibrate your altimetry data. So we need to keep the system. Sorry?
We don't calibrate altimetry.
No, calibrate, but validate. Of course you do this with in
situ
situ
data. Close the sea level
data.
budget, you mean?
Sorry?
We close the sea level budget, you mean?
No, you also do, for the processing of data, you also
we never
validate with in situ data, of course. validate.
But not,
She's not saying calibrate.
yeah,
Validating.
but we don't validate altimetry against Argo. We validate altimetry
Maybe not
against
altimetry, but there are
gateways,
other data out around there. So I'm very general here.
Yeah.
So I'm not
Yeah,
talking
that's not
about
calibration.
only. Of course, you do this also for SST. You do this for chlorophyll. You do a lot of things, right? And also for the different correction parameters for altimetry, you do this as well, right? It's not about sea level only. So, however, it's a different discussion. And so, so I lost my. but I want and we also to have new ways, like for example, when you start to look at the role of mesoscale. So I think that that's important that we continue to track new advancements and continue to track to understand what's not working and what can be improved, which will allow us then to have a better performance for each of us than to continue to work in all corners on the same questions. So that's, I think, is important.
Well, one thing I want to say to Maria that was not much series, but I think it's if we come up with the same answer from two independent estimate or two independent measurements, that will increase the confidence of our estimate because we don't have a truth. So I think it's not much, agreeing a series is good or not. Or just a two independent measurement. It's agreeing. I think that's good.
Both right or both wrong?
That's good, right? But I want to say that we even within a series, we have a two different sort of independent estimate. One is directly measurement the TOA, and another one is computing the TOA flux with totally independent measurement, the modest clouds, and reanalysis, temperature, humidity, and those two agree fairly well. And going with that, and we can't quantify the uncertainty, but we get the feeling that if you say uncertainty is 5 watts, we can get the feeling that no matter what we do, the global mean is very stable, and we can't tweak our global mean by 5 watts. And so, doing this for a long time, we got sense of uncertainty. It can't be quantified very well, but the sense of uncertainty we can build in by doing this.
Now it's on? Is it still on?
It's on now.
Okay. That I will be trying to chair.
Okay.
Oh, you want to go?
No.
Oh, no. Okay.
Well, I can help you too.
Oh, yeah. Can we split the work? Somebody pulls up slides and somebody, okay. So we're starting with a completely new session, session 2, on space techniques to measure the EEI. You want to stay? Oh, please stay. Oh, you time, perfect. Do you time for 15 minutes? Okay. Yeah, okay. And our first speaker, are we ready? Anne Banu. Anne is going to speak first, kick off the session, and she will be talking about understanding the non-closure of the global mean sea level budget for the EI estimate and technical issues. And I think we will be aiming at 15-minute talks so that everybody has time for questions right after the talk. If not, we will be strict.
Thanks.
Okay, there we go.
So, hi everyone. I'm going to speak about the non-closure of the global mean sea level budget. And in the second part, we'll look at how it impacts the EI estimate. So, the global mean sea level budget says that the total sea level change is the sum of the contribution from the baryostatic component, which account for the mass, water mass displacement, and from the steroid component due to temperature and salinity variations. So we have altimetry sensing the total sea level variations, Grace gravimetric satellites sensing the baryostatic component, and then the steroid component is inferred from the Institute Argo temperature and salinity data. And we assess this sea level budget because it's a tool to assess the consistency between these three observing systems in observing the sea level change. So here is a global mean sea level budget with the altimetry global mean sea level rise in black, the baryostatic component in blue from Grace, and the steroid component from Argo in green. And the sum of Argo and Grace gives the white curve, which is the sum of the components, and that we compare with the black curve, giving the residuals you have in the other plot. So we can see that until 2015, 2016, the sea level budget was closed within uncertainties. But over the last years, we ended up with a residual trends of about 2 ± 1 millimeter per year. So this means that we have some errors somewhere in any of these three components. So what we've done is to investigate each of these components to try to figure out what are the source of errors that are responsible for the observed non-closures. So let's start with the halospheric component due to salinity variations. This is just a comparison of halospheric sea level from various Argo graded products, and we observed first high discrepancy between these different data sets, but most importantly, a decrease in the halospheric sea level, which is not what we expect, as in global mean, we would expect this halospheric sea level to be either close to zero, either slightly increasing due to the freshening of the oceans. And it appears that this drop in the halospheric was actually due to some sensors of the Argo float that measured salinity sensors, sorry, of the Argo floats that started to drift very quickly after they were put into the oceans. And these problems occurred from around 2015, so it corresponds to the non-closure here. So in global mean, what we can do is to neglect this halospheric component that is supposed to be nearly zero. So this budget was the initial budget with the total steroid component, and on the other side you have the budget neglecting the halospheric component with only the thermosteric and baryostatic components, giving this sum of contributions here, and this allowed to reduce the budget residuals by about 40%. But still we have some significant residuals left there, so it was not the only issue. Then we looked at the altimetry component. So the altimetry global mean sea level is based on a succession of reference missions, which were TOPEX starting in 1993, then JSON-1, JSON-2, and JSON-3, which was launched in 2016, when the budget starts to show non-closure issues. And on board the altimetry missions, we have two instruments. We have the altimeter that measures the distance between the satellite and the surface of the ocean. And we have the radiometer, which is here to correct for the path delay, which is due to the wet troposphere between the satellite and the ocean. And this wet troposphere correction is actually known to be a major contribution of uncertainty in altimetry. So we looked closer to the specific wet troposphere correction of JSON-3 by comparing it to other wet tropospheric corrections, two from other satellites, Sentinel-3A and Sara-Altica, to the altimetry satellite, sorry. And we also compared it to a wet tropospheric correction that we derived from water vapor climate data records from our EMSS, the EMSS dataset. And all these comparisons agree to say that we have a significant drift of the JSON-3 radiometer of about 0.5 millimeter per year. So it's a redundancy between all these comparisons that give us confidence in the fact that it is the JSON-3 wet tropospheric correction which is drifting. But as you see, it's not really linear over time. So we use all this comparison to estimate an empirical correction to correct the global mean sea level. So here it's the sea level budget in solid line. It was before correcting for the drift of JSON3 with tropospheric correction, and in dashed line it's after correcting for this drift. Same in the residuals here. So you see here that once again we can reduce a little bit the residuals by 30%, but there are still residuals here left. So now we'll move to the thermosteric, back to Argo, to the thermosteric component. So this is a budget we ended up just before, after neglecting the allosteric component and correcting for JSON3 drift with the Argo thermosteric component here. And on the other side, what we've done is to replace the Argo thermosteric component by an estimate from the ORAS-5 reanalysis here. And suddenly we have no more non-closure at the end, but you can see that it's not true all over the period. We have some long-term residuals here. Also, we have to keep in mind that ORAS-5 is not independent from altimetric data. So we have a kind of some redundancy between our components here. The idea when we did this at the beginning was to say, okay, if the problem is in GWACE data, if we remove them from, well, if, then this should still not close as GWACE or not here. But if it closes, maybe the problem is not from GWACE. Sorry, it's confusing. So this result, it's actually difficult to interpret due to the non-independency of the data. But what we get to is to say, when we change the thermosteric component, we have quite different results. And while Argo, until 2015, allowed to close well the sea level budget with very flat residuals, and then we have a change of behavior in the end. If the problems come from the thermosteric component estimated from Argo, it might actually, there might be a reason, which is that the Argo gridded dataset we use contains a lot of real-time data from the Argo float due to the lack of delay mode quality control data available, and they are not necessarily updated when this delay mode quality data becomes available. So we have certainly an underestimated uncertainty of our thermosteric component over the last years, but we have not much more. The inference that we can make from this comparison are still vague for me. But it will be useful a little bit later as well. And we're for now going to switch to the barostatic component from GWACE data. So once again, we have, this time we remove the altimetric component, and we have the barostatic sea level observed by GWACE. And this time we look at the ocean mass budget. So we compare the total barostatic component to the sum of its contributions from Greenland, Antarctica, glaciers, terrestrial water storage variations, and atmosphere water vapor. And all these contributions are estimated from models that are nearly independent from GWACE data. And what we see is we still have non-closure over the end of the period, but we do have also non-closure at other periods. And here what we are going to look at this time is not the difference between the sum on GWACE, but we are going to look at kind of the residuals of the terrestrial water storage variations somehow. So on the next slide, what we look at is to compare this terrestrial water storage from hydrological models to GWACE minus Greenland, Antarctica, glaciers, and atmosphere water vapor. And we'll also, compare it to altimetry minus thermosteric minus ice and atmosphere. So here, what I'm talking about. This pink curve is the terrestrial water storage variations from hydrological models. And if we compare it to the black one, which is GWACE, actually we see a pretty good match, even at the end. The only part where it's not really good, it will be at periods such as in 2015 when we have ENSO events. And it seems that the terrestrial water storage variation from hydrological models actually lack amplitudes when there are very strong events such as El Nino, La Nina. We can just quickly look at the comparison with altimetry minus Argo minus ice on the atmosphere models, which is the blue curve where we have this big mismatch at the end, which is a little bit reduced with when using ORAS5 instead of Argo data. But it's not true at other times. I should speed up. The first conclusion on the sea-level budget is that we have identified a salinity drift and a drift in JSON3 radiometer wet tropospheric correction that we should correct for. But we still have a remaining non-closure, which is, we for now suspect to be attributed to the Argo-based thermospheric component whose uncertainties are likely to be underestimated due to these real-time data. But that should be improved in future updates of the Argo gridded datasets. And we have this terrestrial water storage variation from hydrological models that lack amplitude during extreme events. So now I have just a few slides left to see how these observations affect the Earth energy imbalance estimate. So we are going to talk about the Earth energy imbalance, which is derived from geodetic measurements, from the difference between altimetry and GWACE and Argo for the halosteric component data. So in Toulouse, in Lagos and Magellan, we are developing such a Earth energy imbalance estimate. I'm not going to detail it because it will be done by Victor Rousseau just in a few talks. But I want to show you how understanding the non-closure of the sea-level budget helped us improve the Earth energy imbalance estimate and get closer to COS estimates. So I'm going back 1 year, 1 year ago, where we had this space geodetic estimates of the Earth energy imbalance in black compared to COS, which was in blue here. Everything being filtered at 3 years. Okay. So we had a rather good agreement between the COS and the geodetic EI estimates until the end of the period, where we have a big discrepancy between the two. So for this one, no, it doesn't work. So the black curve was done by computing based on the thermospheric computed from altimetry minus GWACE minus the halosteric from Argo. Then we neglected the halosteric component, giving the green curve. And third curve, the red curve, we applied the correction for JSON3 wet tropospheric correction drift. Each time you see that we reduce this bump at the end of the period, getting closer to COS. Just one warning, this red curve is still not the current, the latest version of the EI, so Victor will present you the real latest version of the Earth energy imbalance we've estimated just after. But what I wanted to show here is that we had to take into account the drift of the halosteric and of JSON3 wet tropospheric correction in order to get a better estimates with respect to COS. So to conclude, we have both the sea-level budget and the energy budget to assess the consistency of the observing systems. And from the sea-level budget assessment, we have a few recommendations for the Earth energy imbalance estimates. First, concerning Argo dataset, we have to use as much as possible delay mode quality control data rather than real-time data. And this is also true for in-situ-based estimates and also regional studies where we'll not be able to neglect the allosteric component. And I'm in particular talking about the Argo gridded dataset because even when some delay mode quality control data are available, they are not always included in the gridded dataset that are provided. So as users of these gridded datasets, we need this data to be included regularly. Then in global mean, we have to neglect the allosteric component. For altimetry data, we need to correct for this nonlinear drift of a JSON tree wet troposphere correction. And finally, even if the energy budget closes, we still need to understand the remaining non-closure of the global mean sea level budget, for a matter of consistency of the observing system. And we are going to do further work on in particular within the framework of the ESA-ESRIN sea level budget closure CCI plus project that just started. Thanks.
Thank you so much. Very nice. I think we have time for questions. Tim?
Thank you. I think Annie Wong is going to give tomorrow a talk about the Argo data and the salinity drift. I don't want to speak too much for her, but I don't think that the problem is that salinity drift corrections are not being applied. I think they are, and when you do apply them, there is still some change in the salinity and in the allosteric. And I don't think there's a problem with applying there are going to be some problems in delayed mode temperature, but nothing like a salinity drift. Quite often, the real-time data for temperature is also the delayed mode. Yeah. So I don't know that thermosteric is going to change that much between real-time and delayed mode. Although, of course, they do find quality.
Maybe our uncertainty will increase a little bit, making it less non-consistent. I don't know. Even if it's not a drift, but I don't know.
Yeah, there will be some floats found to have bad temperature or a problem with pressure and sometimes, okay. But I don't know that it's not the same as with the salinity drift, which you have to, if you don't use the correction with the salinity drift, then you have a problem. But I don't think there's that kind of problem with temperature. So okay. I don't think you're going to get that magnitude of difference between real-time and delayed mode Argo data.
Okay. So the question is still very open to understand what's happening.
Sorry. Any pressing questions? I had a question, and I was just wondering, when I look at the time series, is it a non-closure within uncertainties or no? Is it a true non-closure? And is it still significant after your correction?
Yeah, when we work only with, not speaking about the analysis, but only with altimetry, GWACE, and Argo thermosteric, in the end, so here it's just the time series, but in the end, if we compute trends over the period, they become significantly different than 0 over the end of the period. Trends might not be a good proxy to assess it, but they become significant. Yeah.
Yes. Okay. Okay, last one. Karina.
Very quick. And did you test the area between 60 north and 60 south? Did you reduce the area for altimetry, for example, to see whether this could be also a reason because there are some areas not included in Argo?
Yeah, there's a mask applied here to get the common area between the data sets. So it corresponds more or less to where, so it's roughly plus or minus 60 without internal seas, without the Indonesian seas. And also there's a mask near the coasts due to great data. So it's a great reduced area.
Our next speaker being James Regan. Is he online or is he in?
Yes, I'm here. Can you hear me?
Yes, we can hear you
Okay.
very well. Is that right back
Great.
there? Okay. We will allow for you to share your screen. You should be able now. Is that right? And James is,
Okay.
yes. Oh,
Can you see this okay?
yes, but, oh yeah, perfect. Now it's in presenter mode.
Okay, great. Thank you. Yeah, so the talk today is, sorry, I just want to get this out of the way here. Okay, thank you. Yeah, so today talking about, and this follows from Anne's talk very well, diagnosing the recent halosteric sea level trends. And this is work being done by myself and colleagues Tim Boyer, who I know is there, and Zankun Wang. And you've already seen this time series before in the previous presentation, and this is a time series provided by Eric Loyette at NOAA as well. And again, the top lines, the purple and grays, are your altimeter measurements of global mean sea level over 1993 to 2022. Your bariostatic, your ocean mass changes in the blue and black. And what I'm really going to focus on today are these Christmas colors down below here, these red and greens, and in particularly this lime green, which is the total steric sea level change that the NOAA NCI product produces. And what you can immediately see is that there is a difference rising from about 2015 onward, where the total steric from NCI, which is the halosteric plus thermosteric components, is tracking lower than other in situ total steric calculations. And the question is, why is it doing this? So here we have the 2005-2022 total steric sea level change between 0 and 2,000 meters. And the orange line is your thermosteric component, which tracks from roughly 15 millimeters up to 35 millimeters through 2022. Your halosteric, which tracks from about 0 to around -4 going to 2022. And with that change causes a decrease in the total steric. So the total steric follows quite well until 2014 and then begins to deviate from the thermosteric. And all of these measurements are made from in situ profiles within the World Ocean Database. And what we note is that the recent halosteric contribution to total steric sea level change has acted to reduce the total steric sea level change by as much as 15%. And this is just the way to go about calculating the halosteric using the beta coefficient and the salinity anomaly and integrating between depth layers. So what we want to do is figure out, okay, well, what is going on with the 2015-2022 halosteric sea level change? So if we go ahead and calculate, and this is again what you've seen previously, on the left side is your 0 to 2,000 meter global halosteric sea level anomaly. And again, you can see it tracks pretty well between 0 and -1 up through 2014, and then begins to dive down going towards 2022, going from -0.5 or so, almost down to -5. At the same time, and uncoincidentally, we also see a rise in the 0 to 2,000 meter global average salinity anomaly, particularly from 2014 onward, where it's around 0.0005 and goes up to about 0.003 at 2022. And if we just coordinate both of these, it's about a 0.0007 change in average salinity between 0 and 2,000 meters results in a halosteric sea level change of about 1 millimeter. So you can see a very, very small change in salinity can have quite a large impact on the halosteric sea level in the upper 2,000 meters. Now, the first question, of course, is the recent increase in salinity, can that be explained by the salty bias of Argo propylene floats? And I won't spend too much time on this. I won't spend too much time on this slide because I know Annie Wang has a presentation tomorrow entitled Bias and Argo Salinity, the Impact and Best Ways to Use Argo Data. And that will be tomorrow, so I definitely suggest checking that out. What I just want to highlight here is Argo really comes in 3 different modes. The real-time data, which is shipped out within 12 to 24 hours of last measurement, your real-time adjustment, which comes in, again, in about the same latency, but has some corrections applied based on delayed mode salinity adjustments of the same cycle. And then, of course, your delayed mode data that comes in normally after 12 months. So what we wanted to do is look into the salty bias. And of course, there it is there. If we look at we know that the 2015 was the start of that manufacturer error with the cell sensor drift. And we wanted to look into and see, well, are we really fully accounting for that in the data? So this plot shows your pink bars are the data that has been adjusted, whether it's a real-time adjustment or a delayed mode adjustment. And your blue bars are the ones who have not been adjusted yet, are still in real-time mode. And what we can see is from 2005 through 2016, over 90% of the data has been adjusted. And then 2017, 86, and so forth, but you're still over 75% of the data up through 2020, and even over 50% as in 2022. Of course, that's mostly real-time adjustment, but there is at least some kind of an adjustment added to the salinity. And in red is what you see is the delayed mode average adjustment for that time period. And you can see it kind of revolves around 0, pretty close to 0, up through 2013. Then it begins to start to go down in 2014, 2015, and kind of maxes out at around 2019, 2020, 2021, where the average correction is about minus 0.005. And that negative adjustment means Argo is being corrected downward, i.e. it's being made fresher. And we wanted to look deeper into this particular adjustment. So if we look at how the adjustments are applied in real-time data and delayed mode data, we get this time series. Now, what I want to really pay close attention to are the blue lines, and I did shade the background very light on purpose because I wanted to highlight the time series, the line plots here. So if you just focus on the blue, the green, and the purple lines, those are the delayed mode adjustments from the Atlantic, the Indian Ocean, and the Pacific Ocean. And what you see is, if we look at the blue line, this is the Atlantic. Again, it tracks similar to the global mean that I showed previously, up to 0, and then begins to dip down towards minus 0.005. The green does something very similar from the Indian Ocean and the Pacific as well, although the Pacific dips down a little sooner than the Indian Ocean and Atlantic, but it drifts pretty close by the end of the time series. And if we look at the real-time adjustment, which again, this would be your orange, red, and brown lines, they also track very well with what we see in the delayed mode adjustment. The notable exception that is clear in this plot is the red line, and this is the Indian Ocean real-time adjustment, particularly in 2014 and 2019. And I won't spend too much time on this. I did take a quick look at why these were spiking. You can see that the red bar plot here, it's a very small percentage of the total data included. And there's just a few outliers here that are quite large, making this spike. Same thing with 2019. Again, it's a small amount of data, and it's only a few that are making this kind of negative spike downward. But overall, what I wanted to take away from this plot is that the real-time adjustment and delayed mode adjustment track well with one another for each ocean basin. Now, why do we have to take these biases into account? Well, for starters, if we look at the left plot, the 0 to 2,000 meter halosteric sea level anomaly, this orange line is what we get when we account for the salinity drift and the bias, and we include the bias adjustments. Over time, we get a total of around 4 millimeter change in halosteric, negative 4 millimeter. However, if we do not take into account any bias adjustments, that actually ends up doubling. So this is that blue line here, and it goes down to -8 by the end of the time series. So if we didn't use these bias adjustments, then this time series would account for over 30% of the total steric sea level change. And this here is just your thermosteric component of sea level. And you can see it's at about 35. And if this value is around 8, that would bring the total steric sea level down to 27 or so. So again, a significant portion would be explained by halosteric if we did not account for the bias adjustment. Now, after doing this, we wanted to double check and make sure that are there any residual salinity bias contributions even after the bias adjustments have been applied. So we did a quick analysis to look at whether or not there is still a bias there. And here we have the Argo adjusted salinity minus deep measurements from bottle and CTD from the WOS, GoShip, and CLIBAR programs. And these are research ships that go out and take these high quality hydrographic measurements. So what we see over time, and this is 2015 through 2022, and this is Argo minus OSD and or Argo minus bottle and Argo minus CTD. What we actually see when we look at 2015, 2016, 2017 is really there is no significant mean positive bias. If anything, there's actually a bit of a negative bias indicating that we may be even a bit fresher than we should be. So it does appear that Argo is well taking care of this bias correction in the data. Now, with that being said, are we seeing the contributions from this change in halosteric consistent across all 2,000 meters? So in order to investigate that, what we did was we split it up into 200-meter bins. And that is what you see on the left side. So this here, again, is just your 0 to 2,000 meter global salinity anomaly. And that's just your time series. And down here is how it's split up between 200-meter bins within the 2,000 meter depth level. And if you look at the 0 to 200, which is by far the largest salinity anomaly that we see, it has actually been increasing pretty steadily since 2005. There's not necessarily a big bump up when we do see the bias correction or the cell drift issue really crop up in 2015. And even with the 200 to 400 level, even with the 200 to 400 level, again, we see this, it's constant through 2008, and then it's constant through 2016, 17, and then it bumps up in 2018, almost some kind of oscillation. However, even if we start to look at some of the deeper levels, so if we look at this blue curve, which is the 600 to 800 meter halosteric or global salinity anomaly, what we see is it actually begins increasing in 2010. It's a very small increase, but it's been increasing quite consistently from 2010 to 2022. And similarly between 400 and 600 and other deeper levels. So a lot of these positive trends in salinity have actually started before this bias correction or this larger bias was introduced in 2015. However, based on this plot, we know and can clearly see that the 0 to 400 level is the main contributor to the halosteric sea level anomaly. So these are plotted here, the 0 to 400 meter halosteric sea level anomaly. So 0 to 200, again, is the main contributor. And you can see it's been decreasing pretty steadily since 2005. Whereas in the 200 to 400 meter layer, not so steadily, but does begin to drop down in 2016 and goes down through 2022. So those are your two major components of the halosteric sea level decrease. And then if we break that down by basin, we start to see an even more interesting pattern evolve. For the Atlantic Ocean, that dominates the 0 to 200 meter halosteric sea level global anomaly. And that's plotted in black. And what you see is pretty constant values up through 2016 and then begins to decrease. Now, the reason why we were actually seeing, and I just want to back up, the reason why we're actually seeing this steady decrease is because the Pacific from 2005 through 2014 was actually decreasing. So overall trend is a pretty monotonic decrease in 0 to 200 meters when you begin to apply both the Atlantic and Pacific contributions. However, if we look at just the 200 to 400 meter layer, we recognize that the Pacific is actually the main driver of the halosteric sea level decrease. And I do note that these changes, these abrupt changes in this red line that the Pacific represents, they happen during major El Niños, the 2010-2011 La Nina, and the 2015-16 El Nino. 2010-2011, it goes up, and then 2015-16 El Nino drops back down. So an interesting just food for thought on how these halosteric changes are occurring, not only at different individual levels, but also in different basins. And that's, part of the reason is the halosteric sea level change is very, very regional indeed. If you look at the 2018 and 20, these are just the anomalies of the mean salinity anomaly between 0 and 200 and 200 400. Yes, we see the North Atlantic kind of consistent with the hydrological cycle amplification that has been discussed quite a lot, with the Atlantic, seeing a lot of salinity increases. The Pacific, there is quite a bit of orange here representing a positive salinity anomaly, but there are some blues and so forth. I don't want to spend too much time on this slide. I just wanted to show that there is a lot of regional variability in the salinity anomaly. And same for the trends over time. So this is your 0 to 200 meter salinity trend, which is shaded, and then your halosteric trend, which is in the dotted line. So where you see positive salinity trends, you see negative halosteric trends. And again, are very regionally focused trends, but when you average them over the globe, they do signify a signal. And then finally, what I wanted to end with is what role could E minus P be playing in the upper ocean salinity change? And here you have the significant changes in the precipitation over time from 2005 to 2022, and this is from the GPCP product. So you do see this very significant decrease in precipitation over this time. At the same time, you see some heightened evaporation over the South Atlantic, North Atlantic, and in the Western Pacific regions. And if you combine both of them and look at the significant trends over DE over time between E minus P, what really stands out is the subtropical North Atlantic, parts of the Southern Ocean, but overall, we see more reds than blues in this plot. So we realize that there is a removal of fresh water from the global ocean, and that's what this time series shows. So the black line is your global E minus P anomaly from 2005 to 2022, and what we see from about 2015 onward is this increase in E minus P. So this increase in the removal of fresh water from the ocean. At the same time, we see it in both the Atlantic and the Pacific. So, and this is just a quick calculation, but the loss of fresh water over the global ocean from E minus P alone would be about 0.1 meters from 2015, which would equate to roughly a 0.018 change in salinity upper 200 meters. Now, of course, there is a lot of other processes that go along with salinity contribution, and the mixed layer salinity budget is much more than just E minus P. But this is just to show that there is at least one factor behind this on why we do see this salinity increase. And these are just the conclusions. I don't have to read through them, but the main conclusion that we raise is most of the salinity change is between 0 and 400 meters, which is where most of the halosteric change is isolated. The salty drift appears to have been well corrected by the Argo community, and the upper 200 meter increase may be related to a net loss of fresh water from the ocean. And the 200 to 400 meter layer seems to be more in sync with what the Pacific Ocean is doing. And these are just some references, and I just want to say thank you, and thank you for the conveners for giving this opportunity to talk about this today.
Thank you, James. Very nice presentation. Do we have questions in the crowd? Benoit? Mike?
Thank you. Hi, James. Benoit speaking. I have a question. Theoretically, if you compute the change in freshwater in the ocean at global scale, the salinity shouldn't change. There are several publications about this. So what I understand from your presentation is you're saying that this trend in salinity is potentially some signal. So I would interpret this as the circulation has changed and salinity has concentrated probably more where there is measurements from Argo, and this is probably a problem of sampling from Argo. Do you agree with that?
So I do agree that we have to get a better handle of what is going on below 2,000 meters. I think that is a big question that needs to be answered. In terms of, yes, salinity we should expect salinity to be constant in the ocean. However, I think on interannual timescales, even decadal timescales, we can see this freshwater redistribution, which could cause real salinity changes over longer periods of time. Yeah, I think it will be constant, but on these timescales, I do believe the freshwater redistribution can have a change in global salinity.
Okay, thank you. There's more questions, Tim?
I guess I don't understand, this is more to you, Benoit, why we would expect, yeah, the salts in the ocean are constant or relatively constant, but there are freshwater changes. And so that's what we're seeing in salinity changes, freshwater change. And at the very least, continental glaciers are melting and the amount of fresh water is changing, and that's going to give a change in salinity. And we're also seeing these global changes in E-P. So more water is being extracted from the ocean than is being put back. And you're right, it goes somewhere. Even if it lands, is precipitated over land, eventually it'll run back in rivers or so on and back into the ocean. So that is a redistribution of fresh water, which will consequently change the salinity along the margins, at least for river runoff and things like that. But you could also have that E-P might be stored on land for some period of time, and that would change the freshwater balance of the ocean and or change the amount of fresh water in the ocean and affect the salinity. So I don't think we should assume that we should expect a constant salinity if you integrate over the global ocean.
Well, it's just I'm referring to the papers from Gregory and colleagues in 2006, and I think there was a Monk also earlier. It's just like the levels we are talking about in terms of exchange of fresh water are so small that it's actually not visible. It shouldn't be visible if we had a global monitoring. So it does change, but it's very, very small, according to those calculations, which are based on like the amounts of fresh water which is exchange. But what we looked into salinity in my team a few years ago, and what I noticed, and I don't know if James you agree with that, is that actually there are salinity changes which are very strong in the very located regions, like in the Arctic Ocean, especially at the surface because of P-E, and because we don't monitor the other regions, like especially the other region of the Arctic Ocean. We tend to focus on those regions because they are sampled, and we see some salinity changes. But if that was actually really estimated at global scales, that should be much smaller than what we see. So I suspect that that's my suspicion, and that was my feedback from that study at that time, where we compared Gray's estimate of salinity and the estimate from Argo, is that actually the Argo sampling is amplifying very much the variability in the allosteric sea level in salinity because of the sampling.
That's a possibility, but I don't think in that paper or the recent paper that came out, which showed an overall freshening of the ocean, decrease in salinity, small, but statistically significant, at least by the neural network procedure they used. I don't think they considered evaporation minus precipitation. I mean, they look at the melt of continental glaciers, and that's adding fresh water to the ocean. And then in this recent paper, it makes a calculation and says, with the amount of salinity change we see, there's not enough fresh water to make that change. But they don't look at E-P, and I'm not sure if the Gregory paper does or not. And that is a factor in the change in fresh water, in the change in salinity. So, I mean, we're not saying that you may be right. Maybe Argo is selectively sampling the more salinificating areas, but we can't just set. When we look at allosteric, we can't discount what Argo is saying. We've got to work it into the budget. We've got to figure out why it's changing. I I guess what I'm saying is you need to prove to me that Argo is subsampling in a way that's making more salinification rather than just saying that and discounting the Argo halosteric.
Okay, and then I give you the microphone. I would say it's the other way around. If you don't sample everything, you have to take into account the fluxes at the boundary, and that's something which is not done.
I mean, we can debate this, and we, in our calculations, we do use more than just Argo, and we have a lot of glider data that's on continental shelves. We'll have ice tethered profiles in the Arctic, at least not too much, but there's more coverage than open ocean Argo. So we just want to, and sorry, Jim, that I'm speaking for you, reopen this debate instead of just discounting it and saying what we see from Argo is not real. Let's look into it.
I know there's 2 more questions in the audience.
Yeah, I just wanted to offer to help in a way, because so in ECO, right, we have a constraint that is we account for the freshwater entering and leaving the ocean in terms of mass. So that means the total amount of salt in the system is constant, strictly constant, okay? But the salinity changes. So you can sample ECO in that way, that Argo does, to test these questions, because it's built in as a constraint in this system.
Li Jing had a question.
Yes, just a comment on the comparison between Argo with the CDT, because you compare Argo with 10 years distance of CDT, and it's really large. I think it's not really proof that adjusted Argo data is bias-free. So I would argue that even after adjustment, Argo is still biased in salinity. So you should really compare the side by side.
It is difficult to find enough CTD and bottle measurements. That's why we tried to take we took 1,500 to 2,000 meters to try to remove as much of the seasonal cycle and high variability that you see near the upper waters. Also, to hopefully reduce the amount of trends that could be seen in the deeper layers. So I agree. More high, and then this is in this previous session as well. The more research vessel drops of bottle and CTD would certainly help us in terms of being able to validate the current Argo measurements.
Okay, thank you very much. We can discuss more on the coffee breaks ahead. Moving on, our next speaker is also online, and it's Felix Landerer. And he's talking about Earth's energy imbalance from the geodetic ocean perspective. Felix, can you hear us?
Yes, I can hear you. Can you hear me?
Yes, nicely. Looks good too.
Great. Awesome. Okay, so welcome everyone. Yeah, I'm sad I can't join you. The sun is just coming up where I'm at. Oops. So I want to talk about the geodetic ocean perspective on this topic, EEI. This is work that's been done at JPL together with Maria and our previous postdoc, Thomas. A lot of the figures you'll see are from this paper down here. Maria had already shown quite a few of those images, so I can be brief and fast on those. And a lot of the discussions that have took place in the last couple hours are actually also conducive for me to skip over a few details. So we've already seen a figure or sketch like this from Anne and others about the sea level budget, what it's comprised of. I don't need to go into any details. I do want to make one point though, which is that the budget as such is in first principle, this comprises the budget, the sea level budgets, the steric and the mass needs to add up to the total. However, considering our observing system, this need not close at all. Argo, as we all know, just covers the 50% of the upper ocean, and all 3 have sampling issues, higher latitudes or continental margins. So it's really essential to include these corrections and residuals. That some of these are geophysical corrections like glacial isostatic adjustment that show up in the satellites in different ways. Some are instrumental corrections like Anne discussed. So it's really important, I think, to not forget this point that this budget need not close given the observing system. So I can skip over this. These figures are all from the paper we published a couple of years ago. This is on Argo. We just had an intense discussion. So I'm just going to go straight to the altimetry and ocean mass component. Altimetry on the left, ocean mass on the right. The only point I want to make here is that we have multiple time series. The seasonal cycle has been removed in both of these. And they all kind of, have or group into fairly tight envelopes. Some come with error estimates, quite a few don't. But at the end of the day, we're going to look at differences between these two. So any small deviations here, of course, amplify in the difference in the residuals and could cause issues when we look at that budget and how to interpret and go about attributing it or maybe deriving additional corrections. As has been said before, also ocean mass is about 60% of the net total sea level rise that we've been observing over the last 15 years or so now. I do want to make one point, and I was actually going to be very brief on this, but this does tie into what was just discussed about the salinity and closure. So when we talk about GRACE and GRACE follow-on, so these satellites observe the Earth's gravity field and changes thereof, and we map that into mass changes. There is a hard constraint in the sense that overall in the global mean, the mass doesn't change. That's shown by the yellow line here in the middle. If we look at individual components, for example, here the blue is all the ice mass summed together. The gray is all the land. So they all need to add up to 0. And that's a really hard constraint. So if you look at just a single component, let's say the ocean mass here, and you think maybe the time series is biased in one way or another, and you start to either change the whole trend or just parts of it when it goes from GRACE to GRACE follow-on, it automatically means that another component in the Earth system, either on land or in ice or the non-cryosphere region, has to compensate, so it sums up to 0. So it's a pretty hard constraint that happens. And with respect to the net P minus E and maybe ocean freshwater loss and deposition on land, the GRACE follow-on data don't really support that. We have a net small but still net mass loss of water storage over land. So if there is such a thing as increased P minus E, it does make its way back, at least on the GRACE data, based on runoff maybe. So it's maybe conceivable that in the middle of the ocean, you see a signature, but if you look at the whole picture, you should not see a salinity increase based on the GRACE data. That's what I would say. I also wanted to briefly discuss, since this was part of the workshop, errors in the data. This is a pretty complicated plot. I'm not going to go into all the details. This shows error levels on the y-axis from GRACE all the way here, 2002 through 2017, and GRACE follow-on. We have a gap, of course, so we can't cross-calibrate the missions. That's not necessary based on the measurement technique, really, we think. But I just want to make a couple points. One is there's variations in the error levels over time. That is often related to so-called repeat orbits, where we just don't have enough coverage over the globe for that given month. The satellites decay naturally, so they go through this period where we just don't have good coverage. And there's also other variation here where we have poor thermal control. We have some instrument degradation on GRACE in the last year or so of the record. GRACE follow-on, we also had some issues with instruments, but I do want to point out that we've been able to really match in terms of error RMS at 300 kilometer resolution on the monthly level, GRACE follow-on with GRACE. And the two curves you see for GRACE are actually two data releases. The green one was so-called release 5. That was the last operational release for GRACE. And then at the end, when we had all the 15 years of data, we reprocessed the entire data record and we got it down to here, to the black line. So about 15 millimeters or so error RMS at that spatial resolution. But GRACE follow-on, we're able to kind of carry that knowledge over to GRACE follow-on. There's some slight variations. You see a green line here. We've started to reprocess the data from GRACE follow-on and are able to knock it down a little bit further. If you average this over the global mean, our sort of best estimate of a monthly uncertainty is sort of 0.3 to 0.4 millimeters in terms of sea level. So let's just get to the geodetic and in situ thermospheric sea level. I'm jumping over a few things because we already talked about that. So we get two time series. One is from the hydrography, which is basically Argo in the upper 2,000 meters, and then the full column steric. That's just altimetry minus grace. In that paper here, we got these two trends. They marginally overlap within the estimated uncertainties, but I think we would say, well, they do differ on the long-term trend over the entire period, but also in the interannual variability. And in fact, the difference, if you just take the straight up difference, 0.5 millimeters or so, is really large and too big to be attributed to deep ocean, so anything below 2,000 meters, given what we know about the deep ocean. When we convert thermospheric to ocean heat content, or then ocean heat uptake, which is just the derivative, we do need to multiply with a factor of the expansion efficiency. And in this paper that we published, and others have looked in this too, Benoit and his group have published on this, you do need to take into account that the expansion efficiency, first of all, varies in the ocean. This is a zonal mean plot. And it's also different for different models and observations. They're all kind of, you know, they are consistent. If you just go the shallow part, the upper 2,000 meters, or you take into account the full column depth, but it is important to recognize that there is a scaling going on, and that need not be constant over time. Anyways, the ocean heat uptake we get from the geodetic estimate that way is fairly high at almost 0.9 watts per square meter. If we just compare that to the in situ Argo only 0.62. So this has been mentioned already a couple of times, and that difference is actually a little bit larger because I updated this to 2020 of a little over 0.2 watts per square meter is pretty large. So I think, let me just go back to this one. So this is the global mean picture or the sampled ocean. But I think it's important or useful to actually go into the spatial domain and look at the trends, what they look like, and see if the residuals that we aggregate in the global integral actually have some geophysical pattern that we understand that maps into what we know about the ocean, how it functions, where there might be deep water formation, where there might be regions that can actually warm given how ocean circulation is set up. So here I've marked with these little pictures which measurement system contributes which map. You see the geocentric altimetry sea level, ocean mass here on the right. These are the trends over this time period. And really the main picture I want you to focus on here is on the bottom right, which is the residual. So this is when we subtract Grace and Grace follow-on from and Argo from each other, from the altimetry. So we get this residual map. And if everything would be accounted for in the upper 2,000 meters and there weren't any errors, this should be very close to zero. Of course, there are errors, and there is the deep ocean. So so a couple of things. As was mentioned in the previous talk, there is the halosteric bias. We can get around that in the global mean because the halosteric contribution is small in the global mean, but that's not the case when we spatially resolve it. So what we did in this study here, what Thomas did is adjust the halosteric bias, all these curves that tend to dip down as in a uniform way. But as we just heard from James, there's actually a spatial pattern to that. So the halosteric, the deviation from a global mean halosteric bias is still in this map. There are other errors in here that we can look at. One thing that we're doing at JPL right now is to look at some geophysical corrections that we use to estimate or separate surface mass from other mass changes that are going on in the Earth system. Namely, there's so-called glacial isostatic adjustment. This is the rebound of the solid Earth from the last ice age. And these global models, these global GIA models, they tend to assume a relatively simple 1D stratified solid Earth with a corresponding viscosity profile. we're now looking into, and this is a general trend in the GIA community, doing 3D viscosity variations in the Earth's mantle to allow for lateral heterogeneity, which we know exists, and it has an impact on how fast the Earth rebounds. And what I'm showing here side by side is just a difference from a very, very preliminary model from 3D minus 1D GIA model. And just by sort of, if you focus on the largest scales, and the color scales here are different, this just goes to plus minus 1 millimeter. So much smaller actually in this range here. But if you focus on this large scale, sort of this blue band, it roughly maps into this kind of red band here. So if we subtract this from that, right, we'll knock down, it will reduce at the large scale this bias a little bit. It's not going to account for all of this, obviously, but I just want to make the point here that there's certainly corrections in here that are you know, not in the measurement system, but they're geophysical and they need to be made. So this is ongoing work here led by Aaron Hightower at Caltech and JPL. The other point I wanted to make is we can kind of have these maps side by side with the estimated the pattern of deep ocean warming. William also showed this already. So when you just kind of hold this side by side, you see some correspondence. Other regions don't correspond at all. Like in the Atlantic, we don't really see that pattern of deep warming reflected here. However, there is a pretty you know, big pattern here in the South Pacific, and this region has been well documented to warm, and it's also been well analyzed by Dean Remick and others. And in fact, Dennis Volkov and I, quite a few years ago now, we haven't updated this, but we looked into this region. Sorry for switching the color scale on you. We looked in this South Pacific subtropical gyre, and basically what we found here, there at that point there wasn't any deep Argo, but what we did have is these Vos ship sections, P06 for example. And if you look down here in this plot, they had these campaigns about 10 years apart. So one data point here and one here, and you just draw a straight line. And the trend with the altimeter minus Grace residual sort of maps or agrees within pretty large uncertainty. But we're now working to update that and hopefully fold in the deep Argo as well. So with that, I'm going to come to my conclusions. I was going to be quick with this talk and give a little bit more time for questions or give you time back to go to your cocktail hour, which I can enjoy. But just want to make the point that the ocean mass data record is consistent between GRACE and GRACE follow-on. That's very important, especially because we do have gaps in the data system. And as was pointed out earlier today, that's often can be a problem. The geophysical and instrument corrections are plentiful, and all these uncertainties, they propagate into a relatively small residual. And so, you know, we've gotten it down to about 0.2, maybe 0.3 watts per square meters from the geodetic estimate, we think. But we do have this still a mismatch if we just compare it straight up to the upper 2,000 meters Argo floats. So I can skip over this. I think maybe for the purposes of the workshop, actually, the part down here is perhaps most important. GRACE follow-on, or the last years of GRACE and GRACE follow-on, it is generally a somewhat noisier measurement due to some instrument issues, but there are no, we don't think we have any drifts in the gravity or mass anomalies. Anne already talked about the altimetry, and we'll have more conversations about the Argo that I'm very much looking forward to. So with that, I'll just wrap it up here, and if there's a question or two, I'd be happy to answer that. Thank you.
Yeah, thank you, Felix. Questions from the audience? Benoit? Oh.
Thank you, Felix, for your talk. It's very interesting. in which confidence interval do you obtain your uncertainties for the ocean heat uptake? You obtain 0.24 watt per square meter. And which interval is it? And which uncertainties do you take into account for the altimetry data?
I believe this was 1 sigma.
Okay, 1 sigma.
And so for the altimetry, I don't remember all the uncertainties that we took into account. I can't.
No problem. We can discuss
I would
that
have to
later.
go back to the paper. Yeah.
Hi, Felix. Benoit speaking. I was looking. I was astonished by your difference between Argo and satellite altimetry, and I found the result very interesting because in your residual,
plot is
I think
this?
it's your slide 13 in maps, in terms of maps.
Oh, okay.
And I find it very interesting, and I find that's true that we can see a bit of your GIA pattern, the one you show afterwards. But we are talking about a signal which is about 10 times bigger than the GIA pattern you were showing. And
Right.
one thing that strikes me in this map on the bottom right panel is that it shows a signal which is correlates very well with the signal itself, with the total signgle, either from
Yeah, that's right.
hydrography or so it seems like we are missing some amplitude somewhere. Yeah, can you comment on that? I mean, my first guess would to say it's not a correction. It's like we're missing some amplitude somehow.
Yeah. You're absolutely right. It does look almost like a downscaled image of part of the data, right? That a scaling factor could account for some of these differences. I don't have a good explanation. You know, if you do the global average and the global residuals, a lot gets averaged out. So it's instructive and maybe a little bit scary to look at it this way. I would be very curious to take another closer look to the halosteric signal. I think that could, you know, explain a few things maybe. I mean, we also see stuff like here in the Indonesian region. This is related to the large Sumatra earthquake, which we haven't masked out here, right? So I mean, this whole blob kind of you should ignore that. But the large structures here in the Central Pacific, right? They're very reminiscent here of this part. So I'm not sure what that is or what that means. You know, I guess you can speculate a lot, but that's something we're looking into. It's a good question.
Okay, I also want to comment on these results because when people do different kind of spatial interpolation, it's kind of a spatial smoothing to the fields. So if you look at different product, they really have different kind of smoothness on the upper ocean steric fields. So that impact the residue like this. So if you have a very smooth steric part, you will give a residue very similar to the pattern. So that is my explanation, really.
Yeah, I think maybe looking at it this way is so everything is sort of averaged it to grace resolution, which is sort of in this, we think of it as the coarsest data product of these two, but maybe of these three, but maybe that's not true. And maybe this needs to be averaged a little bit further, right? Not just in 300 kilometer boxes. So maybe this is too high. We don't actually have that resolution. But it's not random, right? I mean, that's the other part.
Any other questions? If not, I propose we move on. Thank you so much, Felix, for staying up.
Sure, thanks.
us.
Yeah, it's interesting.
Yeah.
Interesting enough so I could stay awake.
So our next speaker is not Florence Marty, but Victor Rousseau. Is that correct? And somebody has to help you with this. Thank you. Are you a postdoc with Benoit? And Victor is going to talk about consistency of a space geodetic observations-based Earth energy imbalance estimate with various estimates from the scientific community. And I think we're ready. Take it away.
Indeed. So as you introduced me, yes, I will represent Florence Marty. I'm Victor Rousseau. I work at Magellan Toulouse, and I will present the result about the comparison of the geodetic Earth energy imbalance estimate with various estimates from the scientific community, which was done in the framework of the GWEX EI assessment. But first, let's talk about the new geodetic, space geodetic product we developed at Lagos Magellan in the framework of a project supported by ESA, CNES, and CNRS. As you may all know, the ocean absorbs 91% of the excess energy stored by the Earth system. So the ocean heat content is a very good proxy to estimate the Earth energy imbalance. From a community effort published in Messignac et al. 2019, they depicted several approaches to estimate the Earth's energy imbalance, and with their advantages and disadvantages, and among them, the space geodetic using data, altimetry data and gravimetry data has several advantages. Among these advantages, it has a really good spatial coverage over a large period, and it's a really highly mature data due to altimetry and gravimetry maturity. So the space geodetic approach is a potential candidate to meet the Earth energy imbalance accuracy requirements, which are of 0.1 watt square meter on the long-term mean for timescale typically superior at 10 years. The space geodetic approach was already published by in Marty et al. 2022. It relies on the sea level budget equation. And as it was already said by Anne Barnou and Felix, the total sea level is decomposed in the ocean mass component, thermospheric component, and allosteric component. The total sea level is derived from altimetry measurement. The mass component is derived from gravimetry measurement, and the allosteric is chosen to be neglected at a global scale. So we are able to derive the thermospheric component, and then the ocean heat content change is obtained by dividing the thermospheric sea level change by the integrated expansion efficiency of heat coefficient, which is derived from the in situ product and taken as constant over time. Then we are able to derive the global OHC change by summing the regional grids of the ocean heat content change, and then we can derive the Earth energy imbalance by dividing the derivative of the global OHC by alpha, which is the fraction of energy entering into the ocean. As we want to look for variation of the Earth energy imbalance with a really good accuracy, we have put much effort and energy into the uncertainty estimation. This uncertainty estimation is based on the covariance matrix approach. We are able to propagate the uncertainty from the sea level and ocean mass down towards the Earth energy imbalance. From the covariance matrix, we are able to derive the trend, the uncertainties on the trend, mean, and acceleration. And Michaela Blanc and Alejandro Blasquez will further talk about how we derive the sea level uncertainty and ocean mass uncertainties and their relative contribution to the Earth energy imbalance uncertainties. So now let's take a look to on the upper slide to the regional grids and the trend of the component of the sea level. As you can see, we are removing the manometric sea level grids to the sea level grids in the first step, and then dividing it by the time constant integrated expansion efficiency of it. And then we are able to derive the ocean heat content grids, and you can see the regional grids, their trends on the bottom right. And as you can see, there is a global warming of the ocean on most of the region over the globe. From this, we are able to derive the results at global scales by summing the regional grids. The space geodetic global OHC is computed over the full period of 1993 to 2022. We are able, as you can see, you have the red curve, which is showing the global OHC with its standard uncertainty, and we are able to derive the linear trend, which show an ocean heat uptake of 0.75 watt per square meter at a 90% confidence level, and also an acceleration of 0.13 watt per square meter per decade. As you can note, our best estimate is not at the center of the envelope, and you will have to wait for Alejandro Blasquez's presentation for more details about this. Then we are able to derive the space geodetics Earth energy imbalance on the full period. We are taking the derivative of the global OHC and filtering out for timescale below 3 years to remove out the internal variability due to ocean atmosphere exchanges. We derive the mean of the EEI, which is 0.83 watt per square meter, which is confident at a 90% confidence level, and the trend, which is 0.3 watt per square meter per year. Sorry, I forgot this. And the really good point is that now there is a really good correlation with the CRS, onto which we have applied a 12 months running mean. This correlation is of 0.70. And on the same period, which is from 2000 to 2022, the space geodetic trend is equivalent to the one of CRS, which is of 0.04 watt per square meter per year. So this space geodetic product was included in the framework of the GWEX EI assessment. We compared it to one other space geodetic products, which is the GPL1, 6 in situ products, and 1 reanalysis product. In the framework of this study, we estimated the Earth energy imbalance the same way as we did in the space geodetic approach. It means that we started from the global OHC to have an homogeneous estimation of the Earth energy imbalance, and it was the same for the uncertainties. We are then able to have a rigorous comparison of Earth energy imbalance estimate, and also with CRS, which is a reference in terms of trend and time variation. Then at the end, it allowed to draw up requirements for the future Earth energy imbalance assessment. All the products are available on the website, which is GWEX EI, and on this website, you have the projects which are available as annual global OHC time series on different periods. So we study them on the same period, which is from 2005 to 2018. Uncertainties are estimated the same way from global OHC covariance matrix. And if they are not available, we transform the standard deviation into diagonal covariance matrix. And for some products which were not representative of the full ocean depths, we added a deep ocean contribution characterized by the uncertainty of Perkin and Johnson. As you can see below, you have the representation of all the global OHC. In red, you have the space geodetic data, which are represented by dotted lines, and you have in blue the reanalysis data, and the other one are in situ data. As you can see, all the product detect the accumulation of heat into the ocean, and are ranging from 0.54 for EN4 up to 0.87 for ISAS-21 and Lagos Magellan. And they are all confident within their confidence level of 90%. Afterward, we are able to derive the Earth energy imbalance the same way for each product from annual global OHC time series. We compute the derivative and divide by the coefficient alpha, and we apply a low-pass filter as we explained before. The Earth energy imbalance mean of the different centers are represented here on the box plot. You get in red the box plot which represent space geodetic data, in cyan the reanalysis data, and in dark blue it is Ceres whose John Lehman solution is anchored to. And you get in gray the in situ products. As you can see, the EI mean of different different centers, if we do not consider the one which do not have associated uncertainties, are consistent within the 90% confidence level. Finally, we can show the results in terms of trends. As you can see, there is exactly the same disposition. We have 4 EI trends which are significant within the 16-84% confidence interval, and 2 EEI trends which are significant within the 19% confidence level to Ceres reference. Finally, as we said, Ceres is also the reference in terms of time variation. So now we want to see how the GWEX products match Ceres reference. So we show the Taylor diagram, which is on the right, and you can see on the x-axis line the dark blue star, which represents Ceres reference datasets, and then you have all the products, and the closest in terms of distance a product is from Ceres reference dataset, the closer it is from Ceres in terms of time variation. With this criteria, we can see that CNR-ISMA, PMLC, YAP, Lagos Magellan, and EN4 represent the best performance. Finally, we have put in evidence a good agreement of the space geodetic Earth energy indicator in terms of mean with the Earth energy imbalance from Argo products, but also in terms of interannual variation and trend with the Earth energy imbalance derived from Ceres. To go further for the GWEX EI assessment, we would like to have the product at monthly timescale, because currently we are limited at annual timescales, and to provide a better characterization of uncertainty with time-correlated errors, so we could aggregate the uncertainties at annual timescale if we do not have monthly series. And afterward, we would like to provide homogeneous physical content between the EI derived from Ceres and from OHC for timescale in less than 2 years. Concerning the Lagos Magellan product, we would like to go further for the space geodetic ocean uptake. This will go by improving the effective temporal resolution, as we are currently limited at 3 years to date, as you can see below, but it's currently matching a 1-year filtering Ceres product. And this will go by improving the consistency between altimetry and gravimetry data, but also by reducing the effect due to internal oceanic variability. And this will be kind of my last conclusive slide. You can go check through our product, which is available on Audatis Aviso portal, which link is indicated here, with a different version of the product are available with their technical documents, and in particular, the last version was published last month in April 2023. Thank you very much for your attention. If you have questions, I'm open to them.
Thank you, Victor. That was awesome. Any questions from the audience? Li Jing?
No, it's really interesting. You have an error bar that is not centered, it's not a Gaussian distribution. Really good. So, have you any analysis on? I noticed that this morning also Norman mentioned that 2016 is really special because all the heat content has negative values, and it is the bar, error bar is higher in the negative part. So any analysis on this kind of asymmetry?
Currently, we didn't check to that, but it could be due to the fact of maybe filtering maybe too much the data at 3 years, and that's it.
Any more questions? So how did you define that the 3-year filter is the best option? Did you try different filters?
Yes, we check for different filters, and actually we could not go below 3 years because otherwise there were too much variability in the product. So this was currently this is the best compromise we have. Yes.
May I also ask a question on that? This is Felix.
Yeah, sure, go on.
The plot that's here, the series data has not been filtered with the 3-year smoothing, or has it? So I suspect if you did that, right, I mean, it would actually be more muted. And our data, JPL, I mean, I think we ran into the same issue that the space geodetic has a lot of variability, in particular in the early parts of the period. So if you were to filter that with 3 years, it should also agree better in your Taylor diagram that you showed with your estimate. Can I just ask one other question real quick? You showed a map of geodetic heat content, if I caught that right. How do you account for halosteric effects in that conversion?
Like we didn't remove the halosteric component from the steric component derived from altimetry and gravimetry. Like it was, we didn't remove it, so we neglect this part at global scale, but not at regional scale. Yes, indeed. Yes.
Sorry, at regional scale, you do not neglect it?
Yes, indeed. We correct for it at regional scale, but not at the global scale.
And where does that information come from? From Argo or a model?
Yeah, it comes from a combination of two products, which are ISAS-20 and EN4 from the Levitus one for the deep Argo contribution.
Okay, thank you.
Can I just very brief comment that we also try to estimate the let's say perfect time scale that fits series and ocean heat content data through cross wavelet analysis, and we also end up with 3 years as a peak of the spectrum. So it's nice to see that there is consistency in this estimate with different methods.
Nice.
Can I add just a comment? It's for you, Maya, and for Felix. So I think one thing is which is interesting. If you go below, if you go below 3 years and you between 1 month and 2 years with the geodetic data, we find large variations. Some of it can be due to exchanges between ocean and atmosphere, intrinsic variability of the ocean, but some of it we just suspect it's like spurious, which is coming from aliasing when we combine gravimetry and altimetry. And we have to solve for this. But what I find interesting in this comparison, where CIRES, if you in this plot, if you apply the same filtering to CIRES, you increase the correlation with the geodetic measurements. But what is interesting by not applying the filtering is that you see that CIRES is indicating that probably between 1 year and 3 years, there is not so many signals. And I think that's very interesting, at least for the geodetic approach and for sea level and also GRACE. That means that we are not dominating how we are combining GRACE and altimetry at those timescales. And I think CIRES is providing us a very interesting constraint here. We need to understand what's happening between a few months and 3 years in altimetry and GRACE in a consistent way. And that's probably what that means, if that is true, is that we probably have issues also on the sea level budget at those timescales. And that's the reason why, Norman, I was asking for uncertainty, for correlation and uncertainties, because it would provide us a constraint on our own work for sea level budget on those timescales. Because that's very interesting that your curve doesn't show anything between 1 and 3 years, because we fit very well with our estimate on 3 years.
Thank you. Any more comments? Online? Okay. So I believe we can take a coffee break. And we are a little bit behind by 17 minutes. Shall we shorten the coffee break or no? When do we return?
By 5 minutes, maybe?
By 5 minutes. I can't do the math. So we're back at, shall we say by 5? Or what time?
So let's say by 5,
Yeah?
What time was it?
The break was supposed to start at 20 past and go till 50.
It's not much. It's just, well,
So let's say we come by 5.
5?
Fine.
Yeah,
Well,
let's say 5.
Let's reconvene at 5 p.m.
fine. So 10 minutes behind. Back.
Okay, well.
Two on space techniques to measure the EI. And our first speaker is Michael Ablin, with the title In Calculating and Propagating Uncertainties from Space Altimetry Measurements to the Earth Energy Imbalance. And we are ready.
Okay, so thank you, Maria, for introducing my talks. So thank you for all my co-authors from Toulouse, Magellan, Lagos, and CLS, and also all the co-authors involved in altimetry for a lot of years and not cited here. So just let me introduce how the mean sea level data record is calculated from the altimetry. Just a reminder. So a lot of you are already aware of this calculation. So these figures shows the altimeter space altimeter constellation from the beginning of the altimetry era. In red, you have red or pink, you have the past altimeter missions. In orange, the current altimeter mission, and in yellow, the future altimeter missions. And just some figures to illustrate the space altimeter mission. We have from 90, we have 19 space altimeter missions from 1991. And I would just would like to say that currently there are more than 100 engineers which are involved in the monitoring and the improvement of the altimetry data. In here, I have indicated that among all these altimeter missions, some of them are so-called the reference mission. It is a mission used for to build the mean sea level climate data record, because these missions are all on the same orbits, and they are also so-called tandem phase between the mission to link this altimeter mission together very accurately, and this mission also are very stable. Just to remind you how the sea surface height is derived from altimetry processing. It is derived from the difference between the position of the satellite, between the orbit, and between the range, the distance between the satellite and the surface of the ocean measured by the radar instruments. And we have also to correct this sea surface height by different corrections. Among these corrections, there's the atmospherical correction coming from the ionosphere, but also from the troposphere, which is derived from other instruments that are onboarded to the altimeter, space altimeter missions. And it is microwave radiometer. We have also to correct the effect of the sea state, which is more an altimeter correction also. And we have also to correct from the other geophysical correction as the tides, the ocean tides that we do not we like to measure when we would like to deduce geostrophical circulation in the oceans, and or also correction as the global isostatic adjustment. The things important to say is these data are very precise at 1 Hertz, between 2 and 2.5 centimeter within a 90 confidence percent confidence level. The random measurement errors are linked to the sea state, to the effect of a long wave swell for a system, for instance, and how also the radar pulse interact with the ocean surface. We have also a very good accuracy at 1 Hertz. So accuracy is the systematic errors that we have on the altimeter measurement at 1 Hertz. And this the level of accuracy is between 2.5 and 3.5 centimeters, depending on the altimeter mission, in the same confidence level interval. These systematic errors are coming from mainly from the orbit determination and the wet troposphere corrections. So from this altimeter constellation, we are able to derive the daily sea level grids with a very good height resolution at 4 degrees, 4 per 4 degrees over from January 1993 until now. And from these daily grids, we are able to derive the regional mean sea level trends. And as you can see here, these trends are positive almost everywhere in the ocean, with large patterns that between 0 and 10 millimeter period, which are very well correlated with the steric sea level components. And from this sea level grids, also we are able to derive the global mean sea level time series over this 30 years period. And this series is very close to the reference missions, TOPEX Poseidon, and from 1993 to 2002, JSON-1 from 2002 to 2008, JSON-2 from 2008 to 2016, and JSON-3. And now it's not plotted on this figure. We have recently moved on Sentinel-6 reference missions. And as you can see here, and as you know, the global mean sea level is increases at with on average at a rate of 3.3 millimeter per year, and it also accelerated at a rate of 0.12 millimeter per square year. And I just would like to pay your attention on the uncertainty on this figure on the trend and this rate on the trend and the acceleration, because we have very accurate result with an uncertainty of 0 plus or minus 0.1 millimeter per year for the trends and 0.05 millimeter per square year for the acceleration in a confidence level of 90%. So this is in the second part of my talk. I just would like to give you more details on how we obtain these uncertainties. I just forgot to say that we have also provide and calculate these uncertainties also at regional scales. It is the work of Pierre Prandy, and it will be described in more detail in his talk just after. Just in order to calculate the uncertainties of the mean sea level data records, we have firstly identified the main source of uncertainties in the altimetry data record. These sources are identified in this table here. There are errors which are very high frequency error due to the precise orbit determination, to the altimeter parameter, to the geophysical correction. It could be considered as a noise. We have also a main source of error which is due to the problem of stability of the wet troposphere corrections. We have also another quite important source of uncertainty, but mainly at regional scale, not too much at global scale, which is the precise orbit determination stability, which and also we have a source of uncertainty to link the altimeter mission together, but the source of uncertainty is now very low thanks to the tandem phase that we have between the reference missions. We have also a source of uncertainties due to the geophysical correction, as the global the glacial isostatic adjustment, and also due to some stability of altimeter parameter, but it is mainly at the beginning of the altimetry era on Topex Poseidon. All these sources of uncertainty were identified by comparing altimeter missions together, and we were able to detect potential anomaly in the altimeter parameters and waves and winds parameters and sea level anomaly, and then calculate uncertainties. We have also compared the wet troposphere correction from different microwave radiometers, thanks to the altimeter the large altimeter constellations that we have, and also comparing this correction with models. We have also compared the orbit solution from different centers, CNES, GPL, GSFC, GFX, etc. We have also identified the source of uncertainties, compared altimeter data with in-situ data as tail gauge, the Argo temperature and salinity profiles, for instance, and also the uncertainties in geophysical correction were deduced from different models, as for the ocean tides or the global isostatic adjustment. And then, once the source of uncertainties were identified, were models their behavior. 5 minutes, okay. Okay, I have to go quick. And we have identified this type of uncertainties with different approach plotted here. I skip this slide quite quickly because Pierre will give you more details. And the last step was to provide these uncertainties, the value of these uncertainties. And once from this table, from this global mean sea level uncertainty budget, we are able to calculate the variance covariance matrix of these errors over all the altimetry era. And thanks to an adapted mathematical formalisms, we are able to calculate the trends uncertainty at any period of times and for any period length, and also the uncertainties in the acceleration. Pierre will also provide more details on this figure. And an important thing also is uncertainties have been assessed by different ways. They have been assessed comparing all the altimeter missions together. It is represented in this figure here also, where the global mean sea level has been plotted for different missions, not only the reference mission, but also the complementary altimeter missions. We have also assessed these uncertainties by comparing this mean sea level uncertainties with independent data as tail gauge. Here you can see the differences between the global mean sea level, the mean sea level data record interpolated at tail gauge record, tail gauge location, and with the tail gauge data, and with the sea level budget approach explained
just before by Anne, and also by comparing this data by other space data. And recently, Luzanga et al. Compare the regional sea level trends provided by ISAT-2 with JSON-3, and ISAT-2 is another technique based on LIDAR. So now, once we know this uncertainty, we would like to propagate them until the Earth energy imbalance, our geodetic Earth energy imbalance. So, as introduced by Victor, the main principle of this propagation is based on the propagation of the variance-covariance matrix from the input data, from the global mean sea level provided by altimetry data, and from the gravimetry data. And at each step of our process, we are able to calculate the matrix of variance covariance of the uncertainties, and to deduce and to calculate the uncertainties in trends, here for the global mean sea level, and then for the global ocean mass. This will be presented by Alejandro just after my talk. And for the ocean heat content at global scales, and finally for the mean of the Earth's energy imbalance. And then we obtain this plot presented by Victor, but here only focus on the Grace and Grace-Folleron era, where we are able from this variance covariance matrix able to provide the envelope of uncertainties of the Earth's energy imbalance, and also the interval of confidence that is not centered here, as explained by Victor and Alejandro. And then we have also able to provide the Earth's energy imbalance, the uncertainty of Earth's energy mean at any period of time. It is in the x-axis, and for any period length in the y-axis. On the left panel, it is for all the uncertainties of our geodetic Earth energy imbalance, and on the right panel, it is only considering the altimetry uncertainties. And if you look at the top of these two diagrams, you can get the uncertainties over all the period. It is about 0.27 watt per square meter in a 90 confidence level for the Earth energy imbalance. And considering only the altimetry uncertainties, the contribution is 0.40 watt per square meters. But we can do the same for other time scales, and here at 5 years, for instance. And a way to assess this Earth energy imbalance uncertainty is to compare the space geodetic Earth energy balance with independent Earth energy imbalance data coming from our reference here is Ceres, and this is exactly the plot showed by Victor just before, and you can see that the Ceres Earth energy imbalance is included in our uncertainty envelope at 1 sigma a year. This is a way to assess our uncertainty. So in conclusion, one of the main objectives of my talk this afternoon was to show you the maturity of the mean sea level altimetry record after 30 years of intense work of the altimetry community to assess the altimeter data. We have almost a worldwide coverage, accepted at very high latitude, a very low rate of missing or corrupted data, less than 44% in open ocean. We have robust validation against independent data as tail gauges. We have advanced estimation of uncertainties, including temporal correlation of errors. And we have also a very high stability of the mean sea level data records, close to 0.3 millimeter per year on time scales of 20 years. And thanks to our formalisms to propagate the uncertainties in the Earth energy imbalance, we are able to propagate only the altimetry uncertainties in our Earth energy imbalances derived from space geodetic data. just in perspective, also, despite their very good accuracy, we have to continue to improve altimetry data. It's necessary to get closer the sea level stability requirements. For the moment, we are in the column in black in the middle. It is the performance that we have in terms of stability for the mean sea level records at global scale and regional scales. But in the next decade, we have to improve these performances, and this is explained in a paper in preparation under review by Benoît Messniak to answer different scientific questions to estimate the Earth's energy imbalance. And the work is ongoing, and currently we have a project at ESA called ASALSU, where we work with meteorology experts from NPL. And one of the objectives of this project is to propagate the altimetry uncertainty from the elementary altimeter measurement from level 0, from the radar equations, until the sea level records. And this work is quite well advanced. We have already presented the result in different meetings. This is just an illustration of a poster from the NPL team here, where we propagate these uncertainties. And we have already identified some scenario where we would like to improve each source of uncertainties on our current mean sea level data records to get closer the 0.1 millimeter per year uncertainties in trends at global scales. That's all. If you have any question, you're welcome.
Thank you so much. I learned a lot. Do we have questions in the audience? Okay, well, maybe we talk later some more. Thank you. Okay, let's move on to your colleague. Oh, we have to switch slides.
I'll try.
Okay.
We'll try. No, you're the expert.
Okay. Upcoming talk is by Alejandro Blasquez, From the Uncertainties in the Barostatic Sea Level Rise to Uncertainty in the Geodetic Estimate of the Earth's Energy Imbalance. So I guess we're now moving to uncertainties in the ocean mass component.
Tu peux prendre vite, hein? Okay.
Hi, everyone. I'm Alejandro Blasquez, working at Lagos and CNES at Toulouse. So I guess you already know about the barostatic sea level rise. It's also called the ocean mass, and I'm not going into the details of how we use it to compute the Earth energy imbalance, because you already heard this out 4 or 5 times today. So just same idea as the gravimetry missions. This is the missions about the gravimetry. There are people that said that the gravimetry observation started with the Sputnik. I will skip the part before the year 2000. And there was at the beginning was the gravity field, which was not temporal, time variable gravity field with Sham and Gauss. And then after the arrival of Grace and Grace follow on, we start analyzing the time variable gravity field.
I'm sorry to interrupt. We cannot
Yeah.
see the slides online.
Okay, thanks.
That's weird.
Yes.
Hold on. Okay. Can you see it now, Felix?
Yes, thank you.
Thanks. So, and just to say that the precision we already have is about 1 millimeter at 400 kilometers. This is in geoid height, which is quite more or less relative to the equivalent water height we will be. And in the next years, the mass change mission in the US and DLR side, and also NGDM has proven are on the good way. And there are also some studies from the European Union for post-Carioca mission in the next 20 years. So how works the gravity missions, the GRACE-like gravity missions? There are a couple of satellites up to of around 480 kilometers height. What follows at 250 kilometers, and what we measure is the inter-satellite link, which is measured nowadays with a precision around 50 nanometers. And then with the use of the accelerometers and the star tracker and the GPS measures, we inverse to obtain the gravity, which is called the gravity field. Wait a minute, because I don't see half of the screen, sorry. So, and then we also use the ancillary data from models to the ocean, the atmospheric de-icing. And this inversion process is done in the several processing centers, and what they come out is with the gravity GRACE L2 solution, which is the gravity field. But if we want to use this to analyze the water mass transport studies, we need first to apply some corrections to the L2 limitations, which are the add of a geocenter motion, which is not observed by GRACE missions. We have also to improve the Earth obliqueness, as is bad resolved with this kind of mission, and then correct for the noise and the leakage and give effects. But as far as we are interested in the water mass transport, we also need to correct for the solid Earth changes that affects the gravity, but are not due to the water mass changes, which includes the glacial statistical adjustment, GEA correction, the correction for the earthquakes, pole tide correction, among others. So what we decided at CNES was to create an ensemble to try to assess the known of these L2 products and the post-processing possibilities. And by choosing the state-of-the-art of these post-processing and L2 products, we try to assess the uncertainty in the water mass anomalies. So here I just listed all the products we are using, and we're not going into the details for the moment, but there are like 5 different L2 products, 2 geocenter motion, 3 C20, which is the Earth obliqueness, 2 JA models, and 2 kind of filtering. And then on the right side, there are the other post-processing parameters that we are applying, but we are not, today we are not including different solutions in the ensemble. So how do we validate gravity-based estimate? Here I show you the mass change from Greenland and Antarctica from some community papers in the last years, the IMB project. And this is a intercomparison of different methods, which includes the altimetry, the input-output method, and the gravimetry to estimate the mass change in the ice sheets in Greenland and then in Antarctica. So each figure corresponds to a different product. So you can see that there are like 50 different kind of solutions. And what we've done is to superpose our ensemble solution in this solution. So this helps us to analyze the uncertainty we know. And for example, if we focus on the West Antarctica, we see that our uncertainty includes all the GRACE products. And the uncertainties are quite realistic. But for example, in the East Antarctica, our uncertainties are really huge. And this is due because there are big differences in the JA models. And it happens that most of the JA products use the same correction. So all the gravimetry timelines, or the gravimetry estimates are in agreement. But then we see that the gravimetry estimates are not so in agreement with the input-output method. But thanks to our ensemble and the fact that we cover a lot of different post-processing solutions, this is included, and there's a better correlation. Another way to compare ourselves is to do this same kind of analysis, but for the trends. So here in the figures, we have the error bars correspond to the different public estimates for the publication for the last years. And the gray shadow areas correspond to the trend uncertainty distribution from our ensemble. So these kind of results give us confidence in the way we estimate this gravity-based estimate. And then another way to observe this is more or less is the same is the global water budget, which is, in fact, as Felix said before, GRACE observes the whole Earth. So the water is just transferred from one stock to the other. And in this figure, we see how the ocean mass is increasing and how this came from the contribution from Greenland, glaciers, Antarctica, or the atmosphere. And it helps to understand that if we want, for example, this morning we was discussing about an extra contribution from the terrestrial water storage, from the land precipitation minus evaporation, it could be something in the error bar that we provide here. Okay, it's not. And another way to validate this product is that we also compare to the mass change from the lakes. So in the figure, I'm comparing the trends we obtained with the GRACE estimates and the residual ones we correct for the lakes mass change from altimetry and the glacier from imagery. So now if we focus on the barystatic sea level, this is in the figure, we see the barystatic sea level, and the small box correspond to the trend distribution of this ensemble. So in the figure, I also added the CSR and GPL mass consolutions, and we see that they are in a good agreement, all the gravity-based products, which gives us also confidence in the result. And there's something that is quite surprising, is that the distribution is far from Gaussian. And in fact, there are 4 distribution in the same distribution. So I just analyze why this is happening. And we see that all of uncertainty is coming from the different products in the geocenter and the GIA models we use. And in fact, our ensemble is not a continuous product, continuous distribution of products. There are like 4 different products which correspond to the combination of the geocenter from Le Moine or the TN13 and the GIA from ICG or Caron. And each one corresponds to one of the figures. So now let's have a look on this post-processing correction. Sorry, before that, I just looked Victor. So that's why we decided not to use the mean in our Earth energy imbalance productor. And we are using only our best estimate. So if we focus on the JA model, we observe that we are currently using 2 different JA models, and that there are some difference, about 0.15 millimeters in the sea level rise. So that is, as JI only applies to the trends, that explain the difference between the 2 different, in the small box, between the blue, the dark blue and the light blue, and between yellow and red distributions. And then if we focus on the geocenter and the certainty, the geocenter, for those who doesn't know, is also referred as the first degree of the Stokes coefficient, but it's related to the movement between the center of mass of the Earth and the center of the solid Earth, which includes the envelope fluid, which means the ocean and the atmosphere. And as all the satellites turn around the center of masses, we don't observe this satellite, so we don't observe this geocenter motion, and we need to use it from another sources. And here I'm using the 2 solutions we consider. The one from Le Moine, which is computed using SLR, satellite laser ranging satellites, and the one computed by the SAN method, which is actually the technical note 13, which is the official one. And this one, as you may see in the figure, presents an important trend around the Z-axis and also around the X-axis. And it's computed using the ECHO model to obtain an ocean mass that fits our model, or the ocean model. Although on the other side, the Lemoine method is completely independent, but it results that using the Lemoine method, we are far from closing the sea level budget. So there's something we need to address there. And then here I just saw a comparison I've done with different products from this geocenter to show that the uncertainty is quite huge. I only include 2 models in our ensemble because the other are not available for the full grace period. But there is actually an important uncertainty around 0.5 millimeters in the Z-axis, which is currently the limitation of the knowledge of the geocenter. So this difference in the X-axis and the Z-axis explain the difference between the blue figures and the red and yellow ones, explaining most of the uncertainty in our barostatic sea level. So as Michael showed before, using this ensemble method, we are also able to derive these trend maps and the standard deviation at 90% confidence level. And we see that for trends far with length of period over 10 years, the uncertainty is quite stable. This is mainly due because the uncertainty in the geocenter is stable and it's increase. It doesn't increase with time. So as a conclusion, I would say that the maturity of the gravity-based barostatic sea levels record after 21 years, it presents a worldwide coverage. Of course, it has its limitation around the coastal regions, and there's a lot of work that has been done in the past years. As Felix showed before, each time there's a new release, the uncertainties comes lower. There's a very low rate of missing data. It's like 80% of monthly availables, knowing that there's only a small gap of 11 months between grace and grace follow-on, and we hope there will be no more gaps in the future. And there's robust validation against independent data, and the estimation of the uncertainties is reliable as it gives uncertainties which are in line with the uncertainties we obtain for other independent data. The new perspective for the uncertainty reduction is not so optimistic or realistic as Michael says for the altimetry part, but we hope in the future there will be a good increase, a good reduction in uncertainties with the use of the new ITRF model 2020, which includes an annual cycle for the geocenter motion. And there's also a future mission, which is called Genesis. It has been proven in the last year from the European Union. And the idea is to co-localize different observing system to reduce the uncertainty in the geocenter motion. And as I said before, future missions are on the way, and there's several years to come from reducing the uncertainty. And just to finish, I take the same table as Michael showed before, and I added the gravity uncertainty contribution at 90% confidence level for the long-term trends of 20 years and for the interannual trend of 5 years. And we see that roughly the gravity uncertainty dominates the long-term trends, and which 0.23 watt per square meters. And this, as we said before, is mainly due to the geocenter and the terrestrial water storage, geocenter and the area. And that's all. Thanks.
Thank you so much. Any questions here or online? No. Okay. I guess we can move on.
Yes.
And discuss later. Thank you. With that, I think we're moving into a virtual presentation by Bernd Übing. Bernd, are you there?
Yes, can you hear me?
Yes, we can hear you.
I try to share my screen.
Okay, we will allow you that in a second.
Okay, I'll wait.
It should work now.
Okay.
And your talk is about reconciling and improving formulations for thermodynamics and conservation principles in Earth system models. Is that correct? That doesn't make sense. Oh, it's wrong. There's the correct title.
Okay, can you
Thank
see
you.
my presentation full screen now?
Yes.
Okay, great. So I just start. Thank you for the kind introduction. So what I'm going to talk about is our approach for assessing the Earth's energy imbalance, or better to say the ocean heat uptake from a combination of GRACE and multi-mission altimetry. This is more or less an expansion with respect to the standard method that is applied, where you use this global factor for converting steric trends. And I think we have seen this a lot today. So we have the Earth energy budget, where we find an imbalance at the top of the atmosphere on the order of 0.6 to 0.8 watt per square meters per year, sometimes even a little bit larger, depending on the time period that you're looking at. And about 90% of this excess heat is going into the ocean and then leading to a volumetric or steric expansion of the water column, and so steric sea level rise. And the idea is to measure this steric sea level rise from a combination of the GRACE and GRACE follow-on data with satellite altimetry, where the altimetry measures the total effect, so the sum of all individual contributions, and the GRACE measures the ocean mass changes. And from that, we can then induce the steric changes. So this basically requires the construction of a sea level budget, as we have heard already before. So I don't have to explain this in detail. With the approach we use here in Bonn, we are using a global fingerprint inversion. The idea is that we have, on the one hand, our input data, so the altimetry data, the GRACE data. This could also be additionally Argo data, but in this talk, I'm limiting the input data to the GRACE and altimetry. And on the other hand, we have auxiliary data, so prior information on how the sea level will change depending on certain variations, for example, in a basin in Greenland. So how, when the mass changes in that basin, how will the sea level change? And this then leads to, I don't know if you can see the mouse, to this gravitational elastic, rotationally consistent, spatially sea level patterns, which are also called fingerprints. And we, based on the prior information, we have quite a lot of these. So for the steric, this would be derived from an ocean model, where we partition the, for example, steric sea level change into empirical orthogonal functions and corresponding principal components, and then use the spatial information in the empirical orthogonal functions and fit them together with the mass fingerprints to the input data in order to estimate monthly scaling factors for each individual fingerprint. And from the combination with of the scaling factor with the corresponding fingerprints, one can then reconstruct either total sea level change or individual sub-contributions, depending on the subset of fingerprints that you choose. And this then allows to either derive global or regional sea level budgets, since we always reconstruct the sea level of each individual component on a global map. And with respect to the last talk, I quickly want to mention that one benefit of this approach is also that we do not have to account for the degree 1 differences in that much, because we basically co-estimate this from the combination of GRACE and altimetry, since altimetry can see the degree 1 changes, but GRACE can't. But from the combination, we are able to also derive information on the degree 1, which I will not show here, but it fits quite well to what other people find. So in addition, some have been maybe to EGU, where I also presented this. I used a slightly different inversion than I'm going to use today. So for the EGU, I limited the input data of altimetry to the JSON nominal emissions. However, when I thought about this after EGU, I thought it makes much more sense to utilize as much altimetry as we can, because especially for the comparison with the CERES data, where we have global coverage, it makes much more sense to include all the other missions, which give a much better spatial temporal coverage and also information in higher latitude regions. So in my opinion, this makes more sense in combination with data sets like CERES. So when we look at the sea level budget here, we can see that the budget is closed quite nicely. So the residual is in the order of 0.05 millimeters per year, which is quite nice. And actually today, after the talk from Felix, I thought about what he mentioned about that the sampling matters, and I totally agree with this, because when we look at the same budget evaluated once on the altimetry positions, like I did here, which is more or less consistent with how the global mean is computed from Steve Nerem's paper in 2018. When we do the same computations on the grid, we can see some differences, and we also see a slightly larger residual component. But when we decompose the residuals again into EUFs, we basically only find some ocean dynamic signals, and based on the explained variances shown here on the right, I think that we can conclude that for the inversion, we do not have any significant signal left in the residuals, despite the ocean dynamics, which are not explicitly modeled. And in the following, I will use the gridded steric data for the following analysis with respect to ocean heat content and Earth energy imbalance. So first, a quick recap on the standard approach, where which is basically based on the paper by Russell et al. in 2000, where an expansion coefficient of heat is computed by dividing the derivative of specific volume with respect to temperature by the specific heat capacity, and this can then be converted into units of meters per yottajoule, which then again can be converted to the factor that most people probably know of 0.52 watt per square meter per millimeter per year, where you can convert a steric sea level change to a corresponding change in ocean heat content, or in this case, ocean heat uptake. And if we look at these coefficients spatially, as we have already also seen earlier, they are not spatially constant. There is a dependence on depth and also on location. And what we can see that especially in the higher latitudes, there is we find quite larger expansion efficiency coefficients. However, due to so if you would apply this approach regionally, due to the smaller area, this does not have a too large impact. So with respect to our expansion of the standard method, I want to, or we had the idea to utilize the spatial information that we have available in the inversion. So we have these steric fingerprints. We have the original principal components derived by the model, and we have the estimated ones derived from the inversion approach. So one could see the inversion as or the inversion output as a rescaling of the input model, which is in this case ORAS5. And the idea is to utilize this spatial information and project the model ocean heat content, which we get from the same model, onto the same basis, so the same fingerprints, in order to derive the model principal components relative to the steric spatial patterns. So this assumes that the change so that the steric sea level change and the variation in ocean heat content is pretty similar, which of course is not true 100%, but we think it's a much better assumption than simply taking one global factor for converting a steric sea level trend. And in the next step, we then rescale this modeled ocean heat content by using by dividing the RMS of the fitted steric principal components and the model components, and multiplying this to the projected ocean heat content modes, principal components, sorry, in order to derive observation-based rescaled ocean heat content principal components, which can then be again combined with the steric or with the basis or the steric fingerprints or EOFs, in order to derive monthly spatial maps of ocean heat content changes driven by the combination of GRACE and altimetry data. And these can then be, of course, further analyzed with respect to global and regional ocean heat content variations. So coming to the results, first I want to look at the global results in comparison also with the Ceres data. Here we can see the Ceres in black in the background. So, and the ORAS5 model in green, and the two data-driven approaches. So I called the standard approach here the epsilon scaling approach, and our EOF-based rescaling show a significantly smaller trend here, which we will also see later in the ocean heat update estimates, compared to what the original model data said. And at the same time, we also find a smaller contribution than, or a smaller trend compared to the Ceres data. When we look at this on regional scales, since we have these maps of these monthly maps, we can also do the same analysis on regional scales. We can see quite a difference in the Atlantic Ocean. So that probably the major difference comes from the Atlantic Ocean compared to the model, where the model data shows a much larger trend compared to the data-driven methods. Slightly similar in the Pacific Ocean, but not as strong as in the Atlantic Ocean. And in the Indian Ocean, we interestingly find a different anticyclic or an anticyclic behavior of the epsilon scaling or the scaling approach compared to what the model and also the rescaled model basically say. So this also will lead to an impact on the derived ocean heat uptake. And I forgot to mention this on the last slide. So I limit the investigations here to the time period between 2005 and end of 2015. On the one hand, due to the lack of Argo coverage, which affects the model data before 2005. And after 2015, as we have already seen today, we have some impacts from potential biases in the JSON data or biases or trends in the Argo and also in the then model-driven data. And we also have the decline of the GRACE data and the gap between the GRACE missions. So to have a look at this later part, we first have to extend the inversion with more GRACE follow-on data in the future to have better databases for analysis here. So looking at the ocean heat uptake estimates, we can again compare on a global scale with CERES, where the top of atmosphere data is converted to ocean heat uptake by basically taking 90% of the value and also accounting for the larger area at the top of atmosphere. So it's basically the difference in area of the sphere. And this can then be compared to the EOF rescaling method, to the standard method, let's say, and to the model data. And what we can see is that the model ocean heat uptake is clearly larger than the one found with the CERES data, while the two data-driven methods show smaller estimates, where the standard approach, I think, fits pretty well to what was published in the paper by Marti et al. In 2022. And we can see that the model is clearly overestimating the contribution, or is seeing a much larger heat uptake in the Atlantic Ocean, which cannot be confirmed by both of the data methods, while we see a smaller contribution in the Indian Ocean, which explains most of the difference between the standard method and the EOF rescaling approach. But we also see a difference in the Arctic, where I think the larger values I showed early on an earlier slide play a significant role. And what we also have to keep in mind is that the CERES data are adjusted to selected ocean and ice and land heat storage estimates, as we have heard this morning. So depending on the bias adjustment of the CERES data, these values obviously will also change. And this brings me already to my conclusions. So I hope I was able to show that with our global fingerprint inversion, we are able to close the sea level budget quite well within less than 0.1 millimeter per year, depending on the sampling of the data. And from that, we are able to estimate ocean heat uptake in the order of 0.5 watt per square meter or 0.58 watt per square meter when we use the standard method. And this is quite close to what we find from the CERES data. As a reminder, if you remember my EGU presentation, if we only use the JSON data and evaluate only over the JSON domain, we get an estimate in around 0.6, 0.63 watt per square meters, which is closer to what we also find from CERES. And the major difference between the two data-driven methods is found in the Indian Ocean. And from the model data, we clearly find an overestimation to some extent in the Pacific, but mostly in the Atlantic Ocean for the heat distribution. And with that, I'm finished, and I'm happy to take some questions.
Thank you, Bernd. Questions in the audience? Benoit has a question.
Thank you, Bernd. I have a question about, I saw you have a very small ocean heat uptake in the Arctic Ocean. Can you comment on that? Did you expect that, and how come this is so close to zero?
If you look at the scale, so I made the scale the same as for all the other contributions. So if you reduce the scale, it's not that smooth, but it's quite small compared to the other oceans in this case. So if you would zoom in closer, it wouldn't be that smooth.
And I have another question. May I suggest, you know that the Southern Ocean is a hotspot for ocean heat uptake, and it's very important for many other climate studies, especially to constrain the ocean heat uptake efficiency. We know that many things are happening there. Maybe that would be a good idea to just to separate the Southern Ocean if you can.
Yeah, sure. That it's also something that I had in mind. So in the past, we always used these Pacific, Atlantic, and Indian Ocean basins, including the Southern Ocean. And for now, I did that for continuity and comparison with our old results. But you're right; it makes sense to separate the Southern Ocean as an additional basin.
Do I have more questions? Ah, I have a naive question. Maybe I missed it. But why is the Indian Ocean so difficult for the two scaling methods? That's where the largest discrepancy is.
That's a good question. If you think of the epsilon scaling, this is basically a rescaling of the steric sea level time series. So what is plotted here, and the ocean heat uptake seems to be phase shifted to this. So and one has to keep in mind that the inversion is not completely independent of the model. So we are kind of constrained to a certain extent what can be done based on the model basis of the fingerprints. So if we assume that the model is correct and the phase modulation of the model is correct, that would or it might indicate a delay between a certain delay in the ocean heat content and the steric, but I haven't taken a closer look at this.
Thank you.
Yeah, may I ask a quick question? I know you're.
Yes,
you're
go
running.
on.
Nice talk, Ben. You showed a map of the expansion efficiency. If you could skip to that real quick. There was a similar map shown earlier.
This one?
Yeah, on the left, this is what I would expect it to look like. Earlier in the talk after me, I'm sorry I didn't catch the name who gave that. That was, the map looked kind of inverted to that with the highest amplitudes in the polar regions. So Benoit, if you have time, you might want to look at that and discuss that in the meeting to make sure.
Basically, this is just a conversion of the units. So this is basically the conversion from meters per yotajoule to watt per square meter per millimeter per year. So
yeah, I mean, this makes sense. But earlier there was a map presented with the same units as on the left, meters per joule, but it had the inverted pattern. So it was either mislabeled or.
Because Felix, we don't use the expansion efficiency of heat. We use the integrated expansion efficiency of heat. It's to avoid, so you probably have issues when you're close to zero. And to avoid these issues, we use another, which is the integrated expansion efficiency of heat is slightly different from the Russell definition in 2000. And the variation, the spatial variations are very different because they are impacted by salinity.
Okay.
It's explained in details in Martin et al. 2022.
Okay. All right. Thank you. I will have to do some homework then. Thanks.
Thank you. No more questions. Thanks very much, Bernd, for joining.
Okay, I'll stop sharing.
And I think the next presentation is also virtual by Deirdre Byrne. Are you there? Oh yeah, we can see you.
Hey, should I try sharing my screen?
It sounds a little quiet.
Oh,
do you
is it?
hear her well?
Can you guys hear me?
Yes, that's better. Thank you.
Oh, okay. All right, so I'm trying to share here. Oh, okay.
Nice.
You can see it?
Yep, looks good. Thank you.
Okay, great. So I'm a I'm an interloper in this conference. I am not working on measuring the Earth's energy imbalance at all. I feel like you guys are out here building fine furniture, and I'm more like somebody who's trying to design a chicken coop on a much more practical level. But we thought, myself and my collaborators who are in this conference and doing more fine furniture work like you are, the work that we're doing in this project might be of use to somebody in this conference. So we're going to present it just on the thought that somebody might be able to use the work that we're doing to improve these very exact estimates you're trying to get to. So I'm going to describe an operational algorithm for driving upper ocean heat content. And right now it's only running in the Caribbean and the North Atlantic, but the intent is to expand it to global. And I'm Deirdre Byrne, and my collaborators are David Trossman and Paige Lavin, who are work with me at NOAA and are also associated with the University of Maryland. And now, okay. So you'll notice that the applications that our algorithm is designed for have nothing to do with global ocean energy imbalances. Our primary motivation really is to assist with predictions of hurricane intensity, but the product that we're designing will also, it's a real-time product. It's going to be able to help with predictions for marine heat waves, for ecosystem management, could be used for ice extent forecasting in places like the Great Lakes. It could generate metrics for people. Ultimately, it could help with things like risk factors or planning resilient coastal infrastructure. And it's also being considered for data assimilation into NOAA's operational models. So as I mentioned already, our primary motivation with this work is to improve tropical cyclone prediction at NOAA, particularly rapid intensification over the ocean and rapid weakening. So in order to help with this, as oceanographers, we're trying to get improved estimates of upper ocean heat content and upper ocean structure. So this is a very empirical approach. We've developed a framework, and we will throw in any parameter that we think increases the skill of the method. And you'll see that as we go along. So our primary and first guess method is the geostrophic empirical mode. And then we are using a variety of machine learning techniques and some other things to generate temperature and salinity profiles and upper ocean heat content. So to summarize what the product is, it's statistically robust, it's observationally based, and we have a strong focus on the upper, say, 400 meters of the ocean, and we're more focused on temperature than salinity, although salinity is important. Our output frequency and resolution are really determined by the availability of satellite altimeter data. This is an altimeter-based product. So we are producing daily output at quarter-degree gridded and approximately 10 kilometers on track. And I know there's lots of altimeter people in there. So basically, we're using the 1 hertz data. And in the vertical, 2 decibar vertical resolution down to 1,800 meters. That's the depth is really determined by the mean depth of the Argo floats. We have a fully functional Gulf of Mexico product that will be running on a daily basis during this hurricane season. And we have a pre-operational product in the Atlantic. And this is a very adaptable algorithm. So we don't have any grand theory, really, about what our values should be. We reference them frequently to in situ data. And we just use those regressions. So there is a product like this that is produced daily at NESDIS, and it provides a mixed layer depth, a 20-degree centigrade isotherm depth, a 26-degree Celsius isotherm depth, and it is climatologically based on the World Ocean Atlas. So before I get into the method, I'll just show you kind of a case example. So Hurricane Ida in late August of 2021 barreled through the Gulf of Mexico, intensified very rapidly within about 6 hours, right before making landfall at in the US. This is a map of absolute dynamic topography from the NOAA EUMETSAT radar altimeter database system, which is what we use exclusively for our data. So that's gridded absolute dynamic topography, and over it, I've plotted the track of the hurricane. I've plotted a specific Jason 3 track. Jason overflew this area about 7 days before the hurricane came through, and the big triangle is a location of an Argo float. So the red blob in the middle of the blue, that is a loop current eddy. So there we go. Rapid intensification was coincident with that loop current eddy. Nearby Argo float profile. Okay, so if we look at the Jason track, this is the absolute dynamic topography at approximately at the 1 hertz data, a long track from Jason. It went right across. And from our method, we get this entire transect. I've plotted in black the depth of the 26-degree isotherm. There in yellow is the Argo float measurement. So you can see that our estimate in black and the yellow triangle are very coincident. The current operational product, again, which is climatologically based, underestimates intense events. That's just an outcome of being climatologically based. Right, so there's ours. And in addition, let's see. Right, the maximum difference between the operational product and our product was 80 meters. This is kind of irrelevant for this conference. But significantly, we had only a 3-meter error in our estimation of the depth of the 26-degree isotherm from this particular Argo float, which is about an order of magnitude better. Interestingly, also, this method correctly represented an extremely warm pool of water that was about 44 decibars thick. And that was actually warmer than anything in the database from which we create the algorithm. So that gave me confidence that it's fairly stable. So how does it work? We call it the BLT method for our Byrne, Lavin, and Trossman. So we start with the geostrophic empirical mode method. This is the bacon in a bacon, lettuce, tomato sandwich. Okay, so we derive lookup tables from ocean profiles, and we calculate steric height for each one of them. And we line up all of the in situ data with respect from low steric height to high steric height. And I call it anomaly because I take out a random constant just to make it closer to the range of the absolute dynamic topography of the altimeter just for convenience. We calculate a fit between absolute dynamic topography and the steric height anomaly. And that means every time the altimeter flies over a piece of the ocean, we can essentially make this first guess estimate of what the temperature and salinity look like. So the result is a lookup table where every satellite measured absolute dynamic topography value in the region has a corresponding first guess temperature and salinity profile. As we expand into larger geographic areas, we're not going to be using hand-drawn regions. We're going to be using clusters. So that's our first sort of pragmatic addition. So GEM alone doesn't fully capture the temperature and salinity variability, particularly near the surface. So as I mentioned, we have a framework. This is a result for the pre-operational product with the North Atlantic. We've thrown in a week dependence on latitude, year day, so 1 to 365, and we use sea surface temperature. So here we're actually estimating sea surface temperature, which is why we get it perfectly right. We're just taking the top measurement from all of our profile data. However, significantly, there was no significant bias found in either temperature or salinity. So now I just ran a little case study in the Gulf of Mexico. This is actually using solely the satellite data. So it's a harsher test of the method. This is the test area, Gulf of Mexico and the Northern Caribbean. I simply divided the data in 2 chunks, chunk 1 and chunk 2. They have coincident temporal spans and spatial extents. I had 6,735 stations. Here is the steric height anomaly and absolute dynamic topography. So again, we're using ADT as a proxy for the steric height. The R-squared correlation for both groups together is about 0.92. And here is the shallowest temperature that was recorded by the profile on the x-axis. The y-axis is your geopolar blended sea surface temperature from satellite. Has an extremely good correlation of 0.977. And then I simply try and estimate with just those two pieces of input and the day of the year. I skipped latitude because this is a small test area. I didn't use the dependence on latitude. I then estimate every one of those. So I make the lookup tables using group 1, and then I estimate all the profiles in group 2. So it's completely independent. So these are the results. The colored lines are essentially the limit of skill of our method. This is what would happen if you actually used the steric height and you actually used the surface temperature from your profile data, and then you used our lookup tables. So it has some notable failures, such as near surface salinity. The dashed line here is showing you with depth the percent variance explained by the geostrophic empirical method. And so as you note, as you can see, it doesn't do very well estimating temperature in the mixed layer. The next line is a seasonal estimate. And again, this is just a year day. So it improves, it's a big improvement in the top, say 70 decibars. You can't see it here because I added a third correction, which I don't apply for salinity, which is dependence on sea surface temperature. And the reason I don't use it for salinity is because it showed absolutely no skill in predicting near surface salinity. So the thick black line is basically using satellite input only, 2 pieces of satellite information and the year day, the percent variance that we can explain in all of the group 2 profiles, which would be the blue dots on the lower right map, by using lookup tables made from the red profiles in group 1. All right, as I mentioned, we have virtually no skill in the sea surface salinity. We will be testing, again, this is an empirical method. We throw in anything into our soup pot that we think will help. So we will be testing incorporation of satellite surface salinity soon to see how that will work on improving near surface estimates. Temperature throughout the water column is replicated with a pretty high degree of accuracy. And that's pretty good. The geopolar sea surface temperature added a great deal of skill to near surface temperature estimates. So the skill falls off pretty rapidly, deeper than 1,000 decibars, which for most of our applications is not very important. So the gridded absolute dynamic topography in some ways is a limitation. As we all know, most altimeters just measure essentially at the nadir right below where they're going. And so in the grid, there were more gaps than observations, unlike the sea surface temperature. And that's not to say that the altimetry data isn't great, but if you're going to, in this case, to match the Argo profile locations, I had to use a gridded product. I wasn't using a long track product. It's very unusual to have an Argo float go exactly under your altimeter as it's flying over. And the noise in that regression is going to affect our estimate throughout the water column. But that's life. So summary and conclusions. This is based largely on machine learning. After we develop the algorithm, essentially we're going to be using machine learning to tune it. We're going to be updating the correlations annually for every hurricane season so that they'll remain robust in the face of warmer temperatures or lower salinities or whatever. We've shown that the algorithm better captures extremes because the geostrophic empirical mode is a dynamically based mode. Use of machine learning should allow for, number one, for us to quickly update the profile database so we can include new profiles and annual updates to lookup tables. The high depth resolution provides us with flexibility to derive metrics that people want, and I'm going to speak to that in a second. So we're still working on this. We are testing the use of self-organizing maps for all the subsequent corrections after the gem. We'll be expanding the product to global, and we're also trying to get it near to the coast because that's something that's been requested by virtually every customer we have. And of course, SWOT data might prove incredibly useful for this. What I was thinking when I put this talk in was, I know for people who are making in situ estimates of ocean heat content, such as Tim Boyer, who's one of the conference organizers, it might be useful to be able to, if you get an Argo float that has some kind of enormous heat content, just go back here to this picture, it might be very useful to be able to look at a product like this and get an idea of the horizontal scale of the heat anomaly. And since we're going to be having daily output, you could also potentially combine those with eddy tracking or something else and get an idea of the impact of that heat. Is that just something that appears and then gets reabsorbed, right? Is it like a Brazil current eddy, or is it actually some heat that's actually going off into another basin like you might see in the Agulhas retroflexion? So I was mostly thinking this might be a product that people would use in conjunction with energy imbalance techniques that they're using. So thank you for your attention. That's all I have.
Thank you. Are there any questions for Deirdre? And online? So maybe it's not a question, more for clarifying. So you are looking into forecasting applications, right? And the impact of ocean heat content variability on extremes like hurricanes.
We're more trying to produce the best advice about the ocean that we can. So we'll be producing a retrospective product because the fisheries, for example, people and the ocean service would like to have several decades of output from this that they can use to derive metrics that are independent from, say, a model. And we'll be producing a daily output that the Weather Service can use in any way it wants to improve their forecasts. So we're not doing the forecasting. We're just putting out a product.
Okay. But it's like you're kind of filling a gap because this is some type of instantaneous estimate that you need for these types of predictions, something that we don't have actually measured. Right. Okay.
Right.
Thank you. Any more questions? Okay.
Right.
Thanks very
Paige
much for joining.
Yeah, Paige just mentioned in the chat that we will be evaluating the skill of real-time forecasts by looking at this product. We're also going to be testing assimilating it. So thank you very much.
Thank you. Okay, it's time for the last presentation of today, which is by Pierre Prandi, who's here. Yay, we need to switch the slides. And we're closing today's session with a presentation on recent updates to uncertainties in global and regional sea level trends and accelerations derived from satellite radar altimetry.
Merci. Okay, thanks. So I'll try to stay within my slot because everyone's yearning for a drink, I guess. So I'm Pierre. I work at CLS, part of a team that does monitoring of the performance of the satellite altimetry ocean surface topography observing system. And today I'm going to try to give you an overview of how we estimate and try to verify the uncertainty budget associated with this technique. And there's going to be some overlap with Michael's talk just previously. So I try to go quick on some aspects that have been already covered by Michael. So we've been measuring ocean topography since 1993, and this is the global mean sea level record derived from these measurements. And also we have the opportunity to have geographic information, and that we translate to maps of sea level trends. And the question I'm going to cover in this talk is how do we estimate the uncertainties at climate scale? So there will be no discussion about the capability of the system to resolve small-scale ocean features for mesoscale, for example. And a little bit of a history here. At least in the Toulouse group, this started like this by two papers by Michael Ablin in 2009 and 2015. And at first it was really information taken from comparison between different models or different solutions, and that provided a rough estimate of the uncertainty. Already we had kind of a resolution, different terms contributing to a certain level to the total uncertainty, but everything was expressed as a trend, as an error on the trend value itself. And in 2019, which was updated last year by Adrien Guéroux, we have a much finer description of the error budget on altimetry. And this time you'll see that, I have a pointer. Yeah. So now errors are categorized by their error covariance structure. So correlated errors, there are drifts, and also errors that we commit when we change from one reference mission to the next one. We also addressed the local sea level uncertainty using this method. And I'd like to also mention that so the previous work is based on our kind of an empirical knowledge from what we observe about the error on the system. And there's also been a recent initiative to try to go the other way around. So start from the instrument and actually the raw signal and propagate that down through the whole altimetry chain down to the global mean sea level. So there are many boxes and steps in this processing, and we're trying to identify where are the main contributors to the uncertainty. And in the end, we should be able to do the job both ways and see if they are consistent with each other. So how does that work? Well, we have an error budget, which is each error is described as a line, which has a type and an amplitude, and each line or error is associated with an error covariance matrix, and these do add up to build the total error covariance, which is then used to estimate the uncertainty on the model parameters you're interested in here. So here this will be trends and accelerations mainly. In the altimeter, in the global mean sea level, there are from altimetry, so there are errors coming from the altimeter itself, from the radiometer, from the orbit determination, and from all the geophysical corrections that we need to apply. And I'll try to go maybe quickly because it's not super sexy. Through the error budget. So the first part is the high frequency component, so errors that will decorrelate pretty quickly. And we estimate these empirically from the data itself. So it's there are limitations here because we're not always able to separate the natural variability of the ocean we're observing from the errors coming from the observing system. Hopefully this will improve with the SWOT data. We'll have a few months of a one-day repeat cycle that we'll learn a lot from. TOPEX. So TOPEX is the first mission of the global mean sea level record, and we have knowledge that there are some large errors on the TOPEX, especially on the first side of the mission. We've talked a lot about the wet tropospheric correction derived from the radiometer on JSON3, and this was first addressed by Michael Ablin in 2019, but we updated this value to account for the known drift of the JSON3 radiometer, which was already presented by Anne earlier. And mainly the bulk of this comes from intercomparisons between different radiometers. So for example, Sullivan Tao in 2014 did a triple collocation analysis comparing to SSMI to address the variances and the biases of the different systems. We also have uncertainties coming from the orbits and the ITRF. Again, most of this is taken from either from inputs from the POD team, who do satellite laser ranging to track the radial accuracy of the orbit, and from comparisons that we do between different orbit solutions. Another contribution is the GIA, which also is applied to altimetry and has its uncertainty. So here we use an ensemble of members for the GIA correction, and of course offsets between missions. So we have to switch from TOPEX to JSON1 and from JSON1 to JSON2 and so on. And each time you have a bias to be estimated in between missions. And this is based on the metrics we compute during verification phases between missions. And I'll come back to that later on in this presentation. So here's the result. Michael has already shown this result. I'll just go a couple of. So there's a sweet spot here where the uncertainty is a minimum, and this basically is the longest record we can compute without including the early part of the TOPEX record, which has higher uncertainties. Another aspect is that we would expect this to decrease as we are closer to present, but in the latest release, we have a slight upward trend of the uncertainty, and this is because we updated the uncertainty budget linked to the JSON3 radiometer. So just a quick update on that, because so the findings from Anne were supported by another analysis performed by Joana Fernandez at University of Porto, and this is currently under investigation by our GPL colleagues to track down this down to the instrument itself. What we can also do is try to separate the contributions to this error. So here we are moving along this side of the triangle here, the left side, no, the right side, sorry. And we are moving, when you're moving up along this side, you're moving right on this graph. So you see that at short time scale, so 5 to 10 years, the high frequency noise tend to dominate. And then at time scales greater than 10 years, then the radiometer and the becomes dominant in the error budget, and at very long time scale, then the stability of the reference frame or the uncertainty on the reference frame becomes dominant in this error budget. How am I regarding time? Okay. Keep going. And we can try to do the same thing at 5 minutes at the. Okay, I'll skip that then. So I'm gonna focus on how we try to verify this allocated error budget. So here's an example taken from the JSON3 versus Sentinel-6 verification phase. So during this verification phase, 2 missions are fly together minutes apart. And this allows to a very precise comparison between the global mean sea level measured by both missions. So this is actually on the bottom plot the differences between JSON3 and S6 Sentinel-6 during the period where they were flying in tandem. And this has always been performed when switching from one reference mission to another, except between TOPEX A and TOPEX B, where there's an instrument shift on board that does not allow for that. What we do routinely also is that we check the internal consistency of one mission, and we also routinely intercompare instruments, and there are 9 altimeters flying at the moment on different orbits, etc. So we use crossovers, for example, to perform this type of comparisons. Another thing we do is that with every new standard that comes up, so that may be new orbit solutions or new updates in the instrument processing or new geophysical models, this is an occasion to verify the error allocation that we use. So here's an example taken from an orbit, 2 different orbit solutions, one coming from the CNES POD team and one coming from the GPL. And you see that this is, again, over the Sentinel-6 period, and over this period, you see that the difference in the global mean sea level trend by switching from one orbit to another is only 0.06 millimeter per year. So that's below the 0.1 millimeter per year that we use in our uncertainty budget. So we are not the only ones to compute the global mean sea level. So Adrien performed this analysis wherein intercompared all the global mean sea level records in between groups, and except for the TOPEX period where there are some discrepancies, all groups agree within the error envelope. And regarding trends and acceleration, again, everyone is, all the groups are consistent within the confidence interval. We also try to do comparisons to independent measurements of sea level. So Anne talked about the sea level budget approach. We also do a comparison to tide gauges. So here's a map of the network of tide gauges we're using. And this allows to derive. So it's far from ideal, of course, and tide gauges are only located at the coast. But this allows to derive long-term time series of biases between altimetry and the in-situ reference measurements. So again, with the technique, which has its uncertainty itself, we are able to monitor the long-term stability of the system. And this comes, this would be validating the sea level itself, which integrates all error sources, and this comes on top of a dedicated instrument monitoring efforts. Transponders and corner reflectors for the altimeter, radiosondes and various calibrations for the radiometer, and satellite laser ranging for the orbit solutions, which are all performed by expert teams in their domain. So I'll switch this to, I'll skip this, sorry. So just as a conclusion, so the stability of the altimeter record is improving over time, and so is our understanding of the errors affecting this observation system. And this is a graph, again, taken from the ASELSU project, where we compare the uncertainty budget over the first half of the period and the second, so the first, how much is that, 20 years of the period and the last 20. And you see that we've reduced the uncertainty budget over time, mainly because the TOPEX drift has been removed. And we can probably do a bit better. So this is the third column by addressing the long-term stability of the microwave radiometer on board the altimetry missions. But we will still be pretty far from the updated stability requirements, which are 0.1 millimeter per year. So this will need, meeting these requirements will need, of course, some work and some time, probably. But in the meantime, and I'd like to end with this, maybe this question to the Earth Energy Imbalance community. In the meantime, there's maybe some information that is existent, but and that we know, but we are not communicating well to you. So if you have any, if you feel you need any key information about the altimetry system, we can always try to provide it, at least what is the current state of the art for our knowledge of the stability of this altimetry system. Thank you.
Thank you. Any questions? Or, yeah?
Question, do you expect to improve the high frequency errors with SWOT? Do you expect to improve the high frequency errors with SWOT?
So I don't know if we'll actually improve the high frequency error with SWOT. At least we'll have a better picture of the high. We'll be certainly able to separate the natural ocean variability from the error at high frequencies with this one-day repeat phase. Okay. I'm not sure this will actually translate into an improvement of the error budget. We'll see. But clearly, this will bring new insights on the high frequency variability of the ocean.
Do we have more questions? I'm like pondering your question, but I can't too much right now. I mean, I'm already learning so much about these different uncertainty sources that I wasn't quite aware of before. So I just, need to look at this in more detail because I think it all relates to the non-closure and things like that, right? So, yeah. Okay.
So my perspective would be one of a data provider to the sea-level budget closure and to the EE estimates here. So if you have any request, I'd be happy to talk about that with a drink. Thanks.
Sounds perfect to me. And that means we did it. The first day very successfully completed. Is there anything I should say about tomorrow or now? No? Okay. So thank you very much to all the presenters today, online and in person. We will continue with the poster session and icebreaker in person. I think it's the end for the virtual participants. And we'll see each other tomorrow at the same time. Right? Oh, Jérôme? Yeah, thank you.
Thank you very much to the chairs that worked really hard all day. I'd like to say that there is indeed a poster session, so it's right there. The cocktail is in the room where you had coffee break. I added a pirate poster on the Altimetry Virtual Lab if you're interested to see how we process delay Doppler data, synthetic aperture data from Sentinel-6, Sentinel-3. And the bus is leaving at 8 sharp, maybe 2 minutes before 8, so don't miss it. If not, it's a long walk. It might be under the rain.